Raz, raz, dwa. Raz, raz, dwa. Raz, dwa. Raz, dwa. Raz, dwa. To. Hej.
Raz, raz. We should go to Mars.
We should go to Mars.
Because it's human nature to keep exploring.
Because we want to discover intelligent life in our solar system.
Because establishing a presence out there is a huge stepping stone to limitless possibilities.
Because we can.
Because our ambitions exceed this world.
Because humanity has unlimited curiosity and is destined to conquer the universe for good.
We should go to Mars because it's been long enough.
Because it helps to develop new technologies that are also very useful on Earth.
Because look at Mars could improve the way we look at our Earth.
Because Mars exploration is a huge milestone to extend our vision and discover a new home.
To play sports in low gravity.
And to define past, present and future of our planet.
It opens doors of opportunities for developing talents like us who wish to explore newer horizons and decipher the unimaginable.
We should go to Mars because the sky is no longer the limit.
Space industry is booming all over Europe. And so whether you're Luxembourg or Portugal or Spain or Italy, whether you're big or small, you're trying to be part of this.
I cannot imagine a better way of preparing people for our future projects than, competitions like this.
And all these jobs are there to be had. So if you're studying something that you think has nothing to do with space, check again. You might find out that 10 years from now, you're actually needed.
Great engineers and great scientists building great products. That is what the space industry consists of.
There's something deeply philosophical about space.
And we are the first generation where Mars is just about to be at the reach of our hands. It's a logical continuation of feeding and nourishing that nomadic gene that is within us as humans.
The most important and fundamental part of being human is imagination, this aspiration that we have, which drives us to explore space. So this is something to be proud of, this is something to celebrate.
The cooperation is obviously not just between governments, but it's between the private sector, academics, non-governmental organizations, even students that are combining math and science studies with imagination and creativity.
One person can make a difference and therefore should. That's my assignment to you.
We should go to Mars.
We should go to Mars.
Because it's human nature to keep exploring.
Because we want to discover intelligent life in our solar system.
Because establishing a presence out there is a huge stepping stone to limitless possibilities.
Because we can.
Because our ambitions exceed this world.
Because humanity has unlimited curiosity and is destined to conquer the universe for good.
We should go to Mars because it's been long enough.
Because it helps to develop new technologies that are also very useful on Earth.
Because look at Mars could improve the way we look at our Earth.
Because Mars exploration is a huge milestone to extend our vision and discover a new home.
To play sports in low gravity.
And to define past, present and future of our planet.
It opens doors of opportunities for developing talents like us who wish to explore newer horizons and decipher the unimaginable.
We should go to Mars because the sky is no longer the limit.
Space industry is booming all over Europe. And so whether you're Luxembourg or Portugal or Spain or Italy, whether you're big or small, you try to be part of this.
I cannot imagine a better way of preparing people for our future projects than, competitions like this.
And all these jobs are there to be had. So if you're studying something that you think has nothing to do with space, check again. You might find out that 10 years from now, you're actually needed.
Great engineers and great scientists building great products. That is what the space industry consists of.
There's something deeply philosophical about space.
And we are the first generation where Mars is just about to be at the reach of our hands. It's a logical continuation of feeding and nourishing that nomadic gene that is within us as humans.
The most important and fundamental part of being human is imagination, this aspiration that we have, which drives us to explore space. So this is something to be proud of, this is something to celebrate.
The cooperation is obviously not just between governments, but it's between the private sector, academics, non-governmental organizations, even students that are combining math and science studies with imagination and creativity.
One person can make a difference and therefore shoot. That's my assignment to you.
Ladies and gentlemen, it's my great pleasure to welcome you to the European Rover Challenge 2023. My name is Milena Ratajczak and I'm pleased to greet you here in Kielce, Poland, for the biggest robotics and space event in Europe addressed to the world of science and business as well as to the general public. Space unites people. It's fantastic to see so many distinguished guests and space enthusiasts here, as well as a wide audience watching our broadcast live. The main part of this event is an international robotic competition where teams from around the world present their mobile robot designs, competing in competitions based on real ESA and NASA missions. The competition takes place in the world's largest artificial Martian track, which is directly derived from the surface of the red planet. Similar to the last year, the competition is held in both formulas: on-site, where teams compete with self-constructed robots on Mars Yard in Poland, and remote, where competitors will remotely control the robot physically moving along a track located here in Kielce. This year, more than 80 teams entered the European Rover Challenge, and it's my pleasure to welcome 40 teams during the finals, 25 teams in on-site formula and 15 in remote formula. But that is not all. Apart from the Rovers competition, our visitors presented here, as well as the online guests, can listen to inspiring talks given by the speakers from this stage, and also ask questions during the debates. Those of you who want to experience the beauty, power of science and technology are invited to join many kind of cosmic workshops and science shows taking place outside. This day of European Rover Challenge 2023 is called Artemis Day, while tomorrow we will focus on the Earth to learn about the winners of this year's rover competition. Co-organizers of this year's edition are the European Space Foundation, Kielce University of Technology, and Świętokrzyskie Voivodeship. The role of the host city of the event belongs to the city of Kielce. The event is held under the honorary patronage of the European Space Agency and Polish Space Industry Association. Partners of the event are Polish Space Agency, US Consulate General in Krakow, Mars Society Polska, Polish Space Professionals Association, Poznań University of Technology, MathWorks, Redwire, Agencja Rozwoju Przemysłu, ESA, Big Poland, Poland Convention Bureau, the Polish Tourist Organization. And supporting partners of the event are Pokojowy Patrol, Austrian Space Forum, and Pyramid Games. The event is supported by media patrons: Space Communication Alliance, Spacewatch Global, InnovationUs.com, Ground Station Space, RMF, Forum Akademickie, Join the Space, Polish Science Fiction Foundation, Urania, Kosmonauta.net, Telepolis, CHIP, and Focus.pl. The project is partially financed by the Social Responsibility of Science program of the Minister of Education and Science. Let's learn a bit more about Competitors Zone. It's my great pleasure to welcome on stage the representatives of the jury. Marcin Wygachiewicz, who is a head of the ERC on-site formula, and also from CENER. Jakub Muszyński, head of the ERC remote jury. Dr. Anna Łosiak, science team coordinator, and Wojciech Głażewski, who is responsible for the maintenance task. Good morning. So could you please tell us a bit about your role during the competition? So what's your main task and what are you responsible for?
Okay, so let's maybe start from me. I'm the main judge during this competition. So basically my responsibility is to take care about the teams since the beginning. So we start with the proposals, with the preliminary reports, with qualification of the teams. Then we are checking the final reports, videos, and after all, we are meeting here in Kielce and assess what the teams are doing on the Mars Yard.
Me, together with my team, are responsible for designing Mars Yard, where the competition takes place. Each year we have a new design that is always based on a specific location on the Martian surface, but each year it's slightly different in order to provide new challenges for our team teams during the competition. Later, we are also responsible for figuring out if the teams were able to prepare their planned mission from the scientific point of view, meaning that have they analyzed the area, have they figured out what locations are the most interesting, and then we check how did they do during the competition from the scientific point of view.
Together with my team from Poznań University of Technology, we're responsible for the remote formula of the competition. Some of the challenges already took place before, in time before the Kielce started. But today and tomorrow we have the presentation as well.
I'm responsible for the maintenance task, one of the tasks for the on-site formula. But generally, as a jury, we are also responsible for preparing the Mars yard itself, so to set up all the competition fields. But our main responsibility is to make sure student teams learn as much as they can.
So I can see they are learning a lot from the yesterday and last night observations of myself. So, but could you share some insight about the competition? Is there anything unexpected that happened during this year formula, or any special task that you are very proud of that is impossible to be carried out or super difficult to face? How much this year ERC competition is different from last year? So what's different, for example?
So as far as I know, because I'm spending a majority of time during the presentation and listening to the teams, talking with them, mentoring the teams. As far as I know, on the Mars yard, we were a bit surprised that yesterday there were quite some problems with the rovers. So even the teams that we know they have a very good rovers, they had problems with the tasks. Today, apparently, it looks better. So we hope for that for the end of the day.
Yeah, I must admit that this year we finally managed to prepare Mars yard that is really challenging from the geological point of view. So usually most of the teams were able to get most of the features correctly. This year, only a couple of them managed to do most of them correctly. So we are quite proud of our sneakiness and evilness.
This year in the remote formula, we've experienced a very rapid growth in terms of software development for the teams, because about half of the teams already attended some of the previous editions, and we have their data from the previous editions, and we see that, for example, last year they attempted to achieve some of the objectives, and this year in a different version, they expanded some of their algorithms, and it's very interesting to see how it works from year to year, to see their progress. And it's also sometimes even the same people, because they have, for example, 2 to 3 years before they graduate, and when, for example, when they are at their 5th year, sometimes they can send us some incredible software like it was this year.
With regards to the maintenance task, I would say business as usual. Some of the teams don't come prepared, and it can be seen. Some of the teams came prepared really well, and it's a pleasure to observe young men, young people, young girls and boys who learn something. That's the purpose of this whole event. But the Greece team surprised me because they said that one of the guys from one of the Athens University couldn't find enough people for the team, and they get national. They got advertising that they look for the members of the team for the whole Greece, and they found people from 6 other universities, and they combined national team, how should I call them, and they worked most remotely. They prepared the hardware, put the rover together, and come to compete, and they achieved like really good. It was like awesome.
So it's the first time for a Greek team to attend this competition, right?
Yeah.
So so are there which countries are represented the most this year, and also like in general over last years? There are some teams that comes every year, maybe not the same people but the same affiliation, right? So could you comment on that?
Yeah, so as usual, we have 2 or 3 teams from Poland. We have 2 teams from Switzerland, 2 or 3 teams from Germany. Yeah, so those are, I guess. Of course, we have also the teams from Asia, like from India and Bangladesh. We have also a team from Turkey, of course. Yeah, so those are the majority of the teams.
Yeah, like you said, in remote we have many teams from India, but also Bangladesh. And the newcomers this year, we also have 2 teams from Greece, like Wojtek said before me. Yeah, much less teams from Europe than last year, I think.
I also seen students from Japan. They don't compete with their actual rover. I believe they just come to see how all this event look like. And I think they like it. So hopefully next year they will be here with their rover. It will be kind of awesome.
And could you share some insights about the specific task that the teams have to do, or is it secret?
Maybe I can start with the science task, but let's say with the technical part of this task. I will not take Anya's part and Anya's team part. So basically the rover needs to drive along the Mars yard, looks for some features, but then it also has to take 2 samples, a surface sample and a deep sample. So this is also the place where teams can show how they did mechanisms for doing that, because they need to somehow, for example, scoop with a robotic arm the surface sample, take it to the container, which is on board of the rover. The same they have to do with the deep sample, so they usually have kind of a drill, and then also they need to transport what they took somehow to the container. There is also an additional thing in this task, which is a drone. We have built quite a big cage. I would say it wasn't without any issues, but at least since yesterday it's standing, so hopefully it will resist the wind for today. Yeah, and the teams have to enter the cage and do the fly around with the drone, take pictures from the drone, and then also describe it in the report.
Yes, I think that one of the unique features during the ERC is really a deep connection between the engineering and scientific part, because in order to get good grades and to win the competition, it needs to be not only technically excellent, but also the team needs to know what they are doing and why, and be able to explain why they are going to go to certain location on Mars, or Mars yard rather, and explain what are they going to do there. Because we are not sending rovers to other planetary bodies in order to just ride along the craters. We are going there to do scientific exploration. So this is also what they need to prove that they are able to do. So for example, if they are taking the sample, they need to explain why this sample is worth hundreds of millions of dollars to bring home.
In the remote formula, one of the tasks is to grab a box with sensors in it. It transmits the sensors data wirelessly, and you have its orientation of the box, and you have to stick it in a certain orientation onto the Velcro panel. It seems very easy when you have both hands and you're in there, but when you're in a different time zone, it gets pretty tricky, especially when you have to do it autonomously, like write code for the robot to do it by itself using just the cameras. And I have a story about this with one of the teams. They had the best solution for it, but what they did was all we as organizers do is input a parameter, the angle value, how the module should be sticked onto the Velcro. They had a mistake where we did -20, but they did 20 instead. So it was 40 degrees offset, which resulted in 0 points. If they fixed just one issue with the sign, that would be really a great solution for the problem.
Yes, it's not. This competition is not about like technical stuff, how to fix something, but what for? Because it's really impressing. It's really the real value of our job to observe when they learn something, when they do something that works. I don't know, in their shop, at home, and when they put their rover on the field, something breaks, and they start to think why. What should have been? What we should have done better in order to not to break, right? And that's the value. That was something they wouldn't learn if they weren't facing all these like harsh requirements we stand before them.
Perfect. I know you are super busy today, so I don't want really to steal your time, but it's very interesting what you're saying. I would like to wish you good luck today with what you do, and thank you for spending this time with us. Let's thank the jury members with clapping our hands, maybe. And I guess we will leave you some time for doing your job. Thank you very much. I would like to invite on stage Mrs. Amelia van der Laan, Acting Public Affairs Officer from the Consulate General of the United States of America in Krakow, who will greet us during the Artemis Day of ERC 2023. Hello.
Hello. Can everybody hear me? Good morning, everybody. My name is Amelia van der Laan, and I'm our Deputy Public Affairs Officer at the U.S. Consulate. And on behalf of our U.S. Consulate in Poland, as well as the U.S. Embassy in Warsaw, I would like to welcome everybody to Artemis Day. And on behalf of the U.S. government, I want to thank all of our partners at the European Space Foundation, as well as the city of Kielce. This event not only is something we are happy to support, but it shows the cornerstones of U.S. collaboration with other countries on space exploration writ large. And when we look at the Artemis Accords, we of course know that Poland was amongst the first signatories in Europe to sort of boldly step into a new era of space exploration. But as of yesterday, we are now 29 nations strong, with Germany signing on. And we're really looking to develop the next generation of leaders who are going to take space exploration to the next level. So today, I hope that everybody thinks about ways we as multilateral partners can sort of collaborate on scientific exploration, but also developing youth for the future in terms of where we're going. So with that, welcome to Artemis Day, and good luck to every single team out there. The future's with you, and we can't wait to see what you do, not only here, but on foreign surfaces as well.
Thank you, Amelia. So I will invite you once again on the stage later on for the debate, joining the Artemis debate. So, for now, I will thank you for a moment and invite the next speaker. Thank you very much.
Absolutely, thank you.
So we're gonna have a lot of connections to Artemis. Whoops, today. Okay, we will take care of that. So today, and it feels like with every year of European Rover Challenge, we are closer to space and closer in this day to the moon. And let's welcome our fantastic keynote speaker, Mr. Les Johnson, well-known science fiction author, physicist, and NASA technologist, who will introduce us to a traveler's guide to the stars. And for those of you who sits farther away, that's exactly the title of the book that is here, that was written by Les. The stage is yours.
Thank you very much. Yeah, good morning. I have the privilege today to share with you from a lifelong research into interstellar travel that began reading science fiction novels when I was about 8 years old. I ended up following a career in physics because of that and watching as a 7-year-old Neil Armstrong walk on the moon. I remember my parents waking me up in the middle of the night to see that, and I'm forever grateful that they did. But I have to emphasize I'm not here speaking as a representative of NASA today because I write books on the side, and it's not part of my official duties. So I'm here to share with you as a writer, a dreamer, a futurist, and someone who shares a common vision, I think, with most people here of our exploration, not just of the solar system, but eventually the universe. And so if you can bring up my slides, I'll go ahead and get started. One of the things that I get asked a lot is with the recent discovery of exoplanets, what about exoplanets? Can we go? And I mentioned I was a science fiction reader, and prior to the 1990s, we had no scientific evidence that there were planets beyond our solar system. I think planetary scientists and astronomers knew they would be there. The science concluded that we can't possibly be unique in the universe, but there was no data that said, there's one, and we've confirmed it. So the only place I could read about real exoplanets, in quotes, was in science fiction. And this is some of the science fiction I just loved, including the German language Perry Rhodan series, which has been in continuous publication since the year of my birth, I believe, and was translated into English for a while. There are more than 5,000 exoplanets known today. And when I say known and confirmed, to be confirmed, it has to be detected by more than one method, and that would be a whole lecture in and to itself. But taking this data point as a representative example and looking at the fraction of the universe in which, or our solar galaxy in which these exoplanets have been discovered, which is that little oval on the picture here, you can see that within just this small region of the galaxy, we have discovered lots and lots of potential places to visit. So the question comes back, how do we get there? Is it possible to go to the stars? Can we have the technologies in the future that enable this? Is it allowed within the laws of physics? So the talk I'll give today is firmly constrained in our current understanding of the way the universe works. I won't be talking about hypothetical physics, physics that is not real, or science fictional drives, although in my book, as a science fiction fan, I do have a chapter devoted to talking about those and whether or not some of these that we really love in science fiction films and TV series could ever become real based on our current understanding of the universe. So you can't write a book called A Traveler's Guide to the Stars without paying homage to Douglas Adams' Hitchhiker's Guide to the Galaxy, right? And the very first quote I put in the book is this: because the most daunting challenge of traveling to the stars reverberates from this one problem, and that is that space is really, really big, okay? And that is an understatement. This picture it gives an example of how big our local neighborhood is of nearby stars. You can see the nearest star system at over 3 light years away, which is the Centauri system, and then going outward to about 6 light years, what the potential destinations might be if we ever decide to send voyages, whether they be robotic or human, to explore other worlds. This is a very misleading chart. This makes you think these things are close to us and that it's relatively easy to get there. It's not. Think of these numbers. The speed of light, and you have to forgive me, I think in English units, being an American, so I think of how long it takes to get to the stars, and light traveling at these speeds takes over 3 years to get here. And I do want to mention for those that don't think you'll ever touch the stars, if you go out at night and you look up at those twinkling lights in the sky, some of those are hundreds, if not thousands of light years away. Think about that photon that's been traveling through space for all of that time that falls on your eye. You are touching another star when you do that, okay? So the universe is touching your body physically when you look at the stars. I just gave myself goosebumps, okay, thinking about that. So you are actually touching something that emitted from a star perhaps before you were born, most likely before you were born. And if you look at numbers like that, you don't understand them. We understand numbers like this. I just flew in from the USA. It took me the better part of the day, thanks to connections and delayed flights, to get here. On the space station, They traverse around the Earth every 90 minutes. That's great. That's really fast. If you think about going to the moon, the distance there is comparable to what I've driven my car, which is a 2005 Honda. Over the last 15 plus years, I have approximately driven to the moon. And so I have an intuitive feel for what that distance is. When we start talking about interstellar distances, I would contend that even astronomers don't really understand the numbers because we don't experience them. We don't have them in our mindset. So let's give some examples to talk about that. And let's start in the solar system and create our own ruler, okay, to measure the distances to the stars that we have to traverse. The Earth to Sun distance is 1 astronomical unit. Great, 1 AU. What does that mean? In English, that means 93 million miles. In your units that you're used to, 150 million kilometers. Do you understand what that distance is? No, you don't have any experiential basis for that. So I'm going to put it into a similar system that astronomers do. They use what's called the astronomical unit. I'm going to use 1 meter. Let's reduce this distance to something we experience every day. And that distance, which takes light 8 minutes to get here from the sun, is going to be 1 meter, okay? On that scale, the Neptune distance, the outer planet, is about 30 meters away. It's out in the yard, okay? Out in the front part of the building. It's not that far away. It takes us 10 years, on average, to send a spacecraft to that distance. 10 years to go that far. That's only 30 meters. If you want to get to the nearest star, on Less's scale, you have to go to Ostrava in the Czech Republic, okay? And that's with the distance from the Earth to the sun being 1 meter and scaling it to kilometers. That's the nearest star. That's the challenge. So can we go? Well, the answer to that question is going to be after this because we really want to go to these exoplanets, but remember, I'm a science fiction reader. What I'm worried about is this is where the most interesting place is, right? So when I talk about going to the stars, I don't just necessarily want to go to what's next door. I want to enable us to go anywhere, and are the laws of physics going to allow this? The answer to that question is yes, but you have to think differently, and you have to think on different scales that we normally think of when we talk about space exploration. We are already sending our first interstellar explorer, and that's the Voyager probes. They're on their way out of the solar system. They were launched in the 1970s. They're on their way. Unfortunately, even if they were pointed in the right direction, which they're not, to reach the nearest star system, the Proxima Centauri or the Alpha Centauri system, would take 70,000 years. I would contend that is not practical interstellar travel. I put together a unit in my own head of what is practical, and that practical distance for me is a trip that takes no more than 1,000 years. Now, Les, that's a long time. Why did you pick that? Because we are standing and sitting in a country and a culture that goes back well over 1,000 years, all right? So we have in our experiential base of living and as descendants of the people who built the great cathedrals of Europe or the Great Wall of China, and all of the historic sites, the pyramids, civilizations that have lasted many thousands of years. So I picked that metric as the upper limit of what's really a practical interstellar voyage. Will rockets do it? The answer is emphatically not. Thanks to something called the rocket equation and the fact that you have to pack more fuel to go faster, which makes it harder to move your spacecraft because you added all that extra weight. To go a little faster, you have to add more fuel, which means you have more weight to move, and eventually it just becomes impossible. And chemical rockets, thanks to the release of energy in the chemical reactions in the engines, are really almost as high as the theoretical limit, which means chemical rockets will never get us to the stars. I've also worked on in my career something called electric propulsion, which is how you accelerate a spacecraft using electric and magnetic fields instead of chemical energy, which allows you to get higher performance out of your fuel. You get about 10 times the amount of thrust performance from an electric propulsion system per kilogram of fuel than you do with a rocket. But even those aren't efficient enough to get down to a practical time, which I would consider to be 1,000 years. You're still well over 10,000 years. Then I have colleagues, and I've worked on for a couple of years also in my career, nuclear propulsion, nuclear thermal propulsion, where basically you take a fission reactor, like we have generating power in many countries around the world, and you use that heat to accelerate your propellant to very high speeds to get high efficient rockets. You still can't do it. Trips would still take more than 10,000 years. So even releasing the energy of splitting the atom is not enough energy to get us to the stars. This is going to be difficult. How are we going to do this? Fortunately, there are some rockets, and I define a rocket as something that moves by throwing some kind of reaction mass overboard. Very simplistically, if I were crazy enough to be up here on a skateboard and throw a basketball this way, conservation of momentum would push me this way, and I would be a rocket. So what we need to do with a rocket is get a lot of energy in that exhaust so I get a lot of energy in my motion. So are there different types of rockets that can do that? The answer to that question is yes, there are. Let's begin with the next level of atomic energy, which is not fission propulsion, but fusion. Now recall, as I told you, to think about that photon that traveled all that distance through space to reach your eye. That was created through a fusion reaction in a star. And that's where it takes its mass and squeezes hydrogen atoms primarily together to the point where they fuse into helium. They release energy. That gives the outward pressure that keeps the star from collapsing on itself. It produces the heat and light that we experience here on the Earth. If you could tap that fusion energy to drive your propulsion system, the answer is yes. We could have a voyage of under 1,000 years for a robotic probe. And if we're really, really good at our technology, we could build something that might eventually take humans to that distance. The challenge is we have to get break-even fusion propulsion on the ground. We have to miniaturize it to the point where it will be in a spacecraft and be able to put it in that spacecraft to make it go to the stars. I'm not saying the engineering is within hand. As a physicist who works on teams at NASA where I come up with ideas for missions we go do and new technologies, my team hates it. I'll say, oh, you know, we ought to be able to do this. You guys figure out how to make it work. That comes with some interesting challenges. Some really revel in that challenges. Others look at me like I'm crazy, and of course I replace them on the team because I want people who have a can-do attitude, and we don't always succeed, and that's part of what we do in advanced technology development and as a technologist. So what else, Les? Well, I had the privilege of meeting this gentleman circled on the bottom right of this picture, Dr. Freeman Dyson, a few years ago. And back in the 1960s, he came up with a really crazy idea that might actually work. And that crazy idea was Project Orion. Project Orion, very, very politically incorrect. It basically is, imagine this. Imagine you get a submarine, they're sealed, you stand it on end, you put a big steel plate the size of this auditorium, but much wider, underneath it, and begin exploding small hydrogen bombs, one every 3 seconds, right underneath that plate. Boom, boom, boom. You rapidly get your spacecraft off the surface of the Earth, and you can load enough small nuclear devices in there to get up to a few percentage of the speed of light before you leave the solar system. Of course, you trash the Earth in the process. Details, details, details. But theoretically, this ought to work. It was exciting to meet Dr. Dyson. If I get a chance to talk to some of you later, I will tell you the benefits of sometimes breaking a rule to get someone to tell a story. If you're interested in learning more about this, there's a great YouTube video where they did non-nuclear testing of this back in the early 60s. It's silent because it was filmed on 8mm film before they all had the audio features included, but it's fun to watch. This idea, of course, was put on the shelf and never implemented and not seriously considered. And finally, I have for rockets, I have to pay a tribute to the show that really motivated me. And I see a lot of red shirts out here, and if you know Star Trek lore, that means you're the ones who are expendable when we go down to the planet and the monster will eat you. Sorry, we're going to lose you on a crew member. But this was an episode where they were putting what's called an antimatter bomb to destroy this alien. Well, antimatter is real. Okay? Antimatter is produced at the CERN nuclear reactor facility. Imagine a proton, a nuclear accelerator facility, the CERN and other accelerators around the world. But it's really a different kind of matter. Think about a proton, which makes up an atom, or an electron, which circles it. Now imagine that you take this proton, which by definition has charge of +1, and you create something that looks just like a proton, but it has a negative charge. It's called an antiproton. And the electron, there's an antiparticle for it called a positron. And these positrons look just like an electron, but instead of a -1 charge, it has a +1 charge. There are other differences as well, but those are the ones we think of. And the interesting thing about matter and antimatter is when you put it in contact with each other, it goes through a process which is called annihilation. And that annihilation converts all of their mass directly into energy. And that energy is not all useful. A lot of it's gamma rays, X-rays, secondary particles that come out, but it is a very efficient battery. It is the best battery we can possibly have because it goes all the way to Einstein's famous equation, E equals mc². And that equation tells you that if you have a little bit of antimatter and a little bit of matter, you get a lot of energy released. Just to give you an example, if I had a teaspoon of antiprotons and dumped them on the floor to interact with the protons in this room, it would be in the end of this city, and there would be a major, big, large, smoking hole in the ground where this city and university used to be. That's the kind of energy contained in antimatter. It's produced in nanograms per year. The amount that is produced is not dangerous because it interacts a few fractions of atoms, of a mole at a time if you're a chemist. Very, very small amount. It's contained in magnetic fields. We just don't know how to make it in the quantities we need to go to the stars. However, if you eat bananas and you have a banana in your home, there is a radioactive decay process going on in that banana, thanks to the ground it was grown in, where there's a particle of antimatter produced about every 70 minutes that quickly annihilates in the banana and poses no health risk to you, but you are producing antimatter. So this is one of those fun facts to take home to your family, is when there's a bunch of bananas on the table, you have your own antimatter factory right there in your home. Now, if we could find a way to tap into this on the banana plantations, maybe we would have our propulsion ship to go to the stars. The problem is, we don't just need a few atoms of antimatter or a teaspoonful of antimatter. We need 1,000 tons of antimatter. That's a lot of antimatter. Is it possible? Yes. Do we know how to engineer it and store it and put it on our spacecraft? Not yet. Go ahead, students, that's your homework, right? Do that before the end of my journey through this life. Okay, is there another way? Yes. That way is offboard energy through something called a sail, a solar sail. Now, real quickly, this is something that in my day job, I've spent a lot of time working on. It's available in the public literature. A solar sail does not use any kind of rocket. Its energy source is offline. So this light, this big bright spotlight that's shining on me, or the sun that we'll see this afternoon and tomorrow as we look at the Rover Challenge course, is putting out light, little particles of light called photons. These photons have no rest mass, but they do have momentum. So as that light reflects from me, it's pushing on me. I don't feel it because it's an extremely small push. You would never feel it on the Earth. In fact, it's so small, it's almost impossible to measure here on the Earth. But when you get into space, and you unfurl a large, lightweight reflective sheet that looks like aluminum foil, but is much lighter in weight, and the sun reflects from it, just like the wind reflects from a sailboat, that sail will move. And if a spacecraft is attached to it, it'll drag the spacecraft with it. And this type of propulsion is very, very nice, because for small spacecraft currently, you can build sails large enough to get an acceleration to get them up to very high delta V, very high speed, and very high propulsion performance, so that as you're close to the sun, you can go to destinations that rockets can't take you because they run out of fuel trying to get you there or to station keep in those locations. And the reason for that is because the sunlight is constant. It's never nighttime in space unless you're in the shadow of a planet. So you have this constant acceleration pushing on your sail, which enables you to go to places which you otherwise could not have gone. Solar sails have flown in Earth orbit. I was the principal investigator for a sail that launched on Artemis 1. It was called Near-Earth Asteroid Scout. Unfortunately, that demo did not take place because the spacecraft never called home. We were unable to deploy the sail, but you can learn about what the mission would have been, all the work we'd put into building its 86 square meter sail on the internet. And there's another mission that might happen as early as 2028 that NASA's working on, and it's called Solar Cruiser. And this will be a 1,600 square meter sail, 2.5 microns thick, that would deploy from a small spacecraft and go towards the Sun-Earth L1 to demonstrate its operation. So, this is my ambitious plan. My ambitious plan for off-board energy, which is just as challenging as my onboard antimatter or fusion drive, but it's physically possible, is to build sails that aren't 1,600 square meters, they're square kilometers. And instead of deploying them at Earth orbit, we deploy them close to the sun, where the sunlight pressure is very, very high. These sails would then get enough acceleration as they leave the solar system to get our voyage to the stars in less than 1,000 years. And if you use off-board energy, like a laser, to shine on that sail, you can get it to go faster. So there are different groups that are researching this. One I'm most familiar with is the Breakthrough Starshot. It's a privately funded group to build laser sailcraft to go to Alpha Centauri. They are working on the technologies now, and I wish them great success in what they're doing. But this idea is not new. It's been around for a long time. What's new is the technologies of lasers and lightweight components have caught up and might make it actually feasible. So, I really want to talk about some of the practical aspects right now. Let's assume we have a fantastic engineering team that instead of building a rover next year, they build my antimatter system or my laser-driven solar sail, and we're going to do a test. And we want to send that to the nearest star, a small spacecraft, something reasonably sized that might be able to send data back. So let's assume that something a kilogram in mass, with whatever the propulsion system is, and that kilogram of mass is roughly equivalent to a pineapple. So if you've been to the store and held a pineapple, you're holding the size of the spacecraft. Let's launch it, and let's assume we do it with 100% efficiency. So we get up to 10% the speed of light. This is the energy equivalent contained in the kinetic energy of motion of that satellite. It's traveling to the stars at 10% the speed of light. And if we miss the flyby of the planet to take pictures, and instead we hit a planet around Alpha Centauri, we would hit with an energy equivalent of 7 Hiroshima atomic bombs, and we would have just started our first interstellar war. So we want to make sure that if we send a robotic probe to the stars that's not going to slow down and is just going to fly by and produce science, that what we do with that spacecraft is we don't hit the planet, okay? That would not be a bad day for any relations with people or creatures or whatever might be on that world. Lastly, before I get to the questions and answers, I address this in the book because I'm asked this question a lot. Les, are you talking about abandoning Earth? My answer to you is absolutely not. We live in what is perhaps, for our form of life, a unique or nearly unique, wonderful place to live. We are adapted to live here. I think we ought to be using space technology and resources to help save our planet so that we can have our ducks in a row to expand into the solar system and eventually go to the stars. And I contend that there is a very high moral value here. I would contend that in this, what looks like largely empty universe, largely devoid of life, we haven't found other life on other worlds, and if we do, it's going to be rare and in niche places. Most worlds are dead and will never have life. Life is good, okay? I contend that preserving life is a positive moral value, and I mean that from the amoeba to the human. All forms of life are worth preserving, except a few viruses that we all know and don't like very well right now in our culture, right, in our world. However, I can argue that the love that I feel for my children, the enjoyment you get out of seeing art, great films, reading good books, that is a high moral value, and that is good, and that is worth preserving. And because the Earth is a fragile place, all you have to do is look at geologic history. This really was driven home to me when I first read about something that happened many tens of millions of years ago called the Permian extinction. The Permian extinction was apparently caused by massive volcano eruptions in modern-day Russia. These volcanoes put so much soot into the upper atmosphere that photosynthesis stopped. The oceans became acidic, and 90% of all the species on Earth ceased to exist. Then we had the KT impact, which ended the dinosaurs, which a lot of space enthusiasts are familiar with because we believe it was caused by an asteroid impact. Life on Earth is precious and fragile, and we need to make sure that this moral good, which is life, is spread throughout the universe. Now, the other question is, Les, this sounds like colonialism, imperialism. Are you going to repeat the histories of the past? My answer to that is, I sincerely hope not. And that's why I look back to that visionary program, Star Trek, because I think that should guide our exploration of the universe. They had what was called the Prime Directive, where they would not interfere with other cultures if they found them. I think we ought to extend that to be, even if we find microbial life, that's the province of science, not human settlement. We need to be finding worlds that are dead, that otherwise would not have life, and undertake the thousands of year process to terraform them, to make them adaptable to our life. Now, these are all different thoughts that I have written into that book, but I also write science fiction, where I'm able to explore some of this and what it means to be a person or a human in this fantastical future that's trying to actually accomplish some of these tasks and the challenges you'll face. So if you're interested in my work and want to transition from the popular science nonfiction, I also write science fiction where I actually can delve into the whatever the engineering is, here are the challenges we have to face at the end. So to conclude this presentation and get ready for the panel discussion, and I hope we have good time for question and answer, is the universe is full of potential. It's full of planets. There's a lot out there to go see. Physics says we can do this, not just from a propulsion point of view, but from power, from the fundamental aspects of human life support. There are breakthroughs in biology, synthetic biology, genetic engineering that might enable us to store people or to take us and go to the stars. We just don't have the engineering side of the biology intact yet. The life support systems that we're developing for the space station, for exploration of Mars, are getting very efficient. Perhaps these can be adapted to keep people alive for long journeys to the stars. So within the laws of nature that we have today, it looks like this is something we crazy humans on this third planet from our star might be able to do. And I would contend we need to start thinking about it, getting the world to think in a positive way so that maybe that'll spin off and make more people more positive about protecting our planet today so that we can have that Star Trek-like future that we want to have. So the question is, can we get here? Can we get to the Centauri system and look back toward that one star in the sky, which is our star, the sun? Okay? The answer is, I think we can. Lastly, I have to give this quick story. I was asked in a management class, one of those things you have to go through when you work in a big organization, what do you want to have as your professional legacy? I would like my professional legacy to be a footnote when the history of the first settlement on a planet around another star is written. And they have this 1,500-page book about what it took to get there. I would like for my work to be an endnote or a footnote in that book. That's my career goal. I will never see that, but posthumously, that's what I'd like to see happen. There is a group that thinks about this. It's called the Interstellar Research Group. I'm a founding member. We've had 8 meetings. Our last one was in McGill University in Canada. Our next one will be in 2 years in Texas at Texas A&M. At Interstellar Research Group, irg.space. I encourage you to look into that if you want to find other forward-thinking people who look at the challenges of ultra-deep space exploration. It's a nonprofit group. They do give some scholarships for the students that are out there. It's definitely worth looking into. And last is the blatant commercial message for my books and what I write and talk about and what has enabled me to be here today, which is talk about my latest book, A Traveler's Guide to the Stars from Princeton Press. Came out about a year ago. But I would encourage you, I don't just need people to buy the book or whatever, write to me. I love hearing from people who've heard my lectures. I've been getting a lot of email as a result of some of the lectures I've given recently. I'm not the fastest person to respond, but I always respond. I will not ignore you. So if you have questions, would like to reach out, share your thoughts, get involved with any of these activities, please feel free to do that. I'd love to hear from you. Thank you very much.
Thank you very much, Les, for your inspiring talk and a lot of interesting things that we learned. Actually, I'm an astronomer, just a moment, and I just look at the book cover or your of the book that you just mentioned. I think these constellations are faked, aren't they?
They are.
Yeah. Okay. Okay. Questions? Do we have? Yeah. Just a second. Let me
materials here.
By the way, the author doesn't have anything to do with the cover art. That comes from the publisher, and I'm very pleased with this art. I love what it does. It's beautiful for me.
Yes,
I love it.
I have a question about the solar cells you're asking about. You said that they are going to be very, very huge, and I want to ask, will the solar cells be foldable, or and aren't you afraid that, for example, micrometeorite will hit this? And how do you want to prevent that?
I get asked that question a lot, and the nice thing about this material from which sails are made is it's very, very thin material. 2.5 microns is like thinner than, for those of you who have a lot of hair, it's a little thinner than your hair. And the nice thing about that is micrometeorites are traveling really, really fast. And so their interaction time with the material is very, very low, and they don't lose much energy. And the damage in a spacecraft that gets hit by a micrometeorite is usually they're pretty massive. And that micrometeorite hits going 18 to 23 kilometers per second, okay? And it travels through a lot of matter, and it loses energy, which becomes heat. And that heat's in a very small volume. In our terms, we call that a bomb. And so it does a lot of damage. But if a sail is so thin, it doesn't lose much energy and it doesn't do much damage. So it basically pokes a pinhole in the sail, or something maybe the size of a pea that's traveling that fast. And the theoretical models for the propulsion of the sail, it will get hit. And it will get hit in a lot of places. But we can account for up maybe 3% of the area loss from that and still have all the performance it needs to do the mission. And the nice thing about the sail material is also that there's embedded ripstop, like in a parachute, so that if you get a hole and it starts to tear, the tear will be self-contained. So that's a real risk, and one we're working to mitigate, the teams that are doing this, both the teams at NASA, the European teams, and others. Good question.
Yeah, so you were talking about flybys, and for example, in the Centauri system, and those are obviously uncrewed probes, so I guess that's to observe like exoplanets. But if we develop technology to go ever faster and far away, wouldn't it be more efficient that you don't go all the way to Alpha Centauri, but you go to a place very far away, you set up a telescope, and you use gravitational lensing to just observe the surface of these planets without having to go there?
Yes, and in fact, I cover some of this in the book, and I'm also familiar with the work of Dr. Slava Turyshev at JPL, where he's looked at using the solar gravity lens to image exoplanets. Real quick, for what that means, that for those folks who may not be familiar with this, gravity bends when there's a lot of mass, thanks to Einstein, we know this, and the sun actually bends space-time, so that light traveling in a straight line through space-time, when it travels near the sun, following a straight line means it's not straight in Euclidean space, but in Einstein space, it bends. And there's a focus at 550 astronomical units or thereabouts, where light from distant stars is focused by our sun, and that's called the solar gravity lens. And so it is possible to take something of a little bit less capability than the Hubble Space Telescope, put it at the solar gravity lens at a distance of 550 astronomical units, which for reference is much farther, it's 5 times farther than Voyager has reached in 45 years, so we have to do better at speed. But if you put a telescope there and you look in the right place, theoretically, you should be able to image exoplanets and see if someone there has the lights on at night. Okay? So the answer to your question is, yes, we can do that. No, it is not better. And the reason I contend that it's not better is because I believe a big part of exploration is you going there. Humans want to experience these things. I want to take what is good human life to these places. So I think we'll have phased exploration of the stars like we have phased exploration of space now. Before we sent our first person to space, Yuri Gagarin, we sent Sputnik Explorer robots. Before we sent people to the moon, we sent Surveyor. The Russians sent missions to the moon. We're sending robots to Mars as we seriously start thinking about sending people to Mars. I think we ought to be sending flyby missions, orbital missions, maybe telescopes that we launch to put at Alpha Centauri's solar gravity lens to look at other exoplanets. I think that next it needs to be followed by us. Okay, so I would not limit it to just robotic exploration.
Arthur C. Clarke spoke about that there was a transition from sail ships to steamships, but the space exploration is a transition from rocket ships to sail ships. What do you think about using solar sails as a basis for maneuvering, let's say, in-system freight craft carrying bulk cargo or commodities within the solar system?
I've looked at that. And the fundamental equation to remember for a solar sail is not one that'll be alien to most people. Force equals mass times acceleration, right? And the force of sunlight at some distance from the sun is constant. So if you want to have a big acceleration to get your spacecraft going to high enough velocities to cover these distances rapidly, your mass has to be very low. And I get asked the question, why is it that solar sails are being talked about now more than ever, and they weren't talked about 25 years ago in practical terms, even though the sail materials were already available for these smaller, up to 1,000 to 2,000 square meter sails. That thin film was available well over about a quarter of a century ago. Why is it only now that we're doing it? The answer is because spacecrafts have gotten lighter weight. The small sat revolution, the phone in your pocket, the microelectronics, the avionics in spacecraft has made them small enough so that the mass is small enough that a sail that we can build today is large enough to give them a good acceleration. Carrying cargo is heavy. It could be tons. And you could build a sail to do that, but you have to do it with square kilometer class sails. So as we build these big sailcraft in the solar system, to have supply routes of supplies going to all the planets in the inner solar system, we're also building our interstellar sail. And I want a small team over here that's taking that technology and sending those robotic probes to the stars. So I think it's viable, just really hard to do.
Hello. Sorry for my English. I built full electrical promotion, and nobody take me serious. How to change that? I write to NASA, I write to ESA, no response.
That's a good question. The problem is NASA, ESA, and I as an individual get a mix of emails from people. Most people are very well-meaning. But I get I would say 80% of the ideas that come into my email box, whether it be at work or in private, are ideas that after just looking at a cursory level violate known laws of physics. I'm not saying yours is there. I'm just saying that's probably 80 to 90% of unsolicited stuff that comes in the mail. Therefore, an individual probably can't take action on that because it's hard to filter through all that. The space agencies, and I can speak for NASA, and I can speak for some of the private groups who issue solicitations, calls for technology. They have a proposal process where they bring in independent reviewers to look at it and evaluate. Oftentimes, good ideas don't necessarily make it through, but a lot of them get a serious review through that. And in the United States, NASA has a program called the NASA Innovative Advanced Concepts, which funds some pretty far-out ideas, but they go through a rigorous peer review process to make sure that less is rule number one here, which is known laws of physics aren't violated to do it. Doesn't mean we know how to do the engineering. That's the challenge, and that's okay. But there are solicitations out there, they may not be frequently enough, that allow people to get those ideas out there. There's also journals you can submit to who go through a peer review process. And the whole point of that process is to take those good ideas and make sure they're really good. And don't have some flaw and they get published and then publishers have to retract their papers. Like that never happens, right? You all haven't been reading the news. So anyway, that's my advice to you. And we can talk about that in the hallway a little bit more if you'd like.
I tested only on Earth. It's not tested on 0G. Thank you.
Mm-hmm.
Thank you for a great talk. I wonder what would be the achievable discovery regarding the extraterrestrial life that would excite you the most?
What would be the achievable discovery that would excite me the most? I think just the discovery of life on another world would be awesome. in terms of knowing that there is other life out there. The second question would be, is it a cross-contamination with Earth, right? Because we have meteorites on the Earth that came from Mars. There are probably pieces of the Earth from early stages where we had asteroid strikes that are on other planets. Is it common history with Earth or otherwise? But I guess the ultimate would be is if we heard a signal that said, hello, we're here. Is there anybody else out there? And I wrote an essay for my science fiction publisher, Baen Books, and it was called The Aliens Are Not Among Us. And in that essay, I explore the idea of the famous Drake equation of what's the likelihood of there being someone else out there somewhere who might be in a technological civilization trying to communicate. But then I put that in context not just of deep space, but of deep time. And the Earth's been around about 4.5 billion years. And the likelihood of there being another intelligent civilization that's at a comparable stage as we are, that we would even recognize as that's trying to reach out and make contact while we're listening, considering we've only been listening for 100 years, out of 4.5 billion years, the likelihood of someone else being there at about the same time as us is very, very small. And so I'm very skeptical that we're going to hear anything. Not that we shouldn't look. We should be looking, right? But I'm very skeptical of that. But I think it would be fantastic to hear that. And then the implications of that in our culture are a lot of fun to explore also, right? Because that would be something that the world's religions, philosophers, scientists, ethicists, everyone would have to come to grips with. How did they get there? What are they like? Do we answer if they reached out to us? So that would be something we'd really have to look at. As a person of Christian faith, I have no limits on what I believe the creator of the earth and the universe might do, and there might be other life out there. From a naturalistic point of view, it's entirely possible that life developed on other worlds. So I won't give it a zero chance, right? I just think the likelihood of it being right now while we're here listening is roundable to zero. But I hope that I'm wrong.
Thank you very much. I think we can finish this Q&A question for now, because that was a great introduction to the debate that we're going to have now together with other panelists. So, so the first panelist is obviously Les. So I will invite you here. The other guest is Amelia van der Laan, that you know already as well from the U.S. Consulate General in Krakow. So please, Amelia. It's my pleasure also to welcome here Professor Gabriel Patrocínio from Instituto Superior Manuel Teixeira, Gomez, Professor Patrick Vaughan from Jagiellonian University, Department of American Studies, Kamil Muzyka from Polish Space Fiction Foundation, and Helena Milewicz, Head of Products at KP Labs. So, yeah, please take a seat. So we have less microphones than people, but I hope we will share it. Is it enough space for everyone? So, well, some of you already have spoken today, so we know what's your connection to space. But I would like to shortly ask you for introduction and just saying, what's your connection to space? What made you here, and what made you inspired about space? Was there an event or something, the moment that you started to think that space may be the thing that you can talk about, like we're talking today?
Okay, I think I start. A few months ago, I was taking part in a discussion with Dr. Thais Russomano and Dr. Anna Karahan, and tell them about an experiment I did with my students of design theory and criticism to use the movie Arrival as to start a conversation about what could be brought from this movie to our classroom. Then I got invited to be here and talk about it.
So you present the design community, can I call it like this?
Yes, I have the honor to represent the design community, the communication design course at our university.
Thank you.
Yeah, So for me, as a US diplomat, I think that so much of what we do is build international connections globally. And for me, I've been a long time space fan, going to space camp when I was really, really young. But I always view the sort of connections we see in universities of what the next generation is able to do in terms of bringing global partnerships and cooperation kind of to the next level. And so that's why the U.S. Consulate likes to support these things, but also shine a light on just the amazing collaborations that it takes to do something like get to space. When we look at the lunar landing, that was really an extraordinary achievement in humanity, and all the places we'll go going forward in the future.
You just heard me give the lecture about what motivated me, and that was, of course, watching Neil Armstrong when I was 7 years old. But I have to give a lot of credit to Gene Roddenberry and Star Trek. A lot of my colleagues at NASA were inspired by Star Trek, and I'd say it's probably the single most influential thing in my early life that got me interested in studying science, physics, and going to work for NASA. And one quick note, space camps in my town, Huntsville, Alabama, so you were there, so that's great.
Okay. I got into space probably like most of you. I watched Star Trek as a kid. I didn't fully understand it, but I watched it at 5 o'clock regardless. But I reviewed a book by a diplomat or a geostrategic thinker, Zbigniew Brzezinski, whose son is now ambassador here. And I ended up writing a biography about him, and it was a lot about geopolitical strategy and so forth and that sort of thing. But I noticed he wrote a book in 1970 called Between Two Ages. And the thesis of that book is, this is a real revolution, and it is happening so gradually we're not appreciating it. And he made the point that we might not have flying cars, right? Everyone always says, where's the flying cars? But we have penicillin, central heating, air conditioning, satellites, all of these things that we take for granted. And he called that the real revolution. And it happens so gradually. And it's so amazing sometimes that the technology that we take for granted, like, for example, you know, what would John D. Rockefeller pay for this, right? And vulcanized rubber or anything that, these simple things that we take for granted. And I remember when I was a kid growing up in California that I was always amazed about these new things because I was a 7-year-old kid. And my favorite thing to do was go with my mom to the grocery store because they had these doors that opened automatically, right? And I thought it was magic. I thought that was Aladdin. And it made a nice bing sound, which made it even better. And my mom would, of course, say, you can't possibly realize how annoying that is. But it's just an example of the things we take for granted now. And I remember even when I was in high school, George H.W. Bush lost his presidency in a way because he was amazed by a checkout counter that automatically scanned his groceries. And he was like looking like this was from the Jetsons. And the checkout lady or the person in Kennebunkport was probably making $5 an hour, and she's been doing it all day. But it just shows you the technology that we depend on is real, and we take it for granted, I think, and space is only part of it. And that's kind of what got me interested, but Star Trek mostly.
Okay, so I represent company here, KP Labs. We're based in Gliwice. And what we do, we are focusing on onboard data processing from all the different levels, like software, hardware, data processing units to perform, onboard operations, and algorithms. So this is my focus, and this is what I'm responsible for at my job, at my work. And privately, I think what brought me to this space is curiosity. It's curiosity to myself, to others, to the world, and to the space, like the world, not only the Earth that we live in, but also worlds like the whole universe, and something that we cannot imagine because the scale of the space is so huge that probably our mind is not able. Okay, we can calculate it, but we are not able to understand these numbers. And when we are speaking about millions and billions of years, we still are not in a position to understand because our life is so short. So I think this curiosity, this is something that I follow it, and here I am.
So basically, I'm mostly a lawyer, but also I do education, space education, science advocacy, and I sometimes write either sci-fi short stories or long-winded essays on some topics in science fiction, like space mining, manufacturing, world ships, self-replicating technologies, and so on. Well, how was I introduced to science fiction? Most of people said Star Trek. I was introduced by three things. Gandahar, the French animation, Star Wars, and also giant robot from Japanese or American animation. It was my favorite thing, robots, aliens, and so on. And it was my father who introduced me to science fiction. He was, well, he still is an engineer, and his focus on science fiction got into me because his focus wasn't on characters or the plot, but was on devices. What technologies those characters use. Like, see, this he used this, or this armor did that, this vehicle had this and this system, so they could do this and this. So there were solutions to some problems or some gizmos that they use, like James Bond, for example. But anyway, this is well, the biggest focus of science fiction is mostly the technology, and the second is how it impacts people and their way of thinking. And I use mostly science fiction as a part of my research, because I have to do academic research doing space law, but I also sometimes delve into space operas and see, oh, they use an analogy from maritime law. This analogy of space salvage, like maritime salvage, but translated into science fiction. Well, you can see it in even the Aliens. James Cameron's 1986 movie even opens with the reference from, well, there goes our salvage, because the person in the hibernation chamber is still being treated as a crew, and if it's a crewed ship, it's not a wreck.
This was a very nice intro, and actually it showed how wide range of interest we have sitting here. So we have representatives of diplomats, researchers, teachers, designers, writers, technologists, entrepreneurship, and entrepreneurs, and even space lawyers, as far as I understand, and also writers. So we can see that the space inspires not only space engineers that we can see actually competing at the European Rover Challenge here, but also very broad range of people. I wanted to ask an open question. If any of you would like to answer, I'm very happy to listen. How strong is the influence of various means? Like we've heard about like sci-fi books, but also movies or some art or literature and so on the perception of cosmos. So it's like it gives us it gives us some kind of like view of a cosmos that doesn't have to be real, yeah, to be honest. But how do you feel, like how strong is it? And do you feel that there is like this kind of crash sometimes in between our perception, imagination, and reality? That if we start to get deep into to the topic, would you like to comment on that?
Very quickly, I use not only science fiction movies, but I have discussed books by Asimov, Ursula K. Le Guin, and Stanislav Lem with my students, and it's a good help to our conversations and our thoughts about designing. You are designing the future. You are doing something for the future. So it is a good thing to use always.
Okay, so from my point of view, we have a lot of discussions on sci-fi forums, especially the ones that are ran or co-ran by the Polish Science Fiction Foundation, where when there is a discussion, for example, there's the series called The Expanse, or for example, the movie Ad Astra. For example, the Ad Astra is a good example because it's a Heart of Darkness movie, which enables some discussion about being a scientist and being a astronaut in a post-astronautic, post-Apollo era where there is no longer the right stuff. There are people who actually perform missions. Anyway, and many people pointed out, no, this is an inaccuracy. Like, for example, when the dust hit, when something happened, or microgravity doesn't work that way. This doesn't work that way. Even you watch The Expanse, you watch many other shows, and people are pointing out, no, this doesn't actually work that way. And it's education. Like, for example, even Andy Weir, when there was the discussion about The Martian, he admitted, yes, I was wrong about dust storms on Mars, but I see it as some people view it as being an inspiration. And another thing we have to point out, if you watch any historical movies about, for example, well, European medieval history, Knights, the 30 Years' War, the Crusades, many people will point out, no, they didn't use boiled oil, or they used the pavisas and crossbows and so on. It's very educational, because if it's a starting point for you, like you said Star Trek, I said Star Wars, at some point no, it doesn't work that way, but you have to go deeper into it. But if Star Wars, Star Trek, Stanisław Lem, anyone, or Jerzy Żuławski, like in the case of the Becker's wheel for the lunar roving vehicle, if it makes you think about something, it actually made a point. It's the best thing science fiction can do, even if it's not directly inspiring you to create an invention that is being similar to the one showed. It's for you to think, okay, this doesn't work that way. So I'm curious, like you said, it's curiosity what drives you. So how does it work? What is space? How does Mars work? Or what's the magnetism? What's radiation? What are other factors that those other people said were missing in this film?
Well, I would also say that art and science fiction movies, etc., they simplify by intense. And this is good on one hand, because people who are not specialists, who are not experts in this specific domain, can get the point. So we simplify it. But on the other hand, it causes the problem that people think that it's so easy, so why we're not going to the moon again? So what's the trouble? Why it's so easy and we're still not there? I mean, again, so this is one thing, but there is another thing that is kind of inspirational, that people think that, okay, I have no limits, no boundaries, and I can imagine everything. And this is amazing, because sometimes when you go to the engineers, they say, no, we cannot do this, there is no technology in place right now, we have limits in the, power, in this and that, in size, in form factor, etc., radiation, whatever, all the long list with the limitations. So I think it's good to have this kind of inspiration, because we are unlimited. And again, what was already told when there is James Bond speaking to his watches, and right now we're doing exactly the same, and we're getting used to it. So I would say that this is a great example of how sci-fi, how movies, how art, etc., all the creative things could bring us to the future, even if we're not noticing it, even if it's not the intention. So I think there are always pros and cons in this topic.
I teach a science fiction class, and I like to teach it as a history class. So we start with Frankenstein, naturally, but we move through the 30s, things to come, H.G. Wells, and we go into the 50s, the fear of alien invasions in the 60s, scarce resources in the 70s. So I think science fiction is an ethical class. It's a religious elements to it. There are moral elements to it, and of course, scientific elements to it. I think one of the things about space that is related a little bit to what I said a minute ago, is how fast we got used to landing on the moon and said, yeah, that's it. What's the big deal? We're going again, right? And, this is 1971 or 72, and Cape Canaveral, the launch site is almost a ghost town by 1972 in terms of real estate and things like this. So we as a species, we get used to things really fast. And I think Arthur C. Clarke mentioned it was a little bit a case of rising expectations, in that the Saturn rocketry and so forth was so far ahead of its time. He compared it to the race between the Norwegians and the British to get to the South Pole in 1908, and we didn't really have a fixed colony there, or whatever you want to call it, a laboratory, until 1958. So I think we had some inflated expectations, and I think we really take for granted how much effort that went into getting to the moon. And then I teach the class mostly on film, and I show the film called Capricorn 1, which is about faking the moon landing, kind of the Kubrick conspiracy theory, but they were going to Mars, and O.J. Simpson's in it, and James Brolin, I think, Elliot Gould. It was a star cast, but the basic idea was, boy, we got used to going to the moon so fast, people are saying, what's next, right? How come you're not in Mars yet? It's 1977, right? So part of that, I think, was publicity. Von Braun was talking about, apartment buildings on the moon, and by 1979 and things like that. So some of it's just publicity, but I think my students are more concerned with things like Black Mirror, Her, these things about technology that are affecting their everyday lives more than they are space. Because I think, as we just heard from a very excellent presentation, space is really big, and it's just not as realistic as it seemed. In 1939, at the New York World's Fair, they're talking about Venus as a dinosaur planet, like with the jungle atmosphere. And the year before that, of course, the radio broadcast, The War of the Worlds, people legitimately believed the Martians were invading. So I think we're much more realistic now as far as space. But that's kind of boring. Nobody made movies about the space shuttle, which was basically a space taxi, very practical, but nobody wants to watch a movie about it, right? So.
If I can get an advance. Patrick, but because you spoke about Black Mirror, I want to put this question out in the open. Why is it that, for example, if we have science fiction where space is hard, people can die, everything can go wrong, and we still love space science fiction, but when it is robots can break down, robots can rebel, robots can do anything bad, your cybernetics, your implants can go haywire, we don't want it. I see from throughout sci-fi fans that those that see, for example, this and this many people died during the Mars operation and so on, but the colony carried on, and it was like, yeah, space is hard, but it's good. But if you do the same thing about robots in society, it's a dystopia.
I would say that, it is a very good point, but when we look back on how we were exploring the Earth and how many people died within the whole process, or we were using humans and also animals to, conduct different experiments to understand how different cells work. And actually, we're still keeping doing it, maybe not humans, but, animals, and they're all, the ethical questions. So I would say it's pretty much what happened in the future, in the past. So it's, again, might happen in the future, I don't know. But this is something that, we need to keep in mind, that when we were exploring our own home, Earth, it was exactly the same.
Yeah, I think the Star Trek was essentially like Horatio Hornblower, right? I mean, so the strange new lands, and for the British Navy in the Napoleonic Wars, that was the Star Trek was sort of a.
The wagon train, actually.
Yeah, Gene Roddenberry wrote westerns, I think, before that, right? So part of it is just a space western, Star Trek.
So I wanted actually to follow up with this making space simple and bending the laws of physics and so on. In your opinion, how strong can we get into that? I mean, like, at some point it's okay, but we cannot go too deep with that, right? I mean, and just a little comment on that. One of the worst things that you can do, you can go to the space-related movie with a group of space actually experts, because they will destroy the whole movie. So, right? So,
guilty as charged. I have to tell you how I deal with it. And how I deal with it as someone who writes science fiction. I'm not afraid of dreaming, right? But in the science fiction that I write and the science fiction I like to read, and I'm going to give this two different caveats. If it's something that's touted as serious science fiction, i.e. this could happen in the future, if they invoke unknown things or things of physics or things that are blatantly not physically possible in the movie or in the book, I start losing interest. That doesn't mean I didn't enjoy Star Wars. Because going in to see Star Wars, I knew from the outset they are not trying to be a serious science fiction movie. This is an adventure story set in a fantastical universe that whatever, right? And so it doesn't bother me. I love it, right? So I think part of it is where the creator is. And if the creator is doing a movie like we talked about, Arrival, right? I think they were taking themselves seriously. They were trying to write a real what if, right? How the aliens got here is immaterial to that story. Okay, whatever, any of these options for propulsion. The story is the individual, the communication, and they really delved in to get that part of it right. I loved that movie, okay? So for me, I think it's part of the intent of what the book is. There is a movie, I'll go ahead and say it, Gravity, okay, that tried to take itself seriously, but got so much wrong that it was just impossible for me to enjoy. So that's someone who works in the biz and does fantastic writing as well as loves fantastic fiction as part of what the intent is.
Yeah, I mean, I think in general, this is a really important question to ask. And I actually hearken back to my 9th grade science class in Santa Fe, New Mexico, with our physical sciences teacher. And one of the things he really brought to the table was using your critical thinking skills when you look at science fiction portrayed either in the media or in science fiction itself. And he had our 9th grade class watch part of Armageddon. And he gave us a challenge to find 30 scientific errors in 1 minute clip. And, you know, all of our 9th grade class sort of got together and we were able to identify different things where it's like suddenly you're seeing wind on an asteroid that's completely outside the bounds of what you'd expect in physics. But you were sort of developing the skills for how we think critically about problems, not only like here on Earth, but also in space. So even if we are portraying space in a way that maybe isn't scientifically accurate, there are still lenses that we as educators, that we as diplomats, that we as people within civil society can use those lenses for how we think about big global problems. And I will forever be grateful to this science teacher for sort of having us hone in on what those differences were, even though there were scientific inaccuracies. So I think it all comes down to how we look at things and how we think about problems.
Yeah, I think one of the things that, again, I'm going to go back to this, we don't appreciate how much progress has been made. If you look at somebody like my grandmother, who was born in 1900, she's not with us anymore, but how, you know, that was before the airplane. By 1950, they have supersonic jets, right? And I grew up in California, and a familiar sound I heard almost all the time when we were at school, and it would rattle our windows, was a sonic boom. We had no idea what that was, and the teacher said, don't worry about it. But what it really was experimenting out at Edwards Air Force Base, the right stuff. And if you ask me, that Chuck Yeager, that's science fiction in 1900, but in 1950, it's, oh, you know, that's a big deal, right? So I think one of the things that we should do more is appreciate how much R&D went into this revolution that we're all enjoying right now with these modern conveniences that would have been, even 25 years ago, who would have thought about the internet? I remember Brzezinski wrote a book about 1970, Between Two Ages, and he's talking about computers talking to each other. And people are saying, what is that? You know, what, computers can't talk to each other, right? But you look at it now, it doesn't seem so amazing because we're so used to it, all right? We wake up every morning and look at our phone, and that's like Captain Kirk looking at something he didn't even have, right? I mean, our technology is now better than what they had in Star Trek, right? Those doors that open in Star Trek, we do that every day at Jabka, right? So,
well, what I also think about is not to, build too strong expectations. It's great to have an inspiration. It's great to have some kind of direction. But I would say if we build up some kind of expectation, a long list of to do, the space should be like this, that, etc., 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 then it will be like in a meme. Expectations versus reality. So I think it's great to be open, to have an open mind to what could come, to work with, play with the imagination, get some kind of inspiration, but be a bit out of strong expectations of how it should be, because it might be very difficult to face the reality after all.
I think, I'm sorry. The laws of physics are not eternal. Physics evolves, and the distance between imagination, expectation, and reality, it's in design is part of the process. You imagine, you conceive something, you draft something, you prototype, and you test it. So it's the process goes from imagining something to the reality. So it's part of the natural process. So it's good that we use our imagination to set new goals.
Just commenting on that, I had the chance to be a mentor in one of the art, design, and science projects that students representing various disciplines were working on prototypes of some solutions for very important questions, let's call it this way. And actually, I must say that the design students were actually the ones that really drove the whole process of the group working. So that's very important. Sometimes we talk about art and science, but I think we should talk about art, design, and science as a combined thing to work on the complicated things, right? So challenges. So that was just a comment. But Camille, you wanted to say something?
Yeah, about bending the laws of physics for science fiction. It depends what you write. If you want to write a space opera which spans between several systems, and you want to explore different societies, different social structures, how people how people reflect on their place in our space, how they interact with other species or with transhuman species, for example, because there is a trope called transhuman aliens, basically like in the Dan Simmons' Hyperion. Yes, you can do that, but you also need to keep in mind that something that our friend said, that there is the issue that science marches on, which is being, not a plague, but a feature of many hard science fiction, that they become outdated. For example, the Joe Haldeman's The Forever War. It used, it's a war story with time dilation, but they use collapsars, those collapsing stars, which were all the craze in the 70s, 1970s astronomy, and I don't even hear about them or read about them today, because, and it's an outdated concept, but anyway, it was hard science fiction back then, because there is something like, I love in the Hugo Gernsbackian school, or Olaf Stapledon's school of science fiction, which even Lem at some point followed, meaning that science fiction, Larry Niven also followed in his early years, that science fiction needs to be educational. Those stories may be very simple, but they point out, for example, those sci-fi stories in Młody Technik in Polish, those were written mostly by engineering students who wanted to create a story about an invention, like a modern Jules Verne or more modern H.G. Wells or Hugo Gernsback. So anyway, in these cases, yes, we can sometimes get to fall back on the story, but the purpose is to create an inspirational tale about a possible invention that can change the world, change how society works, or even perform certain actions. And it's like for many people, oh, no, I never thought about it. Oh, think about that.
And what about the influence of science fiction on technology? So we have sometimes some predictions that after some years we see that it's actually reality. And how do you feel how really that something was written, invented by someone, influenced the process of creating this thing?
I think the classic example of that is Kubrick and Arthur C. Clarke talking about satellites in the 1940s, and by the time they arrived in the 1960s, again, people just said, oh yeah, satellites. We always knew they could do that, right? But if you watch 2001 now, Space Odyssey from late 60s, a lot of that technology we have every day. So that movie is, people used to say it's a really boring, slow movie, and they only went because of pharmaceuticals of the time and so forth. But the idea was that the technology that amazed people in 1968, to my students, it looks completely boring. And I would say more than half of my students do not like 2001 Space Odyssey, but 45 years ago it was amazing. But now you can see, I think Kubrick's daughter is they're having a video call, and that was amazing in 1968 again, but now it's sort of boring. So sometimes research and development is boring, and it's not made for a movie, right? Long research to make something like the vacuum tube or a semiconductor or a jet airplane. You can't put it into a 2-hour movie. It's just long and boring, and we're all benefiting. I mean, you made a transatlantic flight this morning or yesterday, and Lindbergh, when he did it in 1928, it was like, I can't believe it, right? He took sandwiches with him and by himself. And so again, I think we are living in a science fiction world. I think we just don't appreciate it as much as we should.
So I can tell you several, I will tell you several things, but I will tell you one thing. You look at patent law, and several cases where, for example, in the case of Robert A. Heinlein's concepts of the nylon waterbed, there was a patent application for a nylon waterbed, which was rejected on the basis that the patent examiner actually saw a similar device being, not even descripted. It was disclosed in a way that you could even replicate the device in a sci-fi story. Similar things happened with the Donald Duck's maritime salvage device, which used air pressure and golf balls, no, not golf balls, tennis balls, to actually that would be ballooned, and they would lift from the depths of the ocean a shipwreck. So there were many instances where it happened, to the point where Hugo Gernsback, the one who, from who we get the Hugo Award, actually pointed out in the Galaxy, I recall, the issue from 1953 or 51, that during the American patent reform, they need to give a preliminary patent to sci-fi authors for their inventions, and they would get some kind of a reward or be awarded a partial patent if that device comes to being. But from a business perspective, for example, if you say, oh, I got this idea from a science fiction book, well, it's not a very good marketing, that's first of all. And second of all, that can actually jeopardize your patent application at some point. In Poland, you don't examine science fiction works, but in the US patent system, they are used to doing. Also, there was a Robert Forward book called "Indistinguishable from Magic," where Robert Forward actually wrote that he has an idea for for something for either solar sails or antimatter drives, but he will first apply for a patent for it because he doesn't want to end like Arthur C. Clarke. Because Arthur C. Clarke, till the end of his day, he deeply regretted that he published his work on the telecommunication relays in geostationary orbits as a popular science article and not as a patent application.
I think another thing is that reality is sort of boring. You know, young people, I was looking at the top 20 movies of the money makers for the last 10 years, and I could see one of them was just about a normal pedestrian family or something that when I grew up, all the Academy Awards were about a drama around a marriage or something falling apart. Now they're all about paranormal, Marvel, heroics. And I think it's a good and a bad thing. I think one of the things it shows you is we are curious as a species. And I think young people now, the Marvel universe and everything like that, I would have never imagined that as a kid, that it would be so popular. I mean, when I was a kid, Superman was a half-hour cartoon on Saturday, and maybe you'd watch it. But the levels of enthusiasm now for just this alternative sort of existence is I think it's good and bad. In some ways, it makes their own lives seem sort of boring, right? Because they say, why don't I live in the Marvel world? How come I have to wash these dishes or something, right? But I think it does show you that we as a species do crave for science fiction because it's fun and it's an adventure and it's something that you're never really bored with science fiction because you don't know what's going to happen. It's a make-believe world. So I think that's why people like it, even if it's not literally true. So I think it's just fun. I think science fiction is a fun genre, and it's also educational. I think you learn something in it.
Okay, so one thing I had to add to what Patrick said, we need to recall that during even my childhood, many people didn't have dishwashers and Roombas. But we had the Jetsons and Rosie. And today it's like we have a housekeeping robot. Oh yeah, we bought them at a convenience store.
So, yeah, unfortunately, we are really getting short of time. But I wanted to get back to the topic of inspiration. So there were like several events in the history of science, of space exploration, that really made working on the inspiration to many generations, like moon landing and all these things, right? All these things, I mean, let's say, namely moon landing. And what do you think, what would be the next step for us? Can you imagine any kind of like event or like a discovery that would be so strongly influential and inspirational on the people?
I think our way to the moon and to Mars colonies, when we get there, which apparently will be sooner than we think. It will be a really inspirational event, just like the first landing on the moon. That I also remember my parents calling me in the middle of the night. I was 9 years old already, a little bit older than you, but it's a mark.
I think with the current technologies, with the social media, streaming platforms, etc., pretty much everything could be, because, we're too much into marketing, into, new triggers, fast-moving, things. So I think that it could be very unexpected thing, but in general, I agree that getting back to the moon and human landing on Mars, this is something really huge. But again, thanks to the marketing, we cannot predict it, I would say.
I have to say, I love inspirational. I mean, that's what just these big, grand things get me excited. But I want to live in Patrick's universe. And Patrick's universe is, it's all around us, it's commonplace. I want to catch the shuttle to the moon and think of it as like I'm catching the flight home. So I don't really want the inspiration. I want the mundanity, because that will be when we've succeeded and it's a part of our lives and we're in a species expanding into the solar system. You want to go take your vacation on Mars? Let's sign up. We'll go next summer. We'll save up like we're saving up for a cruise. That's what I want. Common, everyday part of life. Make it happen.
Yeah, I think for me, when I look at, for example, the Artemis Accords, I mean, we now have 29 signatories on this. And if you hearken back to the US lunar landing, that was much more of a unilateral action by one particular government to get a person on the moon. And when we sort of expand Artemis out, we can sort of see much more of a multilateral coalition in terms of looking at the next steps. And I think there's so much in terms of space exploration that can be done jointly. That's where I see a lot of the real excitement in the future. And, you know, the idea of having a woman on the moon, a woman of color, for example, I think is incredibly exciting. But also just the bounds of how space exploration can also impact life here on Earth. So when we look at a lot of the climate change research that's done, NASA has the SEVER program that does all sorts of early warning systems and things like that. So seeing how we can use technology to sort of impact some of our sort of more terrestrial goals, I think is also really inspirational. And so the question comes down to collaboration and how we do that jointly in terms of all of those next steps.
I think one of the things that we haven't been emphasizing, at least in fiction in the last couple of years at least, is this idea of the first contact. And I think that's the one that really got everybody's imagination, just with the UFO craze in the 40s and into District 9 or whatever. And earlier you were mentioning the Voyager probes, and they're going out into space. And I was just a kid, but I remember the Viking landed on Mars. But I remember I read about that Carl Sagan had directions to Earth for anybody that would find this probe. And I, for one, was only in 4th grade, but I said, "Are we sure this is a good idea? Did anybody vote on this? Because we don't know who's going to intercept this space ball, you know." And but I think the first contact, I think that will be one of those moments that will change the arc of history for everybody. And they have fun with it in some of the old, The Day the Earth Stood Still or The Twilight Zone. It's a cookbook, right? The idea that it could be friendly people, or they could be like childhood ends, where it appears friendly, but it's not. And I think the first contact is one that still is in the back of our minds if it's going to happen.
And for me, it's also fun. Not maybe first contact, because although I would like to see Voyager coming home to its creator, but there is a issue. Well, for me, it's more like finding a different life forms which originated not on Earth, or for example, see how we are related to it, mostly microbial, or even something that we don't even consider as a life form, and we change the definition of a life form. But for me, the greatest inspiration is that many technologies that are being developed for example, lunar mining and lunar manufacturing and sustainable habitats will have the effect and will come back to people on Earth in order to create better technologies that don't use water, don't waste water, better habitats and shelters for people, and ways to, for example, not the drive away climate change, but to adapt to climate change. Because in many modern documents, there is an emphasis on adapting to climate change, not even fighting, but adapting to the change.
Oh, that seems like a very, very fruitful and great discussion. Unfortunately, we are really running out of time, but I promise that there will be a chance to ask questions to our guests. We can ask one question now to the audience, and then I will invite you all to meet our speakers outside in our meeting point. So do we have any question? Okay, so I will thank our speakers once again. So let's clap our hands. Thank you very much. And I just wanted to say for those who are here that the meeting forward with our guests and also the possibility to have a signed book by Les is outside, well, at the zero level here next to the registration point, so you can talk to our guests there. Thank you very much. And for the broadcast, we move to the Mars yard to see how Remco is going there. See you then.
We should go to Mars.
We should go to Mars.
We should go to Mars.
Because it's human nature to keep exploring.
Because we want to discover intelligent life in our solar system.
Because establishing a presence out there is a huge stepping stone to limitless possibilities.
Because we can.
Because our ambitions exceed this world.
Because humanity has unlimited curiosity and is destined to conquer the universe for good.
We should go to Mars because it's been long enough.
Because it helps to develop new technologies that are also very useful on Earth.
Because look at Mars could improve the way we look at our Earth.
Because Mars exploration is a huge milestone to extend our vision and discover a new home.
To play sports in low gravity.
And to define past, present and future of our planet.
It opens doors of opportunities for developing talents like us who wish to explore newer horizons and decipher the unimaginable.
We should go to Mars because the sky is no longer the limit.
Space industry is booming all over Europe. And so whether you're Luxembourg or Portugal or Spain or Italy, whether you're big or small, you try to be part of this.
I cannot imagine a better way of preparing people for our future projects than, competitions like this.
And all these jobs are there to be had. So if you're studying something that you think has nothing to do with space, check again. You might find out that 10 years from now, you're actually needed.
Great engineers and great scientists building great products. That is what the space industry consists of.
There's something deeply philosophical about space.
And we are the first generation where Mars is just about to be at the reach of our hands. It's a logical continuation of feeding and nourishing that nomadic gene that is within us as humans.
The most important and fundamental part of being human is imagination, this aspiration that we have, which drives us to explore space. So this is something to be proud of, this is something to celebrate.
The cooperation is obviously not just between governments, but it's between the private sector, academics, non-governmental organizations, even students that are combining math and science studies with imagination and creativity.
One person can make a difference and therefore shoot. That's my assignment to you.
We should go to Mars.
We should go to Mars.
Because it's human nature to keep exploring.
Because we want to discover intelligent life in our solar system.
Because establishing a presence out there is a huge stepping stone to limitless possibilities.
Because we can.
Because our ambitions exceed this world.
Because humanity has unlimited curiosity and is destined to conquer the universe for good.
We should go to Mars because it's been long enough.
Because it helps to develop new technologies that are also very useful on Earth.
Because look at Mars could improve the way we look at our Earth.
Because Mars exploration is a huge milestone to extend our vision and discover a new home.
To play sports in low gravity.
And to define past, present and future of our planet.
It opens doors of opportunities for developing talents like us who wish to explore newer horizons and decipher the unimaginable.
We should go to Mars because the sky is no longer the limit.
Space industry is booming all over Europe. And so whether you're Luxembourg or Portugal or Spain or Italy, whether you're big or small, you try to be part of this.
I cannot imagine a better way of preparing people for our future projects than, competitions like this.
And all these jobs are there to be had. So if you're studying something that you think has nothing to do with space, check again. You might find out that 10 years from now, you're actually needed.
Great engineers and great scientists building great products. That is what the space industry consists of.
There's something deeply philosophical about space.
And we are the first generation where Mars is just about to be at the reach of our hands. It's a logical continuation of feeding and nourishing that nomadic gene that is within us as humans.
The most important and fundamental part of being human is imagination, this aspiration that we have, which drives us to explore space. So this is something to be proud of, this is something to celebrate.
The cooperation is obviously not just between governments, but it's between the private sector, academics, non-governmental organizations, even students that are combining math and science studies with imagination and creativity.
One person can make a difference and therefore shoot. That's my assignment to you.
Good morning and welcome back to where everything is happening here at the European Rover Challenge 2023. Welcome back to Mars. Behind me, the Mars Yard, where the teams are continuing to compete. The 25 teams that Milena talked about earlier are continuing to compete right behind us here, and you will see some of the action while we talk to very special guests here outside on the Mars Yard. And in the next block of about half an hour, we have very special guests for you. And I'll start right away with one of our astronaut guests. So welcome very much Sławomir Żużnanski, the newly selected Polish ESA astronaut. You were selected from 22,000 plus people, and I hope most of them are watching now, to be one of the new ESA astronauts. So tell me a little bit about how that process was and how it feels now to be one of those very exclusively selected 22,000 people.
Oh, thanks, and thanks for having me here. It's a big privilege for me to actually interact with students and be back in my country in Poland, where since my selection I try to be quite often. The competition was hard, but I never really looked so much on the competition. I tried to do my best. The selection was quite long. It took a year, roughly a year and a half. But I knew when the selection was going to open, I knew I was going to apply, and I couldn't wait for this to happen. I was following the selection of 2008, so that this is the previous selection, and it took my selections 2022, so 14 years for the new one. And yeah, whenever ESA opened the selection, I was ready. I knew I was going to apply, and from one stage to another, I tried to do my best.
It's an amazing story. Now I know there's lots of people out there who might be jealous or who might have the same ambition as you. Do you have any tips on how to prepare for a career as astronaut?
So what I would say first, if you really want to do this, apply. This is the first step. The most important is to send documents. And the first stage was the most crucial one as well, because as you mentioned, there were over 22,000 applicants, but to the following stage, there were roughly 1,500 invited. So this is probably one of the most difficult stages to polish the documents and look for examples you want to showcase from your professional life that would match potentially the astronaut career and who you are. What is really important is to be, I think, open, honest, and showing your experience, who you are, what you like doing, and what you could eventually bring to the table if one day you could go to space.
Excellent. Now, many people out there think that the life of an astronaut is very glamorous. You sit on rockets all the time and do cool stuff. But in reality, that might be slightly different. I mean, we're here on a Saturday. You're talking to the media. How has being selected changed your life, and what are the maybe less glamorous sides of your selection?
I was always working long hours, so this is not new to me, to be honest. As an engineer, as a scientist, I did most of my career I spent at CERN, the European Organization for Nuclear Research, and we also work long hours. But since the selection, there is obviously a big new part of my life. So media attention, interviews, and participating to events. I always love doing this and interacting with young people and seeing the hardware and what the young people are interested in, what they build, how they solve problems. It's inspiring for me as well. And yeah, so this part I really love. Doing interviews, obviously, it's really important. The science outreach, we have to tell as astronauts, but not only, people working in the space sector, in general, in each sector, to show to the general public why it is important. Why do we invest in technology? Why do we invest in science and in education? And I feel very strongly about education and science because this is my background. But I truly believe this is, with today's technology, we cannot solve future problems and we need to move forward. And this is the young generation that actually is going to tackle these problems.
Excellent. So that's a good bridge to why we're here. I mean, we're standing on a Mars yard. We're standing on a place where this competition is happening. These are students, young professionals, the best of the best from Europe and the rest of the world. What would you say to them to help them in their careers as the future workforce in space? I mean, not everybody can become an astronaut, but we need so many more people in the space sector, like the people developing this technology here. What would be your tips for their careers?
Yeah, I think space is so multidisciplinary. It needs people with such a various background. Even being an astronaut, throughout the selection, I met people specializing in tectonics, geology, studying the origins of the universe or galaxies, astrophysicists, engineers and scientists as I am, medical doctors, pilots. This is really, really open. So if you want to become an astronaut, have a look, because maybe your experience is very relevant. And in the space sector in general, this is not only these career paths, but also business development, funding, fundraising, space law and international law, contracts. This, like all this, space also needs. So if you are really interested in space, probably independently of what you do professionally, you can find really interesting projects in your domain.
Yep. And I really like you saying that, because I always say there is a place in space for everyone. And a few of us can become astronauts, but behind every astronaut, there's thousands of people making this industry into the exciting world that it is. Now, let's look a little bit on the relevance of your selection for the Polish space sector. I mean, you're the second Polish astronaut, and the previous, your predecessor, if you like, grew up in a completely different era. That was a completely different time with different space programs, with different objectives. What is the relevance of your selection for the Polish space sector in general?
Our sector is quite new. I would say that at least our commercial sector started when we entered the European Space Agency as a member state. So it's been in 2012. It's been just 10, 11 years where we have really a commercial sector that is starting to go up. And starting to grow as a branch of industry. We had obviously previous scientific missions with many science institutes, but now there is this big shift towards the commercialization of space, mostly on low Earth orbit, so the closest to us. But this is such a democratized and commercial application nowadays. Sometimes without realizing, we use space technology on a daily basis. Every single time we open the Google Maps and we try to find where we go and what is the traffic, this goes through GPS, Galileo systems and navigation positioning, weather prediction. Today, obviously, modern industries like agriculture, logistics, supply chain, they rely on space and on space technology. So I think it's such a big boom of space technologies and the market that is very dynamically evolving. What is my relevance? I hope I can help to boost the Polish sector to grow. And we have an amazing talent in young generation, young people, engineers who want to build really technology, who want to build cutting edge, world-class technology in Poland. And I hope my selection can boost the interest in space. Also funding behind and this branch of industry where I hope from today, as we stand here, in 10 years' time, in 1 decade, we'll see this big shift and Poland will be one of the leaders of certain technology niches on the market that we have.
Okay, well, I really hope that you can play that role and that you can help the Polish society to claim that role in space. I would like to thank you very much for being with us here, Sławomir, and I wish you all the best in your training, which no doubt is going to be very intense, and I'm really looking forward to seeing what the near future for you will bring, and we'll be following it very closely. So thank you very much again for being here.
Yeah, thank you for having me here, and it's always a pleasure to talk about space to general public and to young people as we do today.
Excellent. Well, thank you very much. And let's talk a little bit more about the role of Poland in space with the ultimate expert in this area. So I would like to invite Professor Rochna, the president of the Polish Space Agency. Thank you very much for joining us, Professor Rochna.
Thank you for the invitation.
My pleasure. And welcome to Mars, I would say. Mars in Poland, as Milena said in the broadcast this morning, the biggest Mars yard in Europe, if not the world, is right here in Kielce today. Now, the theme today is the moon, is humanity going back to the moon, and Poland plays an important role in that. Let's talk a little bit about that, if that's okay with you.
Sure.
Because only a few months ago at Impact 23, you announced a very ambitious plan for a new Polish lunar expedition. Can you tell us a little bit about the ambition of Poland in lunar research?
Right, indeed. We are all following the story of Artemis missions run by NASA in cooperation with other countries. We would like to participate in this program, providing some apparatus, maybe in the future even an astronaut, why not? But we would like to contribute also with our own mission. About a year ago, we announced a call for ideas, what kind of mission it could be. And a number, if I remember, 25 proposals was received. Most of them dedicated indeed to moon exploration. And we have selected the most realistic and still quite ambitious one. We think of a lunar orbiter going around the moon and looking at the moon surface through infrared radiation. And this way searching for minerals which will be important to build and to support lunar bases. Because this is what Artemis program is about, not just to put another footstep, not to set another flag on the moon, just to build a permanent base on the moon, right? So we need some construction materials, but then we need oxygen, we need hydrogen, because we need some fuel, we need energy, and we need water for people to survive. And we are going to look for this kind of minerals with our lunar mission.
Excellent. Now, you mentioned the Artemis Accord, and you signed the Artemis Accords on behalf of the Polish Space Agency in October 2021, very early on in the process, and you expressed the desire there to develop Polish indigenous space technology in support of the Artemis Accords. And I'm assuming this new lunar expedition, this Sony probe in lunar orbit, is part of that?
Yes, indeed, it is. It is intended to be our contribution, but we hope also to provide some apparatus for the Artemis flights. In fact, already in Artemis 1, some Polish instruments were on board, sensors, radiation sensors designed by the Institute of Nuclear Physics from Krakow, from Polish Academy of Sciences, and sensors monitoring the air in the human cabin from Vigo System Company. But those are very, very small items for the beginning. We hope to get something more. Recently, NASA announced a call for instruments which astronauts will bring to the moon in Artemis 3 and Artemis 4 missions. Artemis 3 is too short time to develop something, but I hope that for Artemis 4 we will be ready with some proposal. But this is in a wider context. Apollo missions were claimed by US that this is for all mankind, right? Yeah. Now Artemis is rather with all mankind. US and NASA, they really want to make it an international affair. And therefore, the Artemis Accords declaration is a kind of a club of signatories of this declaration. We meet online every month. We discuss how other countries can participate. Our initiative was to create a working group dedicated to the participation of other countries, and together with Brazil, we chair this working group. We meet regularly every month online, but there was already one meeting in person in Gdańsk a couple of months ago with big participation, about 13 countries, big delegation from NASA, from Department of States. We got guests from Japan, from Brazil, from Canada, very good attendance. And the conclusions of those meetings will be presented in Baku in a couple of weeks during the International Astronautical Congress. I will be chairing one of the sessions of this meeting. So this is a framework so other countries, including Poland, can contribute to the Artemis program.
Excellent. Now we just met the new Polish ESA astronaut Sławomir Żużnanski. I've also heard that Poland is going to increase its contribution to ESA. So Poland is very ambitious in that regard. Can you let us know a little bit about the expected ambition of Poland in the next 5 to 10 years as part of the European space economy and the world space economy in that regard?
Well, indeed, this year we celebrate 550 years anniversary of Nicolaus Copernicus, and this is a very special year for Poland. Indeed, we have increased our contribution to ESA by an order of magnitude, few hundred million euro. So with this money, we hope to build, we plan to build a satellite for Earth observation, both optically and radars. We want to contribute to ESA programs, building complete missions, complete satellites, which is a really breakthrough. So far, we have provided different kind of apparatus, equipment, components for various missions, but now we can make a step forward and provide complete missions, complete satellites. After 10 years of Poland in European Space Agency, a number of companies emerged. 400 companies from Poland are registered in ESA database, and this number is growing. And we believe that thanks to the increase of the contribution, which will return to Poland in form of orders for Polish companies, Polish scientists to provide elements for Artemis, for ESA programs. With this money, our companies will grow, and the space sector will become an important branch of Polish economy. Therefore, I'm very glad that we have this event today, because many young people are coming here. They are motivated by this kind of events, and this kind of competition, building the rovers, building rockets, building different kind of apparatus for satellites is the best way for young people to prepare for them to have a career in space, not necessarily flying into space by themselves, but building apparatus which can fly to space much farther than astronauts could fly.
Absolutely. Well, thank you very much for mentioning that, and thank you very much for being here and representing Polsa at the European Rover Challenge. And thank you very much for your continued support of bringing this important international event to Poland. And I'm really happy to see that we do have many Polish teams participating, and over the last years very successfully so. So a good sign of the capabilities that exist here in Poland and that will continue to grow. So thank you very much for being with us, Professor Rochna. Always an honor. And I'd like to continue to talk about Artemis with a representative of the country that initiated the Artemis Accords. Welcome very much, Amelia van der Laan. Thank you for being here. You represent the US Embassy in Krakow, if I'm correct?
Yeah, the U.S. Consulate General in Krakow.
Excellent. Well, welcome to Mars in Poland. Who would have thought?
Absolutely. No, it's fantastic to be here. And we have so many incredible teams here. And when I think about the Artemis Accords, just how far we've come in space exploration, it's amazing to see all of these dynamic teams out there thinking about next steps ahead in terms of where we're going in science, technology, and space.
Absolutely. This is a prime example of that. Now let's look at these Artemis Accords, because you mentioned it in the previous panel. The Artemis Accords play a very important role in humanity going back to the moon as a jumping board for Mars. What is the relevance of these Artemis Accords for signatory countries like Poland?
Oh, absolutely. So, I mean, if we look at the Artemis Accords sort of established in 2020 writ large, at this point we have 29 signatory countries, with Germany actually signing as of yesterday. I think this sort of constitutes overall collaboration and commitment to space exploration. If we look at the treaty from 1967, in comparison to sort of where we were with the moon launch and everything we did with Apollo, this constitutes a step of global collaboration in terms of our commitments, in terms of not only emergency management and sort of space exploration writ large, but also it underscores collaboration with all of these governments on a whole host of scientific issues. And if we look at the Artemis program of NASA itself, the idea is, you know, we really would like to have a woman on the moon. We want a woman of color on the moon, but also what are we going to do with Mars? What are our next steps? And when I look at Vice President Kamala Harris's leadership in all of this, NASA Administrator Bill Nelson's role, as well as everything the State Department is doing, the reality is there's so much more that we can do together as global partners on science and technology, and that really the next and best in space is ahead.
Professor Rochna, in the interview before, he said it very nicely that during the Apollo missions, NASA went to the moon for all mankind.
Yes.
Now they're going to the moon with all mankind.
Absolutely. I think that sums it up in a brilliant, brilliant way. And I couldn't resonate those statements even more.
Yet in some respects, the Artemis Accords led by the US is sometimes still seen as the US allowing other countries, or bringing other countries with them. But how true is that? Is this the Americans taking other countries to the moon, or is this a truly international effort?
No, I think this is absolutely an international effort, and this is a complete collaboration. And that's where I think the importance of having so many collaborators and signatories, it really constitutes a next step in terms of where we are with science and technology. And so we really do welcome more partners, sort of, this is a big tent project. And I see it in terms of all of the people who are here today. When we think about space exploration, this isn't something that we unilaterally do as one single astronaut getting on the moon. These are team efforts. If we look at Cape Canaveral, there are hundreds of people who are behind any single step into space. If we look at what's happening with the James Webb Telescope, there are hundreds of thousands of people who are sort of involved in those projects. And so it absolutely is a global effort, and we need all of that creativity and vibrance to sort of take us along. And so I would say the U.S. is, though a strategic and lead partner in all of this, it's definitely an effort of many in general.
Okay, we have 29 signatories. Why
Yes.
don't we have 200? There's
Well,
200 countries in the world, more or less.
This is a process, right? And I think that's what comes back to diplomacy in general. So, I mean, when you look at the U.S. government writ large, we have consulates and embassies all around the world, and we do all sorts of things in space and technology writ large. And that's true with NASA or any of our scientific programs. And so the question comes down to what our individual relationships are with each country. And this is a joint effort. So, you know, in general, countries have to want to be signatories. But we're definitely taking an open approach. And when I look at all of the diplomatic work that I've personally done in my career, NASA has always been kind of at the forefront of a lot of our youth and educational exploration. When I was at U.S. Embassy in Cyprus, we brought NASA astronauts to Cyprus, and we worked with the Cypriot Space Agency. And so I sort of anticipate that at every stop along my career. And so more the merrier would sort of be my personal take on the entire thing.
Well, that's a great way to summarize it, I take it, because I don't think it's your personal view only, it's the view of all of us.
Absolutely.
Especially from a Polish point of view, where Poland is one of the very proud signatories of the Artemis Accord, so let's hope that many more will follow. I'd like to thank you very much for your contribution, for your continued support of this of this global scale event that really puts Poland in the spotlight of the world. So thank you again for your continued support.
Absolutely. Thank you so much, and have a wonderful day, and best of luck to all of our teams.
Absolutely, absolutely. They're on the Mars Yard as we speak, so I hope you can see them in the background. I would like to move on to a slightly different angle of going back to the moon. And Raphael, if you would like to join me, Raphael Rutgen, you're a venture capitalist and a big ambassador and promoter of space. Let's look at the commercial angle to everything that's happening here, not just going back to the moon, but specifically here. You wrote a book not so long ago, To Infinity, an introduction to the space economy. Why was this book needed?
Well, I always joke that, you know, if you and I, we go to a lot of space conferences, and I always joke we meet like the same 2,000 people more or less. And let's be clear, we both love these 2,000 people, I think, but we're not going to build what we hope to be a multi-trillion-dollar space economy based on those 2,000 people. We need to draw in ever more people who are currently not yet part of the space economy, and explain to them why they are needed in space, what they can do in space, and that they can actually really add value. Because there still is persistent perception, and I'm sure you're a great space communicator as well, so I'm sure you come across the same thing, that most people still believe you have to be a rocket scientist to join a space sector, and that is simply not true. We need anybody from pretty much any role I can think of, including really non-intuitive things like artists, for example, and lawyers and physicians and so forth, to come into the space sector. And that's why I wrote this introductory, non-technical book, and that's also why I'm doing some other things, like my podcast, which you may know, to explain space specifically to non-space people in a hopefully non-technical way.
Okay, so what is new? I mean, space has been around for 60, 70 years. What is new now that prevented this from happening 10, 20 years ago?
That's an excellent question. So I believe space right now is at an inflection point, and that's got all to do with the dramatic cost decreases we're experiencing, both in accessing space and then in operating in space. And so the easiest example I can give to people, even people who are not yet part of the space sector, they may occasionally watch the SpaceX launches, and they may have then watched one of the boosters, the first rocket stage, come back. Well, that is really significant because it means that rather than throwing away a piece of equipment, that first stage, which we may estimate costs maybe something like $30 million, you're reusing it. If you're reusing it, say, 10 times, and SpaceX has reused some of them many more times than 10 times, the cost for that mission is not 30 million for that first stage, it's now 3 million. And that's a dramatic effect. And that is just one example of a cost decrease. Everything else in space is getting cheaper as well. The cost of satellites, their components. Also, things are continuously getting smaller, which is a general technology trend. So actually, I always wanted to calculate the combined effect of all of that. And then friends at McKinsey actually did it about a year ago and wrote a report. And they compared the cost of a what we call a medium resolution Earth observation satellite about 10 years ago to now. And they estimated that the cost of the capability, because of all these cost decreases, decreased by a factor of 3,500 times. And that's insane. That's an insane cost decrease. And so everything that people thought was too expensive to do in space, every business model that people thought, no, this doesn't make sense, space is too expensive, it's only for governments, they have to recalculate this every single one of them, because increasingly, the cheaper we go, the more business models make sense to do in space.
Okay, now we see fantastic technology being developed here by students benefiting from that from the decrease in cost, the technology that they use at very low budgets. It's quite mind-boggling what we see here on the Mars Yard. What can these students do to maybe monetize some of their ideas? They gain great experience and knowledge here. What can they do for their own future, perhaps as entrepreneurs?
Yeah, of course they have to marry it with the commercial angle and see where there is a potential market demand. So planetary rovers are actually emerging as a viable business model. So there is actually a number of startup companies, one of which was actually on my latest podcast episode, which are developing, at the moment, mostly lunar rovers. And some of them are even getting, I mean, most of the contracts they get are still government contracts, but some of them are starting to get commercial contracts, so really from other companies who want to start experimenting with things on the moon. So very tangibly what we're seeing today, that is emerging as a business model. But it's just great to see the students like tackling deep tech, hard problems, because that will be transferable to other problems they can work on.
Excellent. So, I mean, these students are still in university right now. What is the process of becoming an entrepreneur, say, as a student? What steps do you follow? How do you start?
Well, every entrepreneur story is a little bit different. What I encourage the students to do, like, they don't have to be entrepreneurs right away. Maybe they work at a couple of companies, including startups first, see how it goes. There's also a lot of help, including educational help for entrepreneurs. I myself have a couple of online courses, which are basically meant to help fledgling space entrepreneurs. Yeah, so I encourage them to read books, take courses, maybe work at a couple of startup companies or big companies as well.
How does the education system, to your knowledge, support this development, if at all?
The new space economy.
Universities, how do universities adjust to this new reality?
Well, I'm encouraged to see that there is starting from a very low base, there is an increasing number of courses catering not only to the technical parts of space, because of course we've always had a lot of aero-astro courses, but also specifically to the sort of business entrepreneurship side. So I myself, I teach at EPFL, and shout out to the EPFL Rover team, which is here.
They're here, yes.
So I teach a space entrepreneurship course at EPFL, which also exists as an online course. And our other technical institute in Switzerland, ETH, has recently recruited Thomas Zurbuchen, previous associate director of NASA for science. And they will also start something like a new Space Masters, which will also include some business and commercial elements.
Okay, excellent. So opportunities abound for all these students to really think about, maybe add the word entrepreneur to their career options. So thank you very much, Rafael, for explaining that to us. And we're going to see a few commercials right now, and then we'll move into the exhibitor zone. So I'll be seeing you in a few minutes. So, welcome back to the Mars Yard, and we have, before we go to the exhibition zone, we have a very special guest team with us here. This is Team Ares from Japan, and even though they did not qualify for the actual competition, they are here anyway to make sure that they qualify next year. So this is the Ares robotics team, and perhaps you can introduce yourself, which university you represent, and how the Ares project works, please.
Hello, my name is Danishai from Japan. I'm a master second grade in Tohoku University, and this guy is also from Tohoku University, and these two folks are from Keio University. So in Japan, there's no Rover team, so we unite several university team members into one, and we tried to qualify this year, but unfortunately could not. But like we got the fund and lots of support from Japan that made us lead here.
That's amazing, because this is not necessarily the European Rover Challenge. This is an international Rover Challenge that happens to take place in Japan, and you guys really represent that international element of it. So tell us a little bit about your impressions so far. You're from Tohoku University. Tohoku University is a leading institute in robotics, in space robotics.
Exactly.
And so you are amongst the leaders in this field. What is your impression of the competition here so far?
So thank you. Basically, before we came to here, we absolutely had no image what kind of competition it is. We were able to only watch the competition through the YouTube videos they provide, and also only the regulation rule books is the information we got. But after we came here, we are honestly surprised with the rover qualities for all the teams actually created, and also this like difficult Mars yard. Like first impression is very difficult that we saw, but all the teams are actually managing to clear the missions, and that was amazing, absolutely.
That's really good to hear. Now tell us a little bit about your rover. How many people are in the Ares project team?
Yeah, thank you. So basically our project started last year on March. Before that, there were no existing rover team in Japan, actually. So this guy, and including me, only 3 people decided to participate in this rover challenge. It was so challenging to collect the people in Japan because nobody actually had the idea of rover challenge. But right now, because of lots of people help, we got 33 members, and we actually managed to create 5 rovers already. So we have version 5 right now, and we're trying to create the version 6 and try to prepare for next year.
Excellent. So Keita, perhaps you can tell us a little bit about the technology of the rover that you're using.
Yeah, you can answer the technologies of the rover. All right, I'll take the lead.
That's okay.
So basically, at the beginning, what we have tried is there are lots of Japanese private space companies like Gitai or iSpace. They actually create the real rovers go to space. Yes. We tried to copy that as much as possible, but it was very difficult. So we actually look at all the ERC and also the URC rover teams and what kind of rovers they are actually creating. We started to create the small rovers first, and it actually ran without any arm or science instruments. But right now, our rover has an arm, and we created small prototype of the science module, and it's getting over and over, and that's the technology we have right now. But still, we have learned a lot through this competition, and we have a special Japanese field for actually testing these expression rovers. We're planning to test our new rover in October.
Okay, so you have your own Mars yard, if you like. So now that you've been here, you can have a good look around and copy the competition field and make sure that your rover next year is the best here in the field. We've run out of time, but thank you very much for showing us the global interest that the European Rover Challenge, which again is a global rover contest that happens to be in Europe. So I would again encourage teams from all over the world. We have our Japanese friends here. We see teams from India, from Bangladesh, from Turkey, from many places in and outside of Europe participating here. So encourage you to follow the example of these gentlemen and make sure that you register for ERC 2024. So thank you very much, gentlemen.
Thank you.
We will move to commercial now, and then we'll see you in the exhibition zone.
We should go to Mars.
We should go to Mars.
Because it's human nature to keep exploring.
Because we want to discover intelligent life in our solar system.
Because establishing a presence out there is a huge stepping stone to limitless possibilities.
Because we can.
Because our ambitions exceed this world.
Because humanity has unlimited curiosity and is destined to conquer the universe for good.
We should go to Mars because it's been long enough.
Because it helps to develop new technologies that are also very useful on Earth.
Because look at Mars could improve the way we look at our Earth.
Because Mars exploration is a huge milestone to extend our vision and discover a new home.
To play sports in low gravity.
And to define past, present and future of our planet.
It opens doors of opportunities for developing talents like us who wish to explore newer horizons and decipher the unimaginable.
We should go to Mars because the sky is no longer the limit.
Space industry is booming all over Europe. And so whether you're Luxembourg or Portugal or Spain or Italy, whether you're big or small, you try to be part of this.
I cannot imagine a better way of preparing people for our future projects than, competitions like this.
And all these jobs are there to be had. So if you're studying something that you think has nothing to do with space, check again. You might find out that 10 years from now, you're actually needed.
Great engineers and great scientists building great products. That is what the space industry consists of.
There's something deeply philosophical about space.
And we are the first generation where Mars is just about to be at the reach of our hands. It's a logical continuation of feeding and nourishing that nomadic gene that is within us as humans.
The most important and fundamental part of being human is imagination, this aspiration that we have, which drives us to explore space. So this is something to be proud of, this is something to celebrate.
The cooperation is obviously not just between governments, but it's between the private sector, academics, non-governmental organizations, even students that are combining math and science studies with imagination and creativity.
One person can make a difference and therefore should. That's my assignment to you.
So, welcome back and welcome to what we call the Inspiration Zone. We have an amazing exhibit of all sorts of organizations here related to space and robotics. And I'm here right now at the booth of MATLAB. And I'm here with Marietje Menke. Marietje, you're the Education Customer Success Engineer of MATLAB. Now I have two questions. What does your job mean and what does MATLAB do?
All right, so first about me. So yeah, I'm an engineer and I'm taking care of educational customers, so students and teachers, and I show them how MATLAB works, what can they achieve with that, and then they become more aware of that product and they follow their own works on their own.
Okay, and now the second question, what is MATLAB? I just heard from several teams that they use MATLAB intensively. Now, for people who do not understand what MATLAB is, what is it?
Yeah, it's easier to say what it isn't. Yeah, but MATLAB comes from Matrix Laboratory. It's a software which computes matrices, which is very unique and very crucial feature. It has lots of add-ons called toolboxes. Every toolbox does something in many areas like biology, economy, chemistry, physics, computing, and so on. So it has very, very huge potential. That's why many teams use it. Also here.
So what would teams typically use it for?
Mainly for control, for embedded systems, for picture processing, for autonomy. So let's say robots. But if you want, for example, compute if your drone project is profitable, you can also use MATLAB. It's economy module.
Okay, now we're not just talking about MATLAB, but also Simulink. Can you tell us a little bit about that?
Yes. Okay. So I told about many add-ons called toolboxes. Yes, Simulink has its special name. It's a different environment. So you don't write code. You use blocks. Every block has different function. You combine them, and then you have model. For example, you can create that way virtual model, and check how it works. If it works in virtual state, then most probably it will also work live.
So we're talking about testing Rover software in simulated environments based on a mathematical model?
Yes, but only a tiny fraction of capabilities of MATLAB. Of MATLAB.
Okay, very well. Can you show us a little bit about the practical implications of it? We see something here. There's a screen, but there's also a robot working. What are we seeing here?
Here, maybe Konrad would explain better, but we have a robotic arm which is controlled with a pad. It has 5 degrees of freedom, and we created all the algorithms to make it work.
Now, how does this robot relate to MATLAB? What is the role of MATLAB in what we're seeing here?
Okay, so Konrad would explain it better, but we have plugins to operate the system. The code was also exported to C++, and we created an interface to control it, to check how it works.
Now, this software, many of the teams use the software. How is it available? Is this a commercial tool, or how should I see that?
There are different types of licenses. There are, let's say, home, academic, and commercial. Home you can use at home. It's very cheap because of that. And if you want to teach with that, or you want to learn, then you use academic license. The biggest are the campus-wide licenses. You have everything. If you are a student or a teacher, you can use it at home or at the university. And there are also commercial ones, which you can use to commercialize your product.
Okay, I see. Now, tell us a little bit about the software itself. How easy is it? Because if I look at this screen, this looks rather complicated. But how easy is it for students, engineering students, to use this software?
It's not that hard. Okay, here we have let's say advanced working machine, but you can start with a simple project. On MathWorks webpage there are lots of free online courses like Simulink on-ramp. So you start from a single 2 blocks and you combine them and you add another one, another one, another one, and then you end with a working machine. And it's only first course, there are plenty of them, so after many, many hours you can be very skillful.
Okay, now on another note, MATLAB has been a big supporter of the European Rover Challenge. Why is the European Rover Challenge interesting for an organization or company like MATLAB?
Yeah, we are from the beginning with ERC, and why we are here, because robots are one of the most popular users of MATLAB and Simulink, and also there are students. Students which also come to MathWorks and work and develop the products. And MATLAB was first made for, let's say, for engineers. Lots of engineers here, so MATLAB is a crucial tool here.
Okay, now you're demonstrating this live here in a booth. How can you make mathematical software interesting for the general public that is here? How do you attract people here? Of course, with the robot, but what tricks do you use to explain math, to make math cool to the general public?
Yeah, at first don't show math, because then you're lost. Stephen Hawking wrote in his book that every formula in a book decreases the sale of the book by half. So. Yeah, you have a robot, you can control it, and then you attract someone. If somebody gets interested, then from step by step it checks what's behind, and behind those controllers here there are of course numbers, but at the end you show the code, and then it works.
Right, so you start with the practical application and then you work towards, okay, now this is the math that is behind this. So, well, thank you very much, Marici, for introducing us to the world of MATLAB and the role that MATLAB plays for the teams and the role that MATLAB plays here in the European Rover Challenge. So thank you very much, and we're really looking forward to seeing you again in the competition over the next years.
Okay, thank you. See you again.
Thank you very much. We are moving on now to the next exhibitor, and we follow the lead and we walk across the terrain here to find our next exhibitor. And as you can see, this is a pretty big event here. Now the nice thing is we have a very nice day today. Lots of sunshine, lots of people. So let's explore here a little bit. We see lots of children with the rovers. We have cool t-shirts, we have cool experimental vehicles, and we have people from the moon here.
Yes, it was a long way, but we made it.
Yes, exactly. So, let me make sure I have the right people here. I have Lasse Hansen here.
Correct, yes.
From Rostock, yes. And we have Frank Koch here. Correct. All from Rostock in Germany. Now, correctly. Tell us a little bit about the reason that you're here and what is it that you're showing us.
So first of all, we are space enthusiasts. So that's, I would say, is the main reason. And we are part of the Spaceport Rostock, which is a company in northern Germany. And we operate Europe's largest moon-like testbed. So what we did is we took this, regolith simulant, which is 99% physically close to the real moon dust. And we bought 40 tons of it and distributed it in a 5x 17-meter testbed. So the main idea is, and we are a space company which also develop roving systems and other lunar exploration systems. So the main idea is to have a place where you can test these systems under moon-like conditions. So as you can maybe see in this little setup we built, the regolith has really distinctive behavior. So it's very powdery, very dusty. It's comparably sharp. So it's nothing you can really recreate easily on the Earth. So this is all behavior which then is interesting to see how your system behaves in it. For example, ceilings get damaged by the sharp dust. You get stuck with the roving system because the powder doesn't allow or give good traction. So this is all stuff we allow companies to test at our place.
Okay, because that's what your business really is. You operate a very small piece of the moon in Germany.
Correct.
For companies to test their equipment, and we see an example of a rover wheel here,
Yes.
but you test whole systems. What are companies using this facility for?
So, for example, we have one company we partnered up with, is also having a booth here. It's called Neurospace. So they develop small roving systems for a swarm-like robotic operation on the moon surface. And yeah, these are, for example, typical customers which come to our place and want to see how their rovers operate in these conditions, which maneuvers they can do, stuff like that, to really stretch their system to have it ready for the moon.
Yes.
And actually, it's the largest European lunar surface, so it's not so small.
I understand that. Can you repeat again, how large is it?
So it's 18 by 5 meters, so we have 40 tons of regolith simulant. And people can really drive as multiple rovers at the same time. So you can even simulate a traffic jam on the moon, if you like.
That's amazing. Now, what I'm wondering, is there a market for this? Is the industry of lunar rovers developed such that there is an actual commercial market for this?
Actually, yes. So it's starting, right? So we are a commercial company, so we are a service provider offering that facility to anybody. So research institutes are really interested in. But also industry is coming, right? So with the CLIPS program from the US, more and more smaller companies, startups developing these rovers. Because if you have astronauts on the moon, you have the need for transportation on the moon, right? You have to bring the cargo supply from their lander to the moon station. You might want to move astronauts themselves on the moon. So for all these various aspects of traffic, you have various transport vehicles, like on Earth, and all of them needs to be tested up front. And that's what Spaceport Rostock is for.
That's an amazing story, but why can't developers of rovers and lunar equipment build it themselves? I mean, many companies have a floor space that size. What's your added value?
So our added value is that we know how to handle this dust, right? And that is very aggressive. So first, there are not many people who have 40 tons of that material, right? Normally, the average market price is around 40-50 euros per kilogram, so you can do the math. And then handling it is very complex because it's very, very fluffy. You have seen it in the glass, right? Or you can just show it for the camera. So it is very fine powder, and to handle this, it makes sense to build one location that everybody can use, because you only use it for a few days, a month, or a year, and then for the rest, others can use it.
Right, now this material is potentially hazardous as well, isn't it? It's very abrasive. How do you, if it's dusty, how can you operate in the environment?
So actually, if you find a second market for your corona masks, right, you put it in front of your face and then it's okay. So you can eat it, right? Actually, chicken are eating this quite a lot to make stronger eggs. You shouldn't breathe it. That is the main difference. So when you protect your lungs, you're good. But still, you get a long introduction from us how to behave in that environment. And you should follow our rules very, very closely. And if not, you're kindly moved out of it.
That makes sense. Now, we talk a lot about robotic exploration here. How about human exploration? We're going back to the moon. The theme of today is the Artemis missions, yes. Which has the purpose to put humans back onto the moon very soon. Have you been involved in human missions at all?
Well, for humans, we have the large ESA facility in Cologne, right? The main difference is we are operating already. Sorry for this, Jürgen. And therefore, we can do first tests in our environment, but it's mainly for vehicles. For humans, it's different. You would create an airlock so you can test transporting the dust in and out of your facility. So we're really focusing on the surface mainly. So yes, everybody loves to leave their footprints in our environment, right? Everybody wants to have his footprint on the
Great pictures, I presume?
Absolutely. That's the picture number one from our environment, right? You step in and then you make a picture. But actually, we do these dust tests with humans, right? How many dust sticks on your clothes? Especially the shoes. How do you do the cleaning? So I'm now an expert in cleaning of that dust from all the sidewalls and so on. And this is something which the ground station will actually have to do as well. So yes.
Okay, that's amazing. Now I can imagine that this facility is not open to the public. but where can people find information about Spaceport Rostock?
Well, actually, it is open for public, right? So we installed it in the airport of Rostock-Lage. So on the left side, you do the check-in, and you can see on the right side our environment. So
through a glass window, I presume.
Through a glass window, and you can go there and just watch the experience going on.
That's amazing.
So we love this idea of public science. Yes. That's why we installed it directly in the airport terminal. So everybody is more than invited. Testing4.space is our URL. And you're more than welcome to also watch our small exhibition there with rockets and more information about the moon.
Absolutely. So people now have a reason to fly through Rostock on their way to destinations in northern Germany.
Yeah.
Even flying to Berlin, many people may go there, take a little detour, and then hop on the train to Berlin afterwards.
It would be our pleasure to welcome you there.
Absolutely. Well, I can't wait to see the facility with my own eyes. So thank you very much for introducing us. We are now going to see a few commercials during the lunch break, and we will be back with you at around 2 o'clock Central European Time here from the European Rover Challenge 2023 in Kielce. In the meantime, check out your favorite social media channels, #ERC2023. I'll be seeing you again after lunch. Thank you, bye.
We should go to Mars.
We should go to Mars.
Because it's human nature to keep exploring.
Because we want to discover intelligent life in our solar system.
Because establishing a presence out there is a huge stepping stone to limitless possibilities.
Because we can.
Because our ambitions exceed this world.
Because humanity has unlimited curiosity and is destined to conquer the universe for good.
We should go to Mars because it's been long enough.
Because it has to develop new technologies that are also very useful on Earth.
Because look at Mars could improve the way we look at our Earth.
Because Mars exploration is a huge milestone to extend our vision and discover a new home.
To play sports in low gravity.
And to define past, present and future of our planet.
It opens doors of opportunities for developing talents like us who wish to explore newer horizons and decipher the unimaginable.
We should go to Mars because the sky is no longer the limit.
Space industry is booming all over Europe. And so whether you're Luxembourg or Portugal or Spain or Italy, you know, whether you're big or small, you try to be part of this.
I cannot imagine a better way of preparing people for our future projects than, competitions like this.
And all these jobs are there to be had. So if you're studying something that you think has nothing to do with space, check again. You might find out that 10 years from now, you're actually needed.
Great engineers and great scientists building great products. That is what the space industry consists of.
There's something deeply philosophical about space.
And we are the first generation where Mars is just about to be at the reach of our hands. It's a logical continuation of feeding and nourishing that nomadic gene that is within us as humans.
The most important and fundamental part of being human is imagination, this aspiration that we have, which drives us to explore space. So this is something to be proud of, this is something to celebrate.
The cooperation is obviously not just between governments, but it's between the private sector, academics, non-governmental organizations, even students that are combining math and science studies with imagination and creativity.
One person can make a difference and therefore shoot. That's my assignment to you.
We are Sapienza Technology Team from Sapienza University of Rome. After gaining valuable experience last year, we decided to participate for the second time in the European Rover Challenge with a completely new rover, designed and built from scratch, CC8.
The challenge we set for ourselves was to get over of the limitation of its predecessor, both in terms of navigation and robotic arm capabilities, while introducing new features such as drilling and drone integration. This provides us with an opportunity to refine our skills, test innovative technologies,
and acquire new expertise. The team for the on-site formula is composed of 40 members, divided into 7 divisions.
In addition to the leadership, there's the management division that takes care of logistics by organizing contacts with companies that can support the project by processing, for example. Moreover, it cares about promoting the project inside the university and beyond it.
The goal was to create a rover with lightweight and sturdy material and a good maneuverability. The structure division was responsible for constructing the rover chassis, suspension system and drill, while a dedicated division developed the 6 degrees of freedom robotic arm.
The electronic division acts as a bridge between the software and the hardware ones. Its member designed the boards that host the components related in safety circuit and the control of the motors. It also helps in selecting hardware and sensors.
The software division develops the software for the autonomous navigation of the rover using computer vision and artificial intelligence algorithms. The division also develops the software for the control of the robotic arm and for the generation of its optimal trajectories.
The chosen land site is the area northwest of Tyndall crater, because of its strategic position and safety. This zone contains information on the presence of hydrated materials accessible via drilling and drone scouting. The objective is to verify our hypothesis by analyzing regolith composition inside and outside the nearest accessible crater. To ensure a smooth navigation on the Mars yard, the reliable rocker bogie system was once again chosen. This time with the differential bar placed beneath the chassis to provide a broader space for the robotic arm's workspace and other scientific instruments as well. Additionally, by introducing steering wheels, we can increase maneuverability, allowing the rover to steer while moving forward and pivot in place without slipping. A signaling light on top of the rover indicates the status of operations using different colors and flashing patterns to indicate whether autonomous or manual operations are being performed. Additionally, it allows for signaling anomalous states visually. The main emergency button is located at the rear end of the rover. This easily accessible position enables the complete isolation of batteries from the rest of the electronics, instantly stopping the rover when pressed. The autonomous navigation system employs a stereo camera as the main sensor with which the different algorithms running on the onboard computer generate a 2D map used to navigate. The system is also able to detect tags on landmarks in the environment to improve the localization accuracy. The mapping trajectory planning, and localization modules have been tuned and improved during the course of the year, using the experience of the previous competition and tests in an analogous environment. The design robotic arm features a compact structure that enables access to the terrain for the collection of surface samples. A custom end effector equipped with replaceable phalanges also provides a firm grip for performing the maintenance task operations. These operations can also be performed autonomously using predefined trajectories as well as through tag recognition.
Hi, my name is Philip.
What's up? Bartek.
Shiv.
Amelia.
Alex. Mario.
Jamie.
Matthew.
And we are the Imperial Planetary Robotics Lab, or IPRL for short. We are a new team formed at Imperial College London, and we are part of the Imperial College Space Society. This year we are competing in the European Rover Challenge as our first goal and first milestone. And in this video we'd like to present to you our rover, the Harbinger. We are a UK team, but few of us had to already leave the UK for the holidays. That's why Harbinger is being finalized in a few places at once. So in this video we will take a slightly different approach and actually take you for a tour all around the globe to see how our work is progressing. Our first stop is our headquarters in London.
Welcome to EEE 505, the Robotics Lab, where student imagination and chaos come together. This is where the Harbinger, like many other robots, was born.
We created IPRL to support students looking for opportunities in planetary robotics and science by building test projects for them to test their skills on. The ERC is a difficult competition for us to enter. However, it gives us the experience and credibility for us to continue moving our planetary robotics project forward.
We keep our team as small as possible to minimize communication issues and maximize our efficiency. Therefore, we also keep a flat team structure, and the project was broken down to clearly divisible responsibilities so that each sub-team lead is clear about what they and the others are doing, allowing them to also specialize in their field. Now, off to Bartek to tell you more about the electronics which drive Harbinger.
The energy subsystem is broken down into two parts. The first one is the one that powers the robotic arm, and the second one is the one that delivers electricity to the main motors and all the necessary sensors. Each subsystem has a relay which is controlled by the Arduino Mega board, so that we can actually control the power remotely. Naturally, we also monitor the power consumption of each of the electronic subsystems, and apart from that, each subsystem has an array of fuses which stop an excessive current from flowing into the sensitive devices. There is also a physical safety button installed on the rover, which cuts the power delivery completely in case of any failure.
Hello again, let me tell you about how the remote control works.
First, let me tell you the main component of the Harbinger to be controlled. These are the arm, which will play the main role in the maintenance task, and the cheese wheel for the movement. If we take a look inside the rover, we can see the two comm systems set up for the remote control. The secondary comm system is composed of the 2.4 GHz nRF24L1 module connected to the Arduino Mega. This can perform basic transmission but has low bandwidth. The primary is composed of the Raspberry Pi connected to a 5 GHz router outside of the rover. This has high bandwidth and can provide images or video if necessary. The Mega is connected to the motor drivers and the arm to control the components. The status of the components and the rover can be shown by the ground control station. The station will be a laptop with a front end made by React, which will contain the video feed, velocity, orientation, along with other information. Analogous info screens will also be shown for the status of the arm.
Harbinger has a double rocker mechanism suspension based on 4 wheels, which providing a rigid contact attachment point on all 4 wheels. This design was chosen as it compromised well between complexity and reliability. To actuate the rocker, a differential bar was created in contrast to a gear differential to minimize backlash and increase system stiffness. Apart from suspension, each wheel can rotate individually, allowing rover differential steering. With the combination of motors and gearboxes, the rover speed on ground is limited to 0.45 ms/s maximum with its own weight. On top of this, the wheel possesses symmetric tread patterns that offer greater directional stability. Sending you back to UK.
Harbinger features a 4 degree of freedom manipulator to address the science and maintenance tasks.
The manipulator is powered with a number of NEMA 17 and NEMA 23 stepper motors with built-in planetary gearboxes to increase accuracy and torque. The arm is made mainly of laser-cut folded aluminium with steel shafts and 3D printed transmission elements to minimize mass and cost. The transmission is performed by pulleys and tying belts to further increase the torque if needed and to allow for the motors to be positioned at the beginning of links rather than near the joint. This reduces the unloaded torque that the arm has to overcome.
To control the arm, we implement a number of preset positions corresponding to task requirements, such as a stowed position, interaction position, or gathering position. These allow for ease of operation and reduction of time when performing tasks. To do this, we rely on closed-loop control at a motor level and inverse kinematics at a manipulator level. From there, we rely on visual feedback from a camera positioned on the gripper to ensure the task is carried out accurately.
Two identical containers are attached in front of the rover. The load cell with the amplifier with high precision measures the collected sample's weight up to 600 grams by finding difference in mass.
The rover uses a 360 camera to continuously scan the environment for Rover codes. We use the OpenCV library to detect the codes, then refer to a dictionary of known positions and orientations to estimate our own position. Each code can point in 4 possible directions, and multiple codes can be detected simultaneously. We reconcile the different measurements by probabilistically weighing the different positions and choosing the highest weighted one. This gives us an estimate of both the position and orientation of the rover.
The science task requires a suitable landing site that is scientifically interesting and technically feasible. We chose an area near Flickr Moontes, which offer intriguing insights into the planet's mineralogy and presence of water ice. Various geological studies and analysis have provided evidence of volcanic activity, water ice deposits, and tectonic processes in the region, which we hope to explore more.
Greetings from Istanbul Technical University. I'm Emir, the team lead of the ITU Rover team. Please welcome our 8th generation rover, ITU AXA Rover. ITU Rover team is a project team established in 2016 that works in space robotics specialized in rover science. For 8 years, the team keeps working in a multidisciplinary atmosphere that consists of every faculty of our university: engineering, science, management and architecture. There are currently 60 total team members from 6 sub-teams. While the mechanical sub-teams designs the mechanical parts and manufactures them, the electronic sub-team's responsibility is to develop embedded softwares and printed circuit board design. The software sub-teams create algorithms and software architecture to perform tasks, then integrates into the hardware of the rover. Science sub-team's responsibility is to carry out the geological study of Mars. These technical sub-teams coordinate by the technical team lead. The management side is separated to 2 parts, which are the organization sub-team responsible for financial activities and the creative design sub-team that shapes the brand image of the ITU Rover team and creates innovative designs. ITU Rover team is a pioneer in spreading rover science to our whole country. With the European Rover Challenge, we aim to have an important position worldwide to inspire the world, as we do in our country. In order to achieve our this goal, the ERC is a chance to expand our vision and make us better than we were yesterday. Participating in the European Rover Challenge is a huge opportunity to improve ourselves about space robotics while gaining inspiration for new ideas.
In this year's rover, we utilize a 4-wheel rocker suspension with a differential bar to make sure all 4 wheels stay in contact with the ground at all times. This mechanism allows the rover to climb high slopes and increases terrain performance. High-torque brushless DC motors are placed in the aluminum hubs of each wheel to protect them from outer effects, such as the rough terrain, dust, and possible impact. Custom-designed 3D printed TPU tires provide high traction and damping, and the ABS rims strengthen the wheels. Our rover's chassis is made from perforated aluminum profiles for versatility and easy assembly. With this design, we are able to organize the rover according to the mission requirements.
The rover operates using a 42-voltage lithium-ion battery as its power source. Through the use of the power distribution board, we step down the battery voltage to 24, 19.5, 12 and 5 voltage respectively. The rover's power switch is utilized to completely disable the vehicle's power supply. We employ specially designed custom PCB to manage the indicator system of the rover, which then transmit data to the onboard computer. We implement BLDC motor drivers for controlling the brushless motors within the rover's driving system, while in-vehicle communication is facilitated using a KNFT and VR protocol. Communication between the ground station and the rover is established using the 2.4 GHz and 5 GHz Wi-Fi modules.
Our driving system includes path planning, avoiding obstacles, and generating course maps for autonomous navigation. 3D course maps is generated with our SLAM algorithm using LiDAR, and then this map is utilized for path planning. In order to successfully complete the navigation mission, a behavior tree is constructed. After determining initial values of the tag coordinates, rover autonomously goes to goals by detecting AR tags across the environment by the help of the cameras. Also, our rover can be driven with a keyboard from our navigation interface, which is accessible from a web browser.
We have built a new 6 degrees of freedom robotic arm powered by brushless DC motors with cycle-wheel gearboxes and belt-driven systems to achieve required torque and reduce backlash. Belt drives helped us position our motors for better weight balance. To reduce weight, a smaller cycle-wheel reducer has been developed, and carbon fiber tubes has been utilized, which also increased durability. Thanks to our manipulator's versatile design, it can easily change the configuration suitable for different tasks.
In this year's robotic arm, we use a SEM32-based BLDC motor drivers, which uses TFT protocol to communicate. Also, we use holographic magnetic encoders with 14-bit resolution, which provides us the precise control of the robotic arm. Electromagnets are added to the gripper's fingers to have a better grip on the electromagnetic lock in the maintenance phase. A plug is placed on the backside of the gripper to measure the voltage. Furthermore, a custom PCB, which uses TFT and ground communication protocols, is designed to control the multiple features of the gripper to accomplish the goals of the maintenance phase.
Our new robotic arm is designed to excel in high versatility, and it is able to perform even more complicated tasks. Robotic arm can efficiently perform in joint space and Cartesian space by advanced inverse kinematic algorithms. This year, we've highlighted its autonomous features with a behavior tree and performed several tests in both simulation and real life. Also, by addition of several USB cameras, a better observation environment for operators is provided.
Our deep sample collection system utilizes a drill that penetrates through the soil. Around the drill, we have installed a transparent tube to help us observe the collection in real time. To gather samples, our rover includes a versatile end effector, which can collect rocks over 15 centimeters wide. The samples are stored in a container on the rover's top deck. Our system uses brushed motor drivers for collection. We rely on the CAN protocol for communication between the motor drivers. To determine the weight of the samples, we use a load cell sensor. Through our user interface, we can easily view and analyze the weight of the samples and measure their sizes.
Our drone uses powerful brushless motors for enhanced performance and equipped with 1045 carbon propellers. Its durable construction includes a glass fiber mainframe and polyamide nylon arms. The Pixhawk avionics system ensures precise and reliable control. The integrated GPS offers accurate positioning and navigation capabilities. A single 4 ampere per hour 3S lithium polymer battery used to power the system throughout power distribution board. Image transmission and remote control ensured by 2.4 GHz Wi-Fi and radio controller. Additionally, 433 MHz telemetry module used to get telemetry data. With the help of an onboard Raspberry Pi and USB camera, autonomous takeoff and landing on rover owing to image processing is achieved.
As a science team, we search literature of the region to get to know Arcadia Planitia better. We are currently studying various landforms associated with ice, such as domes, craters, and flows. Considering the landforms that color in our studies, we selected a few landing sites. After all, we determined the final landing ellipse by checking the selected landing sites for their suitability for landing.
In this landing site, we decided on the most important ones among several important geological regions that attracted our attention and determined 3 survey areas. Depending on the suitability of the terrain conditions for the rover's movement, we determined a route to investigate these survey areas. By following this route, we searched for answers to some questions we wondered about the area in all 3 survey areas that rover will reach.
Greetings from Team Shunya, from IIT Kanchipuram in collaboration with MCC Chennai. I am Manas Narayan, currently the lead of Team Shunya. We are presenting you the second generation of Rover Versa. We are a students club named Mars Rover Students. This club comprises of BTech students who are doing their majors in computer science, electronics and mechanical engineering. We are currently focusing on building autonomous UGVs and robotic arms. Our problem statement revolves around the exploration of inhabitable zones. Our goal is to build a system that can withstand any possible terrain. Currently, to reach our goals, we Team Shunya are participating in different rover challenges all around the world. The team comprises of 5 teams: software team, electronics, mechanical, science and marketing team. These 5 teams ensure to manage the different aspects of our club, from our technical systems to our outreach events.
Master Platinum, who manifest and develop UGVs and robotic prototypes for industry-ready autonomous systems. We focus on integrating various subsystems that are industry-ready robot systems. As we know, innovation happens when there is a thirst for improvement, and ERC provides such a perfect platform for teams all over the world to participate in. Our designs satisfy all the primary requirements that are integral for the ERC 2023 competition. In this way, we propel innovation in all systems of system design.
The primary task of the science team is to select the landing location for our mission. And for this, the science team utilized the powerful tool JMAS. JMAS grants us quick access to a vast collection of maps, millions of images, and vector data sets gathered from planetary missions. During the competition, our specialized science capsule deeper will collect rock and soil samples. These samples are essential for the science team to formulate hypotheses from specific region on Mars, which will be mentioned in our science report during the final competition. To determine the most suitable path for the rover, our science team conduct a thorough analysis of the terrain. We prioritize path with slope below 45 degrees and avoid area with an abundance of rocks and craters.
जब मैं बोलूँगा तो आप स्टार्ट करो.
The rover's mobility rests on a 6-week rocket-based suspension system supported by a differential bar. This allows a consistent ground contact while fostering safely.
The suspension design optimizes wheel mounting as a fully supported beam configuration instead of cantilever beam. This design aims to reduce drive motor loads, enhancing motor and operational safety. The inner wheel hubs are designed using generative design and manufactured using PETG, contributing to stiffness and strength, while flexible TPU tires on the outside.
हो जाएगा, टेंशन मत ले यार. चल तू.
Greetings, this is Cycle for the mechanical deal of the For precise maintenance and adept manipulation, we have devised a 6-gear manipulator. The link lengths and the gear of the manipulator have been calculated after taking into account the storage area.
The first link employs a linear actuator for precise arm movement, while later links use high-torque RMCS Rhino encoder motors with timing pulleys that distribute weight for reduced torque needs. The linear actuator's precise positioning is calculated for optimal operation and maximum workspace. A camera scans Arco markers aiding scene reconstruction. Control interface with a base station GUI for operator input.
Hey there, we are the electronics team of Team Shumia. We focus on building a control system for navigation, maintenance and science tasks, power distribution system and a communication system.
Custom-made PCBs have been designed and manufactured by us to ensure equitable power distribution and efficient wire management. In addition, for each individual subtask like navigation, maintenance and science cache, task-specific PCBs have been designed. PID mechanism has been integrated with all 6 mobility motors to ensure seamless movement over rugged terrain during the navigation task. The rover's power system utilizes a combination of 24-volt source and 2 12-volt sources in parallel. This configuration ensures that even if one of the 12-volt batteries fail, the rover's functionality remains unaffected. Furthermore, in the event of a 24-volt power failure, the 2 12-volt batteries will automatically switch to a series configuration, guaranteeing continuous power supply to the mobility systems.
Limiting switches are essential safety devices present at each link of the manipulator to restrict the motor's movement within its minimum and maximum positions. They ensure safe operation and aid in homing the manipulator accurately.
In case the rover starts to malfunction, an easily available onboard kill switch is present, which ensures a power cutoff for the entire rover. In case the main communication system fails, the backup communication, which is LoRa here, will come in place and give necessary telemetry operations such that the rover can reach to the base station safely.
Our software team majorly works on developing 2 different software stacks, the autonomous navigation software stack and the autonomous manipulation.
With an autonomous manipulation
Now we will look into
that
the
seamlessly integrates real-time object detection and decision making. This innovative system acquires continuous video from a camera utilizing advanced segmentation and YOLO object detection algorithms. It then aligns pixel coordinates and the camera's coordinate system, enabling precise object positioning. The decision-making process shapes destination poses or positions that the motion planner employs by considering the environmental obstacle model and intended destination. The real-time object detection algorithm defines probing trajectories in autonomous mode, complemented by established paths for added resilience in the face of potential idleness. In terms of safety, the system employs detected obstacles and the AR tags to introduce collision objects into the virtual environment, effectively preventing collisions during motion planning. This proactive measure guarantees operational stability. The system's expertise extends to the strategic arrangement of objectives and manipulator positioning. These decisions are made with a forward-looking perspective, accommodating forthcoming actions by the manipulator. Precision and responsiveness also characterize specific actions like pressing buttons and manipulating probes. These actions are calibrated in real time using live video feed and IMU data. In the event of action failure, recovery mechanisms kick in, underlining the system's adaptability. To ensure progress and quality, the completion of every task is systematically verified.
The system capitalizes multiple state estimation nodes, each contributing automated data from different frames. This orchestrated approach minimizes frame shifting and error accumulation. Leveraging this precise localization, we execute behaviors tailored for the diverse tasks. Using NAV, a potent global and local planner, we traverse dynamically generated obstacle cost maps. For the seamless execution of our navigation plans, we rely on the move-based action and simple action client libraries. Further, to fine-tune the precision of our localization, we meticulously calibrate the covariance matrices of our state estimation nodes. These adjustments are done considering the unique inputs from our IMU data from Z to I. Our system also re-evaluates its localization when detecting and scanning air tags. This recalibration process ensures our autonomy remains unwavering and accurate. Our system is not solely about planned behaviors, it's about real-time decision-making and responsive recovery mechanisms. This dynamic approach safeguards control and stability throughout our autonomous operations.
Hi there, we are EPFL Explore, a student association and make project from the Swiss Federal Institute of Technology, EPFL. This year, we are proud to present to you our latest planetary rover, which we will present to the European Rover Challenge 2023, Project Kirby. Our objective at Explore is to combine space robotics with project-based learning. In this endeavor, we have developed a vehicle capable of autonomous navigation, conducting diverse scientific experiments on terrain soil samples, performing precise object manipulation using a robotic arm, and designing a drone to help us in our scientific mission. This project is made possible thanks to our wonderful team consisting of 48 students from diverse backgrounds, each contributing to a specific aspect of the project. In terms of organizational structure, the managing team consists of the president, project manager, CFO, and 5 systems engineers who oversee the mechanical, software, and electrical aspects of the project from a high level. The technical team further divides into 7 subsystems: control station, science, electronics, navigation, handling device, structure, and drone. Since the creation of Explore, we have consistently participated at the ERC. In 2021, we achieved 3rd place and best prize in science and probing and collection tasks. The following year, we secured the 2nd place and best prize in navigation. Our journey to Kielce has always been filled with excitement as we met like-minded individuals and strive to achieve excellence. This year is no exception. Since last September, we have worked on increasing our rover's robustness and developing systems that will enhance our scientific discovery capabilities. With its 4 steerable wheels, differential system, and increased suspension robustness, Kirby can traverse rough and uneven terrain with ease. The wheels are coated with polyurethane, which increases the rover's grip on steep slopes and prevents any slippage. The rover's differential bar ensures stability during uneven terrain traversal, while the service module protects our custom-made electronics and power supply module from harsh weather conditions. Kirby can move forwards and backwards, turn on itself, and drive on inclines up to 20 degrees. We can control the rover manually by receiving video feed from 4 cameras attached to the rover's chassis and 2 located on the handling device. Autonomous navigation is made possible thanks to our LiDAR and stereo camera. By merging data from these sensors, we can reconstruct a 3D point cloud of the environment and use this to generate a cost map of the terrain. The addition of the stereo camera this year gives us a denser point cloud, which in turn improves obstacle detection and makes the rover's traversal more secure. If any form of danger threatens the rover, an accessible red emergency button can be pressed at all times. This will cut the power from the battery to the rest of the system and stop the rover's movement immediately.
Kirby's handling device is crucial to completing the maintenance and scientific tasks. Its 6 joints provide flexibility in manipulating small elements on a control panel in direct and inverse kinematics. A voltmeter is attached to the arm's end effector, allowing us to measure the control panel's voltage during the maintenance task. The handling device is also equipped with a raster device inspired by NASA's mining robot. Rotating the raster in the soil will allow the rover to perform sampling of regolith. Once the surface sample is acquired, it is dispatched in a container located at the back of the rover where samples can be weighted. This year, we aim to perform the maintenance task autonomously. By using a depth camera attached to the gripper to detect AR tags on the control panel, we can acquire knowledge on their position and perform path planning. This year, the science team faces a new challenge, collecting a deep sample at a minimum depth of 30 centimeters and with a mass of 100 grams. To accomplish this mission, we designed a 2 degrees of freedom drill powered by 3 DC motors. These include 2 actuators for linearly ascending and descending the first and second stages, and another actuator to operate the drill's auger in rotation. The first linear stage encompasses the support module responsible for holding the container and conducting the science experiments. Its objective is to reach the ground to facilitate the drilling operations. The second linear stage, known as the motor block unit, allows the drill to reach this 30 centimeter depth mark by simultaneously rotating the auger and translating it downwards. Our student-made drone Broccoli will lift off from the rover during the science task, take a high-resolution picture of the Mars yard for interesting objects observation, before landing back on the rover. This year, our science plan is dedicated to understanding the soil's fertility and assessing the potential for farming on Mars, taking space exploration to new frontiers. This crucial step paves the way for the establishment of durable human colonies on the Red Planet. To carry out this ambitious plan, we rely on 2 multitask sensors and 1 spectroscopy sensor. The 2 multitask sensors allow us to collect data on the soil's nutrient concentration, such as nitrogen and phosphorus, along with the local soil temperature and humidity. The spectroscopy sensor is located within the science experiments module. By emitting light at different wavelengths, this sensor captures the refracted light from the soil. Composition is identified by comparing the light spectra to a library of known spectra related to a material. Finally, a rock will be collected during the science task. We have designed a simple and large collection container to allow the robotic arm to deposit the selected rock and weigh it in situ.
Hello, we are Team Roverova from VSB Technical University of Ostrava, and this is our rover, K3P4. Our team was formed at the end of 2016, and since 2018 we have participated 4 times in the European Rover Challenge and once in the Anatolian Rover Challenge, where we ended up at the 4th place last year. We meet twice a month to manage the tasks in our team. The work is organized through a Kanban board, with each team member responsible for a subset of tasks. We design our rover in cryoparametric, with its product lifecycle management tool Windchill, which allows all team members to have the current 3D models and documentation. Our workshop is equipped with 3D printers, a pedestal drill and handheld power tools. Therefore, to be able to produce parts in-house, the mechanical design is mostly focused on 3D printing or parts that do not require heavy machining. The rover's mobility system consists of an undercarriage with a rigid rocker suspension. The four wheels have integrated hub motors with planetary gearboxes. There are also 90-watt DC motors with planetary and worm gearboxes, which can steer the wheels individually, giving the rover the ability to drive using several configurations. We designed this suspension with rigidity in mind. Our 3D printed tires help the wheels get necessary traction and provide the rover with compliance to terrain. This, along with the rocker suspension, gives the rover good driving characteristics in terrain with relatively high maximum velocity. The mobility system without additional modules with 35 kilograms can traverse 20 centimeter high obstacles and drive on an incline of up to 40 degrees. The electronics in the rover are divided into two circuits, one for motors and the second for the logic components. An emergency stop button disconnects batteries from both circuits. At the heart of our rover is a Jetson Xavier NX computer, which communicates with various microcontrollers in additional modules. Power distribution boards and driver boards are custom designed and allow us to fit all necessary electronics even in tight spaces. The rover is equipped with a 6 degrees of freedom manipulator that was designed with 3D printing in mind. Two of the joints are utilizing custom 3D printed cyclodal gearboxes that were thoroughly tested in our lab. We have tested the arm in various manipulation tasks. For example, here in our lab, the operators are controlling the arm to use a door handle, fully open the doors and drive through tight spaces. The arm is capable of grasping handles and pulling on drawers. The operator can utilize multiple ways of controlling the manipulator: direct teleoperation with an intuitive human-machine interface, or driving to safe positions, or using inverse kinematics to drive in various specific directions. With this capability, the arm can perform all of these manipulation tasks, for example, grasping objects, delivering objects, turning screws, and rotating valves. All of this while being observed by the operator with multiple camera views. There are several cameras on the manipulator and the end effector and the arm itself, for example FPV cameras, IP cameras or webcams. The arm is also capable of more fine control that allows for operating joysticks. The arm is also precise enough to insert a USB connector and to type on a keyboard. The arm itself weighs 9 kilograms and can grasp and carry objects of various sizes, weighing up to 5 kilograms, or pull heavier objects. We can combine the movement of the arm and the undercarriage to perform tasks that exceed the manipulator workspace. For example, putting a blanket on a human figure. During the science mission, we will collect soil samples to determine the suitability of human settlements in the vicinity and insides of lava tubes. The samples will also be tested for their chemical composition to find if they could be used for 3D printing Mars habitats. We have designed a laboratory module to perform preliminary tests. The module will deposit selected amount of soil into vials with reagents. A camera then observes the chemical reactions. Another set of tests will be done on the samples after they are retrieved by the team members. The laboratory module can also heat and boil the samples when necessary. The rover can be controlled with an 868 MHz RC transmitter or over Wi-Fi. If a signal from the RC transmitter is not available, the rover automatically switches to Wi-Fi. Video from IP cameras and webcams is transmitted over Wi-Fi. These cameras are high definition and capable of 4 times optical zoom. The Wi-Fi can, however, slow down the video transfer depending on the signal strength. That is why we have also implemented analog FPV cameras. The video from analog cameras is transmitted over 5.8 GHz band. Multiple analog FPV cameras with the video signal switch are used for low resolution but real-time feedback. With these systems, even if the rover loses Wi-Fi signal, we can still drive the rover with visual feedback. which allows us to finish missions even in environments without line-of-sight communication. The Wi-Fi and analog video have range of about 1 kilometer. The RC transmitter can control the rover to up to 10 kilometers. The cameras, along with real-time 3D visualization, provide good situational awareness for the rover operators. The autonomous navigation is implemented through ROS. The standard MoveBase package was customized for our needs, to work with our rover geometry and to perform the search for goalposts and gates. The localization relies on the fusion of visual and IMU odometry from Z2 camera, wheel odometry, and data from GPS module. The navigation algorithm is running on the rover itself and does not rely on the wireless connection to the operator station. Right now we are in the process of testing different search strategies in simulations and real field conditions. Once the rover reaches the desired coordinates, it will begin a search strategy to find the goalpost, attempt to drive near it, and display its current state with the lights on its mast. Our team is looking forward to competing once again in the European Rover Challenge. This international event brings together the brightest minds, and we're eager to showcase our latest innovations. We're excited to meet everyone in Poland and wish all participants the best of luck.
During the European Rover Challenge 2023. Today's day, it's called Artemis Day, and it's dedicated to the moon. And it's my pleasure to welcome James A. Skinner Jr., supervisory geologist and USGS NASA Planetary Geologic Mapping Program coordinator, who will join us online for this talk and will share his thoughts about the unique role of geologic mapping in support of lunar exploration. James, can you hear us?
Yes, can you hear me?
Yeah, we can hear you very well. So I would say the floor is yours, or the screen is yours.
Excellent. Thank you so much. It's what a pleasure to be here, and I really appreciate you all taking the time. Congratulations to all the participants, and it's been really nice to see over the past day or so, and I'm looking forward to seeing more. So thank you for having me. What an honor. I wish I could be there in person. What I'm going to be talking about today is planetary geologic mapping and what that means, especially what it means for lunar exploration and the upcoming Artemis missions. And so this is something that we spend a lot of time with here at the U.S. Geological Survey, which is in Flagstaff, Arizona, and I'm happy to share this with you. So a little bit of an outline here. We'll talk about what geologic mapping is and what that means for lunar exploration. And speaking specifically about the past, there's USGS Astrogeology Science Center. It's the first building here on our campus. And it was built specifically to support Apollo. We'll also talk about a little bit about astronaut training and what astronaut training means, especially for geology, and training a lot of these folks who are not geologists to go to the moon and act like geologists. And then the last thing I'll review is two different field operations and testing opportunities that we have ongoing here in northern Arizona. So we're going to talk about the past, we'll talk a little bit about the present, and then we'll talk about the future, which is really exciting. So first of all, who am I? So I work here at the USGS Astrogeology Science Center. We are USGS, we're not NASA, but we get most of our funding from NASA, and we work very closely with our NASA colleagues. I've been here for just over 20 years now, and we got geology degrees. So I'm a geologist. I got geology degrees at North Carolina State and Northern Arizona. And before I came back to research, I worked in environmental and oil industries. Like I was introduced, I am the program coordinator for the USGS and NASA Planetary Geologic Mapping Program. So we're in charge of making all the geologic maps for solid surface bodies in the solar system beyond the Earth. We also do a lot of field training in geologic mapping and work with NASA on the role of geologic maps in missions. And then as a kid, you know, I love maps, I love rocks, I love space. And so I feel really fortunate to be able to do what I do and to be able to share the excitement of lunar exploration and geologic mapping with you folks. Okay, so first of all, let's talk about geologic mapping and what that means. A geologic map is a bulk a chart of bulk geologic observations. And so, we walk around out in the field, we go into the forest, we'll see rocks distributed over the surface. And so our job as geologists is to recognize what kind of rocks they are and to map them out and chart them specifically onto a paper product. These days, we also have digital products. That's great. But it's really important to note that these are geologic observations, and the map is supposed to visually convey the geologic history, how that area formed, and provide context for exploration. On the left-hand side of the slide here, you see an excerpt from a geologic map in northern Arizona. This is a very famous volcano, that little black area there, called SP Crater and SP Flow. This is an area that we do a lot of training. And the point here is to show that on the left, we have satellite images, and on the right, we have a geologic map that is derived from both field observations as well as looking at orbital or satellite images. So in general, geology is the anatomy of landscapes. When we look at geology, we look at rocks, we look at all the sediments, we're trying to put together the history of that one area and what it means for the formation of whatever body we're studying. So there's two different things that we always talk about here is that terrestrial geologic mapping. When we get our degrees and trained as geologists, we are doing everything here on Earth where we can actually go up and touch the rocks. Sometimes you'll see geologists even want to lick a rock. And so we want to get our hands onto the rocks and be able to look at it. And so we observe samples at outcrop. So outcrop is when we can actually walk up and touch the rocks. And we take samples that are about the size of your hand and that you can look at. And what you're looking for is the color of the rock and the minerals they contain, the grain sizes that are there. If there's any kind of horizontal layering, the way one unit matches up with another unit that might be a kilometer away. So we do a lot of field work. We take hand samples. Sometimes we'll sketch out what we call sections, which is how things are varying vertically, and then we'll match those up from place to place. We might take samples and take them into the lab and look at them in a certain way, and then we'll mix all of that together and create a geologic map. But it's really important to note in the upper right there, you see that the field work is outweighing the orbital or the satellite image observations. And in the end, we make a map that shows the distribution and history of these rock products. So planetary geologic mapping is very similar, but it also has some key differences. The main thing is that the orbital observations are what are outweighing the field-based observations. We can't really have the opportunity to get out there and put our hands on these rocks. And so we have to do a lot of different things to make sure that we can get the information that we want. We observe the surface in various data sets. On the left-hand side, you see Mars actually with various data sets from topography to images to kind of thermal and compositional data. We look at the shape of the land surface and specifically the landforms, what kind of landforms might be there, colors and tones. We use data, and then right in the middle, we use just different visualization software because we have a lot of data and we can stack them all together. This middle image is actually of the polar deposits of Mars, looking at them in 3D. And then very importantly, we use our knowledge of geologic processes on Earth. So we have to combine all these together. And again, we make a map that shows distribution and history, but there's some caveats and some things that we have to consider as we move forward. For example, when Gene Shoemaker, who was a USGS geologist, and a lot of the other folks that were making maps of the lunar surface back in the 50s and early 60s, it was unclear whether the mapping methods that they were using, they were excellent trained terrestrial geologists, but were those methods valid on other planets? We're using remote observations. We can't touch the rocks. We have very limited data sets, and sometimes we have information in one area and might not have it in another area. What exactly do we describe and in what detail? And then very importantly, how do we infer 3 dimensions? Because geologic mapping is not about talking about the surface only. It's about trying to correlate things both in space and in time to get a history and a story. So on Earth, terrestrial outcrop, where we see those rocks, are formed by tectonics and erosion. You have plates that are active, they bring rocks to the surface and they erode away. We don't have those similar kinds of processes on other bodies. And so often those rocks are buried. So we're looking at things that are distributed across the surface, and they're very sedimentary-like. They have rocks and boulders. And so we need to be able to use that information to infer the geology. How similar are these geologic processes? In the end, the punchline is that Gene Shoemaker and his whole cohort and other folks that were working on mapping address these questions. And the concepts of mapping work because they're based on observations. So if we focus on observations alone and then offer up interpretations, and it's a very effective way to get geologic maps. So really brief principles of geology as a lunar example. On the right-hand side, you see a little snippet of an area on the lunar near side, and there's different kinds of landforms that are here, from impact ejecta and impact craters to little mountains and volcanic rivers. And so if we take that blue line and take a little slice away and look at things in 3 dimensions, what we're seeing is the mountain is actually poking up from the subsurface, and you have all these plains materials and kind of lava flows that are infilling around it. What you can do then is to start sequencing things out. The oldest thing here are these mountains that are poking up. If you look at them in cross section, you can see them going beneath the lava plains. And then the youngest things are the things that are sitting on top. It's just basic superposition, what sits on top of another, kind of like that old game of pickup sticks. So the youngest rocks here are these impact ejectas from the impact crater that's labeled DI. So if we take this principle and look at it, so Don Wilhelms was another mapping geologist here at the USGS, and he pointed out that the goal is to portray units not just similar appearing, things that have the same shape, but rather look at them as a whole so that we can extract 3-dimensional bodies of finite horizontal and vertical extent. Basically, what we want to do is not just circle things that are bumpy and things that are smooth. We want to be able to look at that into the subsurface and get them in 3 dimensions. And that's effectively mapping out the building blocks of the crust of a planet. So how do we apply this? Well, if you take these principles and start looking at all the data sets, you can create a geologic map of any one body. This is what we call the Unified Geologic Map of the Moon. That was made from the USGS, but it was compartmentalized and put together from lots of different maps and stitched together to create a geologic map of the entire surface of the moon. And so this is a really strong and powerful product to be able to understand the history of the moon. It serves as context for other folks to do their scientific investigations. And other people can go in and look at the data and try to poke holes in the geologic map. Once you have a geologic map as a tool, but you always want to refine it with new information and new observations. And so it's kind of a snapshot of the way we understand the geology of one planet at any one piece of time. So what do the maps do? Well, there's 2 different things in general that they do. They establish fundamental science. Like I said, it's quite simply geologic maps guide research. It's what we call fundamental science or even basic science. It's understanding the natural phenomena of the way any one region or any one body works and how that is formed through time. Importantly, as we move forward, especially into Artemis, we need to start talking about applied science, and that is exploration. So geologic maps for exploration, resources, hazards, where are the boulders and where are the slopes that are too steep that might cause some problems from a hazard standpoint. Where are the rocks in the subsurface that we might be able to push together to create a berm that will protect our lander from a habitation unit, for example. So all of this will be folded into traverse planning. So now we're at a place where we're in 2 different things. So fundamental science and then applied science. The fundamental and basic science concepts have to be developed first, and then we can apply them. This is what happens on the Earth all the time as we make a highway through any one area. First, we need to understand what the context is. We need to understand what rocks are there and how we can excavate things away and make it safe for users. So there's obviously certain challenges here. One of the focuses that we are on right now is, especially for Artemis, is looking at scales of maps. On the right-hand side, you see a pre-mission map of Apollo 17. This is the Taurus-Littrell Valley. And superposed on top of that, kind of at an angle, is the actual traverse path placed over the pre-mission geologic map. And so we need to understand what scales are appropriate. 2 or 3 slides ago, when I showed you a global geologic map of the moon, that's great for context and understanding all of the different units that make up that body, but it's not great for landing sites because it's just not detailed enough. So we need to understand what map scales and what content needs to go into these landing site maps for Artemis. We also need to understand who the users are, because it's not just one map for everybody. One map does not rule them all. One map will be used for the crew. Another map will be used for the back room. The folks that are planning out the tasks and traverses and safety will potentially use even another map. So it's all the same information. It's just pulling that information and putting it together into different maps to make sure that the users have the information that they need. Then obviously we need to talk about data formats and the methods and all the things that go into making a geologic map. We need to adapt those methods, especially moving from science into applied science. And then I've underlined here this last bullet point. One of the key things that we're dealing with Artemis, because we're going to the lunar South Pole, the lighting conditions are very challenging. These low light conditions are going to cause all kinds of problems for landing as well as traversing. We're in a place where there are permanently shadowed regions. One of the reasons why we were going to go there is because of these PSRs. They are cold traps, and we have lots of evidence to show that they are cold trap for volatiles, including water ice. But they are some of the coldest places and darkest places in the solar system. And so there are lighting conditions, there are hazard conditions that are posed for landing and operating in and around the lunar South Pole. Imagine every day if you woke up and the sun was about 6 degrees above the horizon and it was spinning around you all day. Same kind of thing that would be happening on Earth at very high latitudes on either pole. So we need to train the astronauts for the expected conditions. And one of the ways that we can do that is by creating and having them use geologic maps. So then let's talk a little bit about astronaut training and what that means. Astronauts are being trained in multiple places. NASA trains corps of astronauts, both from NASA itself as well as from different international partners. And they receive training in geology. Most of them are not geologists. We just had one that flew, that just came back off a space station, who is a trained geologist. But most of these folks are medics and biologists and lots of pilots. And so we need to be able to get them to understand what they're going to be seeing when they're there. This is not dissimilar to what happened with Apollo. On the right-hand side, you see Gene Shoemaker, who was kind of the founder of astrogeology and certainly the founder of USGS astrogeology, on the rim of Meteor Crater using his rock hammer, this classic kind of pose there, pointing out to Apollo astronauts the kinds of rocks that they see on the edge of this impact crater. So we train mission teams, we train flight operators and the engineers, the suit and software folks, and we still use this region in northern Arizona. It's an excellent ground for exploration. And in fact, every astronaut that walked on the moon trained in Flagstaff. Why? Because Arizona has a lot of terrestrial analogs that are very applicable to understanding how we're going to operate. And not only that, it is because it's in an arid environment, we are in a desert, we don't have a lot of the vegetative cover that we see in lots of other places. So the rocks are at the surface. We, of course, have bushes and grasses that are there, but very often they are exposed, and so that makes it be a good analog. So on Earth, we have volcanoes, and you have the equivalents on the moon. We have lava tubes in northern Arizona that have been studied and are being actively studied right now as places where astronauts be able to go to find some safety, and we have those examples on the moon as well. And then, of course, we have impact craters. Meteor Crater is a very famous impact crater in northern Arizona, and we have excellent impact craters all over the surface of the moon, as well as other bodies. So we prepare astronauts for geologic observation, and we do that through field training. The last two classes of astronauts that have come out here, we just had one this past June, and this is the 2021 class on the right-hand side there. Their nickname is the Flies. And then the astronaut candidates in 2017, aka the Turtles. They were out here a few years before that, and these are just the two most recent ones. On the left-hand side, the folks that are circled in the orange ovals have flown or are on station right now. The ones that are in blue are scheduled to fly. On the right-hand side, the Flies, a lot of these folks are going to be the ones that actually go back to the moon in the Artemis mission. So we have the crew here. We are actually going and we're training them to be active participants in the geologic observation on that planet. So this is the Turtles. The training that we do includes classroom training. There's a lot of very intensive training and hand sample training and mapping that occurs in the classroom, and then they do some lab work as well. The training that is in the classroom is typically done at JSC, so that's in Johnson Space Center down in Houston, and then we take them out in the field in two different places, one in New Mexico, one in northern Arizona, and the northern Arizona example that they participate in is the second and kind of capstone project that they do. So this is the field trainings for the Flies that just happened this past June. We take them into the field and we do field trips. On the right-hand side, on the lower right is Meteor Crater. On the left is obviously the Grand Canyon. The upper left and upper right are the field area that we work in. And the goal is to get them out there looking at the rocks, feeling the rocks, how hard you have to hit a rock to be able to get a sample. What do you see in that sample when you look at it up close to your face? Which samples do you need? The Artemis crew is not going to be able to bring back every sample that they want. So they're going to be very limited in the mass. And we need to get the astronauts thinking about what is a good sample, what is a representative sample, the best sample that I can bring back for people to study, not just in the next few years, but for posterity. There's people that are going to be studying a lot of these samples that come back from Artemis for decades to come, and we need to get the absolute best sample that we can. So what is the purpose here? Apologies for the eye chart, but I hope that people can kind of glance through this. But the purpose of, when we talk about ASCAN, that's Astronaut Candidate Field Training. And the purpose of this is kind of threefold. It's the practical application of the classroom. They learn things in the classroom, and that's great. But we all know that, you know, learning something from a book is not the same thing as getting out into the real world and doing those things yourself. And so we want to have them trained, and then we want to get them out in the field so they can learn how to swing a rock hammer, take a sample, and very specifically describe what they're doing. Because one of the key things that the crew will be doing on the lunar surface is talking to the ground. They'll be describing what they see. They'll be taking pictures. They need to rationalize where they're going and why they're going to those places. The next thing is field objectives, is looking at scenarios, developing hypotheses, testing those hypotheses, understanding what samples are helping address the questions that are the most salient questions that we have for the people that are on the moon. And then last, and very obviously, and it's very fun as well, is this expeditionary skills and behavior, is learning how to work together as a crew. These folks are, you know, once they are astronaut candidates, they're working very closely together for 2.5 years or so. And so emphasizing those expeditionary opportunities, team building and leadership, breaking crews up into smaller teams so that they can tackle problems very quickly, and then learning how to communicate that information. Like I said, being able to talk through what's going to happen is going to be very important for the crew. They need to be able to vocalize their observations and be very consistent. Okay, that's great. So we've been through geologic mapping, what that means. We've been through some astronaut training, and now I want to review two of the opportunities that we've had over the past few years or so, up to 10 years ago even, where we are looking at preparations in the field for operations of Artemis and beyond. So training to implementation, that's what we did in Apollo. We were training out in northern Arizona. And so there's suit tests on the Bonito lava flow, which is a very young lava flow in northern Arizona. And then there's Jack Schmitt standing next to Split Rock in the Taurus Luttra Valley in Apollo 17. And the same thing with the rovers. And so we're just testing the opportunities. How do you make observations? How do you communicate? How do you rove across the surface? So you do it in the field so that when you get there, you're experienced and you know how to do it. I'm always struck when we're doing a lot of these tests because what we're doing, so on the left-hand side there's suit tests on their knees with the San Francisco peaks and Flagstaff right back there in the distance. And so that was in 1964. And now fast forward to 2022, and we're doing the same things. This is from last year's operation, and we have 2 suited crew members in the field pushing around carts and learning how to use the instruments. And so we're doing a lot of the same things. We're trying to leverage the lessons that we learned from Apollo and apply them now. Obviously, there's a lot of differences in technology and tools. And so, we're doing the same thing. And I'm always struck of how much we have done and where we come from and what we continue to do. It's a lot of fun. So the first thing I want to talk about is what's called the joint EVA. And EVA is an extravehicular activity. So that's when you go outside of any kind of vehicle that you're on. You can do that on space station. That's an EVA. Or you can do it on the lunar surface. That's also an EVA. So the Joint EVA Test Team, or JET, is built specifically to do Artemis 3 simulations. So this is not talking about Artemis 9 or 10. This is talking about Artemis 3. 2 suited crew members that are on foot, because Artemis 3 will not have a pressurized or even an unpressurized rover. JET 3, which is the 3rd test of the JET program, was last October, and JET 5 is going to be this October. We are in the throes right now of getting everything together for this JET 5 test. We make all the geologic maps. We have a science back room. 2 crew members from the astronaut corps are in the field. We have mission control and science back room. So there's a full communication loop that is happening between the science room that's talking to the flight controllers that are then talking to the crew in the field. So the whole thing is a test, not just for the crew and science and geologic maps, but for communication and for suits and for tools. Everything is being tested here. And we learn a lot. It's a really big test with lots of people involved, but it's one way for us to move forward really quickly and understand how to operate on the moon. 4 EVAs. Last year it was 2 4-hour EVAs and 2 6-hour EVAs. And like I said, it's a full test and refinement of the range of science and operational parameters, specifically for Jet 3. So we make science traceability matrices. We have a geologic map. We kind of understand, what do we want to sample? Where do we want to go? And so we are the first thing is that we make a geologic map and establish an understanding. That's that context of what maps provide for you. We identify the stations and the locations that we want to go. And then the tasking folks will identify traverses that get us between those stations safely. And so there's a big interplay between science and engineering. And what we're doing is, a really interesting point, is adapting operations on the International Space Station. The International Space Station, when the astronauts leave the airlock and work on the International Space Station, they're working on a vehicle. It is a piece, an equipment, a piece of like a device. And so it is something that is very known. When they get on the lunar surface, it won't be known. And so we need to be able to kind of switch some of the engineering perspectives from working on something that is a known commodity into something that is unknown. And so all of these things work together to create this jet test. Is looking at science and flight operations. There's a back room. They have maps. There's a whole crew of people that are talking about different roles and responsibilities, tools, products, the decisions and the speed with which those decisions need to be made. We're even talking about the science back room and where the desks need to be and what kind of screens and what kind of maps we need. So we're in the mode of testing out what is needed for Artemis 3. And then you also have science in the field. And so my role in this last year was to follow the crew around in the field. On the right-hand side, you can see that it's nighttime, and the nighttime was supposed to emulate this low light conditions that we'll be experiencing at the lunar South Pole. And so these were nighttime tests starting about 8 p.m. and running all the way until about 2 or 3 in the morning. And so the science in the field is looking at the efficiency of the product, the value of that traverse. Are there any missed observations from the crew? And if so, why? Is there something that we can do better in training or in the geologic maps to help them get a better awareness of where they are in the field, to increase safety and to improve science? This is a really interesting photo. This is the ISS. So we were out there and looking up at the International Space Station. The International Space Station was up there and looking down at us. And so this is kind of a back and forth, just really emphasizing the fact that we're going. We have people that are up there right now that are aware of what we're doing. And we are training these folks that are amazing human beings that are going to be able to expand that kind of science envelope for us as we move humankind back off the Earth and into other bodies. So the next opportunity is the Desert Research and Technology Studies, or what we call DRATs. This is something that's been going on for over a decade now. And these are extended Artemis simulations. So it's the same kind of thing, but it is suited crew, but they're in pressurized rovers. So they can take on and off their suit. They can leave the rover and they can rove around and get back into the rover and move. So we've done this in 2009 and 2010, a little bit of a hiatus, and we did it again in 2022, so last year. So these are our Artemis missions, but they are very long term. So Artemis 8, 9, 10, 11, when we actually have the pressurized rovers on the surface, and we are in the process of establishing a base and operating there for lengthy periods of time. These are technology tests, 2 crew members from the astronaut corps. Again, we had the mission control and the science back room. We had long EVAs. This was done with some of our international colleagues from Japan. And so some of the crew members were Japanese, some of the equipment was Japanese. The point here was to test rover capabilities and its role in exploration. Habitability, how can you live in it? What are the speed, maneuverability, what kind of window configurations, those kinds of things. And again, we are relying on geologic maps to identify the stations and the traverse paths. So this was the 2009 daytime operations. There was a habitation unit. There was some unpressurized rovers. The design of the rover at the time was that the spacesuits would be attached to the back and that the crew members would enter from the inside into the spacesuits, and they would detach themselves. And then when they were getting back into the rover, they would back up and kind of dock themselves and then pull themselves out of the spacesuit. That is no longer the configuration that we'll be using, but it was an interesting testing concept. So that was 2009. And then 2022, it was very similar, but nighttime operations. And this is showing a a couple of the crew members as they're moving around in the outside, and some of the training that we were doing. The lower left-hand side is showing the rover that was migrating off of a large lava flow. And again, you see those same background peaks in northern Arizona. So that's it, folks. Takeaways, we're going back to the moon. Geology is a key science driver here. For our role, geologic maps that capture the science are going to be important for safety, as well as improving the amount of science that we can give back and placing the observations that we have in hand samples into a location so people can study them for future decades. We are in the throes, completely right in the middle of testing and training all those science capabilities and what we can do to help the crew, help them be safe and to be good geologists on the lunar surface. And a sustained presence on the moon means that we have to have very strategic products. And so when I talked before about basic science and geologic mapping, that is definitely true, but we're at a place now where we are looking at applied science and how do you apply those maps to enable a sustained presence on the lunar surface. So thank you for having me here. Thank you for taking the time. I really appreciate it and having you listen. And I have any questions, then please let me know.
Thank you very much, James. I hope you can hear us. Can you confirm that you can hear as well? Yeah.
Yes,
okay.
I can hear you just fine. Thank you.
So thank you. I really like the last slide. I mean, the one with this summary saying that, well, we just don't go there just because we want to go there, but we want to do science, we want to explore, and we want to use it for a better future as well. So do we have any questions from the audience? Yes, I can see one.
My question is that we, most of us know, you know it the best, that there are many impact events on the moon occurring, well, even right now, but basically all the time. There are flashes on the moon and so on. My question is, how does a small asteroid impact the geological survey and the changes in the maps?
That's a great question. Yes, there are impacts that are on the surface of the planet, and they are causing different things to churn up on the surface. And so because of the rate of them and how infrequent they are, they tend to be really small as well. And so from a geologic mapping perspective, when we're talking about regions and we're talking about the whole globe, they do not change the geologic map. However, when we start talking about these very localized geologic maps that we need to make, then they can certainly cause new ejecta, but it would be very, very localized. So there have been some studies looking at these bright flashes and where we have new impact craters. And if you zoom into them, you will see that they are very, very localized, and they are distributing rocks across the surface. And so they're basically creating new geologic units, but they're so small and localized that it's not something that we really factor in when we're making our geologic maps. But it's an excellent question.
Thank you. Any more questions? So I think we can smoothly go to the debate that is waiting us right now, and a bit extend the topic. That it was a great introduction. Thank you, James. And James is actually the first panelist of the debate, so he will stay here online. And let me invite on stage our special guest, Nico Detman, who is the European Space Agency Head of Lunar Transportation Group. And Professor Grzegorz Wrochna, President of the Polish Space Agency, Anna Krzyżanowska from the Danish Technological Institute. And we have also two more guests that are joining us online. Maria Antonietta Perino from Thales Alenia Space. Can you hear us? We can see you. And Dr. Gordon Wasilewski from Off-World Europe, who is also joining us online. Hello.
Hello.
So can we just make a test with the sound? Yeah, I think we can. Maria seems frozen, but can you hear us at least? Well, Gordon, I can see you can hear us, so yeah. We'll try. Yeah. So maybe I will go this way. So maybe I will start with the guests who are here on the stage, if you don't mind. I just made a short intro saying your affiliations and so on, but could you please share a bit more about your connection to space? What's your role, and also how are you connected with the moon exploration? Because that's what we're gonna talk about Artemis and moon exploration. So that would be lovely to hear.
Thank you. I got interested in space when I was a very young kid. The first book I have read was about the mysteries of the universe. But then when it turns the time that I should select my study subjects, I selected particle physics, because particle physics told us about the great mysteries of the universe, about the Big Bang, about the creation of elements, about the creation of galaxies, what's going on in stars, and so on. And now I'm the president of the Polish Space Agency.
Okay, so my very personal experience with Moon is, it's actually the first TV event I can remember in my life. I was 3 years old, and it was the first time my parents pulled me in front of the TV, and I realized not what's happening, but I realized that's something important. It was not the spiking arc which, let's say, at the end propelled me into my current position. I started quite differently. I was an aircraft mechanic. Then I studied aerospace engineering. Actually, I was initially more interested in launches, and a bit by coincidence, I ended up in human spaceflight, and I'm now in charge of the Lunar Transportation Division in ESA.
Okay, since I was a little child, I was really thrilled into different kind of technologies, and especially astrophysics. Every time when I look in the sky, I was very amazed, and I was always very curious. I was curious about the working principle of different devices, and this was my main driven through my life. And then I was studying electrical engineering and nanotechnology. And as I always said, space was following me, and it still does, because I was an ESA consultant before, and right now I work as a specialist at Danish Technological Institute. And here my connection to space and lunar exploration is one of our projects is about delivering smart skin for robotic arm.
So maybe Maria? Hello?
Yeah, can you hear me?
Yes,
we can. Hear me?
Yeah, we can hear you well.
Good afternoon, everybody, and thanks for inviting me. So my connection to the moon is very similar to what Nico just said, except for the fact that he was a few years older than you, Nico. So he was 8 years old, and I perfectly remember that event. I was watching with my parents in a black and white television the landing on the moon, and these people jumping on the moon. And I remember that I thought, wow, they look so happy. It must be a lovely place to go. I want to do the same. So that was the initial click. And since then, my path brought me toward people that had a link to the moon. Let me just mention Buzz Aldrin, but not only Buzz, Wendell Mendel, and many other brilliant scientists and astronauts. And I've been spending my life in trying to contribute to exploration. Currently, I don't know if that can be of interest. I've been working in Thales Alenia Space for decades, and currently I'm dealing with space economy. So trying to, how can I say, tackle the new missions, not only from a scientific point of view, but due to the fact that there are many interesting resources there. The point is to go back and try to, how can I say, contribute to a better life on our planet. So we go in space, but with strong links to our planet.
Thank you. Gordon?
Yeah,
Can you
since
share?
I was a kid, I was always fascinated by space exploration since I had my first telescope. But I never saw myself as anything more than a mere observer until I learned about space resources, drilling in space, mining in space, back in 2014 when I was studying petroleum engineering and mining. And only since then I fully focused my career, my endeavors on ISRU, on space resources research and technology development, and it's been 8 years since I've been doing that. It's fascinating time. Now I'm at Off-World Europe in Luxembourg, and we are developing ISRU excavation and extraction and processing technologies for lunar exploration, for lunar missions. And yeah, I'm so glad to be here and have this opportunity to share a bit more about my opinions and in this panel.
Thank you. James, would you like to add something?
No, I think I've already gone through most of my like where I got into this, but I am fascinated with everybody that just talks about how this has been something that has been interesting to them since they were very small, and I find that to be space is very inspirational, something that can bind us all together, that we can all work on collectively. I'm always interested in the work that we do and working with so many different kinds of people and who you get to meet. And so I love the concept of exploration. From my point of view, is from a geology and science aspect, but just being able to connect people together, both nationally and internationally, has been a really big deal. And I encourage it, and I feel like it's very inspirational.
I had the honor and opportunity to meet 2 days ago in Bremen the Artemis 2 crew. And even if those guys won't put a foot on the surface, it's amazing the motivation, the enthusiasm those are putting in the table. And it's really an honor and opportunity to, let's say, contribute in bringing humans back to the moon.
So yeah, but that's the question that I guess we often hear, especially for those who are not very deeply into the topic. Why we haven't been to the moon again yet, and what are the biggest challenge? Why does it take so long to get back there? If anyone would like to answer that question or comment of that, I'll be happy to listen.
So I think we know only since the Earth, the Moon Reconnaissance Orbiter missions in 2009 that there is abundance of water, which makes obviously the Moon much more interesting than the years before. There's always the question, why after 50 years? I would say comparing Apollo with Artemis is comparing apple with pears. First of all, we know that Apollo missions had a much different risk posture. If we fly Artemis crew, we take the responsibility to bring back the crew in a reliable manner with a percentage of higher than 99%. And we are going, and we have heard this already from the speech before, we are going to land in a much more difficult area. So therefore, it's also from a technological point of view, quite a different challenge. And that might explain why we are coming back a bit late. And I think it took some time for the whole community to agree that Moon is a mandatory analog test bed before we consider missions to farther destinations.
I can add to that this 50 years gap was due to the lack of motivation. I mean, the first landing on the moon, apart from all the political reasons and some games between the big countries at that time, it was driven by curiosity. I mean, we all have this in our genes. It is very human. Navigare necessest. We need to go somewhere. We need to visit new places. We need to put our foot on new ground. And this was Apollo 11. But if you remember the movie Apollo 13, TV was not interested anymore in transmitting Apollo 13 landing because it was boring. We were already there. The footstep is there. So what's new, right? And this lack of motivation, I believe, was present for the 50 years. And what has changed, indeed, the technology now is ready to bring people to Mars. And the moon is just the step towards Mars. That's one motivation. The second motivation is that technology was developed into the point that we can build permanent bases on the moon. Likewise, we have on Antarctic pole, not to live there, I mean, not to grow children there, but to be permanently there for scientific reason, for testing technology and so on. So we have a new motivation, and therefore we have a new program.
If I may add something to this, I agree on the point that we need to collaborate and we need to have different countries contributing and different agencies contributing to this mission. And besides this, we are observing right now a huge development in the commercial space sector. And I think these joint forces with national space agencies and commercial sector will bring us further. And this is what we are observing now after 50 years. It's taking a big part, commercial space sector.
Yes,
yeah, these are all great points.
Sorry.
Maybe Maria.
No, go on. Sorry.
No, I totally agree with Anna. The newcomers, the new protagonists, I shall say, in space, private industries, private people are really changing the paradigm. Until, let's say, 20 years ago, whenever I was part of this seminar, of this workshop involving international colleagues, everybody was aware that the budget was somehow, limited. And so how can I say, the decision where to address this budget was very political. I remember that for many, many years, the strong push was, exploration was focusing on Mars. Moon was sort of in the background. But then, as Anna said, we started to have new players that succeeded also in developing transportation capabilities, not just payload or satellites. And that changed the story. And so now we have different destinations. So Mars, for sure, is always the key goal. But on the way to Mars, we are developing infrastructures, commercial infrastructure in orbit around our planet, in orbit around the moon, on the moon, and so on. So for sure, the puzzle is becoming multidimensional.
Yeah, these are all excellent points. And I think what's binding them together is the resources that were mentioned. The moon holds an abundance of resources that can revolutionize our presence beyond Earth. And among these resources, for sure, regolith and water ice stand out, but water ice is a game changer. It can be converted into life-sustaining resources such as drinking water and oxygen. And moreover, through the process of electrolysis, water can be split into hydrogen and oxygen, which are essential components of the rocket propellant. And by extracting these resources from the lunar surface, we reduce the need to transport them from Earth. We significantly cut the cost and environmental impact of space missions. And we've been doing that only now because only now we've saturated our orbits with commercial space, and our efforts can be pushed further out. And the first body that we can push those efforts to is the moon. We've had that short delay in exploration of the moon after Apollo, but we're going back. And I think the pipeline of missions that we're seeing right now, even right now en route, is tremendous, and it's just showcasing that we're really it's a really solid, and they're really passionate about that, and we really want to focus about that to set our presence on the moon first, so that we could go beyond that in the future. The moon as an antroport. That's what we are basically all fighting for at the moment.
Yeah. One last thing to say there, and I think that I agree with everything that everybody said, but follow on from that, those last comments is that this is still, exploration is inherently risky. And so this is not a slam dunk. This is something that a lot of people are working on. There is a risk that is involved here, and there is danger as well. And so it's taking this long to develop a lot of the technologies to make sure that we can get there, as was stated before, with a high certainty of success. And success is bringing crew members home. Science is secondary to that. So there is extreme risk here, and sometimes when we talk about it, we lose focus on that, and we want to make sure that everybody understands what is happening. It's very exciting. It's very risky. If you are having that risk, in order to be spacefaring people, then we need to go to the closest place, and the moon is the closest place. So if something was to happen, it's much easier, quote unquote, to get to the moon and back than it would be to get to an asteroid or to Mars and back. So we need to have that as that test bed, and to understand how things are going to operate, what kind of tools we need, what are the systems in place, so that we can start testing it and establishing those protocols and understandings, and so that we can move forward beyond the moon. So it's the first step off, and it's exciting, but let's keep in mind that the inherent risk is there.
Thank you. So, you brought it several times already, the subject of collaboration. So when we think about Artemis, okay, it's a flagship NASA program, but it wouldn't have happened without ESA involvement, and also in the involvement of any other agencies or countries. So could you elaborate on that, on the level of involvement or ESA and also Artemis Accords? What's the role of all these agreements in the program itself?
I could start on the ESA involvement in the flagship program. So first of all, we have to understand Artemis is not only the launcher or the Orion mission, it's also the gateway and the whole lunar surface architecture, which is still under definition. The contributions of ESA at this stage is on Orion is the delivery of the service module. We are extremely proud, having been selected as the only international partner to contribute with this powerhouse, I would call it, because it's actually the part which is in charge to bring crew safely into orbit and back. There is no crewed mission without ESA in this case, which is something we are very proud of. Then if we are looking on the gateway, the first mission is supposed to be in 2026. It will be the HALO module, which is a habitation module, and the power and electrical module. And this is then followed by two ESA modules, which is another habitation module and the Esprit refueling module. But ESA is also delivering the communication equipment, which is in charge for the communication between Gateway and the lunar surface. Through that agreement, ESA has gained 3 astronaut flights to the Gateway, dates still to be defined. Then if we are looking on the lunar architecture, where, as I said, the definition is not yet done, we are currently in talks with NASA to deliver the ESA-developed lunar uncrewed lander. It's a cargo lander. The maiden flight is planned for 2031. And the idea is to involve this lander into the surface operations on Artemis. And the last thing where ESA is involved is, once we are talking about the lunar infrastructure, we need to have, similar like on Earth, a communication and navigation infrastructure, and that requires a satellite system orbiting around the moon. There is a first Pathfinder mission, which is called the Lunar Pathfinder, which is scheduled as a piggyback mission on a CLPS mission in 26. And we are working with our industry on a program called Moonlight, which would be a constellation of 3 satellites, and then also helping this infrastructure to communicate and navigate. On the Artemis, of course, I would not like to comment for the following reasons. Those are agreements which are signed on governmental level and not on agency level. I think what is maybe of interest, those agreements are meant to implement the Outer Space Treaty from 1967 for the common and peaceful use of outer space.
I can add on this topic. Apollo program was announced by US as done for all mankind. Now there's a change of of attitude. This is rather with all mankind, or at least with the countries who are willing to participate. It is not easy. Indeed, it is governed by the international participation is governed by Artemis Accords declaration. I had a pleasure to sign this declaration myself for the Polish Space Agency 2 years ago. And now we work together in the group of Artemis Accords signatories how to include different countries, how to make significant contribution by the countries who are not necessarily which do not necessarily have a big experience in space technologies. They are just beginners. And for this reason, we propose to create a working group dedicated to this topic. And together with Brazil, Poland chairs this working group. We meet regularly online every month. And once, a couple of months ago, we organized a meeting in Gdańsk, very well attended, big delegation from US, both NASA and Department of States. We have guests from Japan, Brazil, Canada, 13 countries. And the results of the discussion will be presented in a couple of weeks' time during International Astronautical Congress. In the meantime, NASA already announced a call for instruments which astronauts will bring to the moon, and this call is open for other countries as well. For Artemis 3, I mean, the time is too short. We will not be able to prepare anything in time. But I believe that for Artemis 4, something from Poland will be prepared, and we will send some apparatus to the moon with this mission.
I can add to this. So what, in my opinion, makes this project beautiful, it's that it unites different countries, and different scientists are able to perform different experiments, because we need to remember, before we will send anything to space, it needs to be tested and requires certain type of validation. So that's why we collaborate between different institutes, universities, and organizations across Europe and also international across the world. So I think what is really important, that everyone can contribute to this Artemis mission, because we need to have several different expertise in order to be well prepared.
So it's like if you have like a company working space from space sector, so the way to go to be part of Artemis is to go through the national, let's say, governmental accords, things that the one that was already mentioned. So can you apply as a company itself for a given call, if there is any call for instruments or something?
There are two ways to go. You can cooperate directly with NASA, but then you have to have a daughter company in US, because dollars will not fly through the ocean. That is the rule. But it is possible. And to facilitate that, we talk to NASA, we talk to JPL, organizing missions for exploratory missions for NASA. We would like to contribute with some instruments, some apparatus, which will be provided by Poland. But then when we got this flight heritage, when we demonstrate that some apparatus is really working well, then we hope that the companies can work directly with NASA or with JPL. Other way is to go through European Space Agency, because the contribution of ESA is very important. And indeed, after the big increase of our contribution to ESA this year, I mean, I remind you that we have now declared, I mean, the Minister of Economic Development and Technology declared increase of the budget by 360 million euros. So in total, it's almost 500 million euro for next 3 years. We hope it will continue. So and part of this money, 100 million euro, goes to the human and robotic exploration program. So within this program, maybe we will contribute, for example, to the big transporter, which will be provided by ESA to bring some cargo to the moon. We are thinking for some important elements of this transponder. We are right now discussing with ESA what could be our other contributions. So this is also the way to go there. I mean, already on Artemis 1, 2 small equipment from Poland was flying. One was because of thanks to Institute of Nuclear Physics from Polish Academy of Science. It was an apparatus to monitor radiation level, and then from the Vigo System Company, infrared sensors to monitor the air in the module with astronauts. So we already have some involvement of Polish entities, but now we hope to make it much bigger.
Thank you. If any of the online guests would like to add anything?
Yeah, I like to share a very positive news with the audience today. You were asking before what happened, how the industry can be involved in this new adventure. Well, the good news, guys, is that in Thales Alenia Space in Torino, Italy, right now we are welding the modules for the gateway. So it's not just paper stuff, it's happening. So we have been waiting long, but finally we are really going back to the moon. We can touch the hardware. The hardware is coming into shape, okay? So I just wanted to share this very positive news.
Great news indeed.
Mm-hmm.
James or Gordon, would you like to add anything?
Yeah, just going back to the Artemis Accords.
Yeah,
sure.
please.
The U.S. interpretation of the Outer Space Treaty emphasizes the basic rights of individual states to allow private sector to engage in commercial activities in space. So it recognizes that the private sector plays a crucial role in advancing space exploration, bringing innovation, funding, and technology to the forefront. So the Artemis Accords enable and encourage cooperation between governments and commercial entities to drive the future of space exploration. And while it's true that space exploration has been historically domain of a few nations, the Accords changed that landscape. Signatory nations, as we've heard already, are actively collaborating on various aspects of lunar missions, and this collaboration extends to sharing of expertise, resources, and even mission infrastructure. So simple as that, by working together, we can pull our knowledge and capabilities to achieve more ambitious goals. And both Artemis program, which basically created the dawn of heavy landers, heavy launch capabilities, and focused our endeavors on the moon, and particularly on the moon's south pole, and the Artemis Accords on the one hand that are bringing together the international components to those endeavors, is facilitating all of that.
I would like to steal a sentence from another colleague, which I found very nice. He said, the next mission to the moon is not about to put a flag and a footprint, but it's a mission for humanity.
So in terms of a timeline, how does it go right now, the Artemis? So when will we get back to the moon, and what is the timeline for the next levels of the mission?
Well, I'm not supposed to say anything different than what is in the common plans. And the common plans is the Artemis 3 mission is currently scheduled for 2025. This first Artemis mission has still some challenges to overcome, which is amongst others the maiden flight of the Starship. It's a cryopropellant transfer in orbit, but it's also the demo mission of Starship landing. Before crew is put into the first flight, a demo mission has to take place. But considering the challenges which have been taken by this company so far, I'm optimistic. It's probably more a question of the when, but not of the if.
And then maybe I would like to ask about a bit more about what James said about the training of the astronauts to prepare for the project itself. So it's like how well do they go through some kind of like very general training in that terms, or are there already defined some like special subjects, tasks that they will have to deal with? Could you comment on that?
Yeah, that's a really good question. And so the launch is not going to be, the cadence of Artemis is not going to come down to training. It's a good point that we were talking about before with everybody on stage and online, that is that, this is a delicate orchestration between so many different entities. But as far as training goes, we will be, so Artemis 2 crew is actively doing geologic training right now. And that's geologic training, even though they are not going to set foot on the surface, just like the folks on station are not setting foot on the surface, but they are being trained into this. And a lot of that is to institutionalize the geology and the science into NASA and our colleague institutions, is to make sure that everybody understands that science is riding on this. It's not driving it, but it's certainly riding on this. So Artemis 2 is receiving geology training right now. The Artemis 3 crew, once they're assigned, they will also receive training, and that training is going to be very specific to, right now we have 13 candidate landing sites in the lunar South Pole, plus or minus. Those are likely to get down selected. Within those regions, you have effectively a 2-kilometer radius landing location. And so there has to be down selection that goes along with that. The down selection will be contingent upon the orbital dynamics that happen around launch. We will likely not have one site when we do launch. We will have to down select en route, but we will target multiple places. And I say that about trying to analyze the surface and creating maps and all the different products that go into it, because the crew will need to be trained in those products and where they're going to go. A lot of the training that we do for these jet tests, for example, is when we're operating out the field, the crew undergoes, because their time is so dedicated to lots of different things, they don't have a lot of time to spend ramping up to the test. The test is really for the scientists and the engineers and everybody else around it. But when we get assigned crew and we know where we're going, or at least we have an idea between 3 or 4 or 5 locations, they will actively be training, and we will be prepping them on the products that they'll be using, on the tools that they will have, which are under development right now, on the communication scenarios, on how to call out the geologic observations. All those things will be very specifically trained. And so we are on the hook for helping our NASA colleagues understand what that means and the timing of that. But I think that we're up to the challenge, and so we will be there and available for whenever everything is scheduled out.
So that's really busy time ahead of you. So, well, we still have some few minutes, but actually we will have to wrap up our discussion. So it's like, okay, we talk about Artemis, we talk about different components, different parts of the missions, and so on. But the lunar exploration itself, it has also some additional missions, I guess, that are still trying to get to the moon apart from Artemis, and then trying to work on the moon and to study it. Anything that comes to your mind you would like to comment in addition to Artemis? Ongoing, or any tries? We have countered, already several tries recently.
Well, If I may, from a technological point of view, there are many enabling technologies that need to be validated on the moon. For sure, we focus on the crew until now, but we need to provide the crew with the needed resources. To mention one, communication was already mentioned, very important, but super essential power provision, also for the resources that Gordon was mentioning before. Very likely photovoltaic won't be enough, so we will have to try and use nuclear power for sure. Radiation protection. Regolith was mentioned before by Gordon as to the benefit of in situ resource utilization, yes, to produce water, yes, oxygen, yes, but also to provide radiation protection. So regolith to cover the habitat, how can I say, the place where people will be living and working. So transportation capability. Today we are host of the European Rover Challenge. Mobility, rovers, essential element to provide the crew with the capability to move around, both for science and for geological interest. So there are many key elements that we will have to test in parallel to demonstrating the capability to land people back again on the lunar surface. Many others. A very complicated infrastructure will be needed to allow people to operate on our satellite.
So,
sorry, Gordon.
No worries.
Back to you.
I just wanted to talk about, So our vision is first terrestrial and then celestial. So that is why, since the inception of Offworld, we've developed industrial mining robots for tier 1 mining companies around the world to reduce the risks, improve the profitability of mining activities here on Earth. And our robotic platform enables our partners to identify resources, precondition the ore, precision mine the ore, and most importantly, take the humans out of harm's way. But now Offworld Europe, with the support of Luxembourg Space Agency, has been tasked to leverage the capabilities of this robotic platform, lunarize the technology, and develop resource processing technologies to capture the full ISRU value chain on the moon. And we are developing a cadence of missions with a targeted timeline enabled by heavy launch and landing systems that are currently developed. And starting in as early as 2027, we plan to initiate the first demonstration missions, which will showcase the extraction and utilization of lunar ice resources in the PS Artemis, challenging environments of the solar system. Of course, but this will serve as a proof of concept for ISRU. And as we progress, our goal is not only to develop these lunar resources, but to provide lunar settlement services, which includes production of human consumables, generation of propellant for spacecrafts, which of course holds the potential to enable long-term, sustainable lunar exploration and support of future deep space missions, unleashing the true potential and predestination of humanity in space.
Thank you. So do we have any questions from the audience? Oh, apologize.
So, of course, it's excited that we are sending humans into the space, but we should not skip the topic about the machines, because actually we are sending a lot of machinery, devices, robotics, and I think the topic about maintenance and preventing maintenance in space is very important. That's why we should supply this technology and test this here on Earth and send to space, because it will be very costly if we will have some problems with the device or robotics out on the lunar surface. So I think this is one of the crucial things in terms of sending, the machinery and robotics into space.
That sounds really challenging. So, yeah. Any questions from the audience? Yeah, we have. Could I ask someone to bring the micro? Okay, I can give you mine.
Good afternoon. I would like to ask you about the idea that I've heard of to make the moon a large launch station. And do you view it more as a concept or a project that we should start?
Well, if you think about the mission to Mars, the spacecraft should be big because you need to travel many, many months. So perhaps it's impossible, or at least impractical, to launch such a spacecraft in one piece. You could construct it on the orbit. Likewise, we have constructed the International Space Station. But if you want to construct it at the Earth orbit, why not to construct it at the Moon orbit? Because then the gravity is much lower, and then you can easier, using less fuel, less energy, continue to Mars. So maybe not the surface of the moon, but the orbit of the moon could be a next spaceport, if you like.
If I may add to this, I agree with Grzegorz that because of the lower gravity, it's easier to launch from the moon or from the orbit, and also from another physics point of view, it's about lower escape velocity. Then we are making this less. We use less fuel, so that's why it's easier to launch from Luna.
So maybe one more quick question, if anyone would be in. Oh, Artemis. Artemis about Artemis, right?
I've heard this argument, there's less gravity on the moon, so we launch from the moon. But that means that I first have to bring the whole infrastructure to the moon, and then I have to, pump gas there, whatever kind of, fuel I'm going to use, whether it's, I don't know, liquid oxygen, liquid hydrogen, it doesn't matter. But I have to bring it there, especially since liquid oxygen and liquid hydrogen actually bleed off in space. So it's not something that I can get there and just wait 3 years until I use it. So the idea that I can launch from the moon is a bit like my car is broken and now I'm going to repair it, not in Kielce, but in Paris. I mean, it's possible, of course, but it will take a lot of, trouble to do this. And I understand that, there is perhaps, moments that the fact that the moon has lesser gravity will help us in some way. But the idea that we can, build everything and then launch it from there, it's not really very practical. Also, if I want to add something, it's easier to do it, close to Earth.
I totally agree with
I can challenge the point if... Again.
Really, Artemis, I expected that comment from you. Maybe in the future, but I don't see it realistic to consider the moon as a sort of spaceport. First, we need to learn how to live and work there, and that will require time, for sure.
Yeah, we actually figured out what's the threshold of the performance of ISRU systems for them to be a commercial viable alternative to bringing stuff from Earth instead of producing them in situ. And it's basically 35 times the mass that of the systems that we sent to the moon to perform those activities. So in the operational lifetime of such ISRU systems, if we can produce more than 35 times the mass of the system that we send, it's already commercial and it's already viable. And it's not that tremendous technology difference that we need to combat because basically open pit mining can already establish that, at least for the ice resources on the moon. The moon can be an antroport because in order to launch a rocket launch payload from Earth, we need a rocket that has fuel of more than 90% of its mass. It's just fuel, just to reach the orbit. On the moon, it's just 50% of that. So it's a tremendous advantage, and with that, we can have an enormous growth that hasn't been even thought about, that hasn't been established just yet. But it can induce a number of businesses, a number of opportunities, a number of exploration missions that we haven't even thought about. I think we've already established that absolutely, even with Starship, which can lower the cost of transportation to the moon by multiple factors. We can still be profitable, we can still be viable with the exploration development of lunar resources.
I think, well, I cannot say no to that question, I guess. So the very last.
Thank you. Yeah, I agree with Artemis. Before you can launch from the moon, you have to get to the moon. And there's no advantage whatsoever if you want to go to Mars to go to the moon or to lunar orbit. The delta V to go from low Earth orbit to low lunar orbit is 4.2 kilometers a second. The delta V to go from low Earth orbit to Mars on a 6-month transit is 4.2 kilometers a second. So even if propellant was available for free, if you were to stop by lunar orbit on your way to Mars, it would not pay to go there to get it, to say nothing of going to the surface of the moon. However, if you want to go to the moon, then lunar propellant is very useful. ISRU pays off tremendously if you use it at the point of departure. If you try to move propellant around from somewhere else than where it's made, you very quickly run into negative problems. But for lunar ascent, okay, they're using Starship for an ascent vehicle on the moon. It will take 100 tons of oxygen to get Starship from the surface of the moon up to the gateway, okay, which is the same weight as the Starship. So if you could make that 100 tons of oxygen on the surface of the moon instead of transporting it to the moon, you would actually cut the number of Starship launches to do a lunar mission in half, okay, in half, okay. So lunar oxygen is great for lunar ascent. For Mars missions, you want Mars ISRU to pay for Mars, to support Mars ascent. That's it. But if you want to go to Mars, you need to go to Mars.
Well, thank you for that comment.
If we are considering using ISRU technology to extract hydrogen and oxygen from either the icy water or the craters or from the water, I think the amount of energy which is needed to extract it in order to generate the amounts of fuel you would need, we first have to solve the problem of power generation. And that will not be achieved by little IHUs or RTGs or solar cells. For that, we need to solve the problem of fission technology, which is another leap we have to do before we can think about producing propellants on the surface.
Yeah, but we had nuclear power before we had color television. So nuclear power is something that we can do.
Thank you very much. Well, that really leads us to the point of discussion, literally, so which is always a good point, right? So unfortunately, our time is over. So thank you. Thank you to your guests and our guests online for a very fruitful discussion, for joining us here. And thank you all for a very positive, also like interaction with us. And yeah. And for those of you who are watching us live, we can get back to the Mars Yard, where Remco will show you what's going on around right there. And for those of you who are here, I invite you for a debate about space education that will be held in Polish after 5 minutes technical break. Thank you very much.
shall go to Mars.
We should go to Mars.
Because it's human nature to keep exploring.
Because we want to discover intelligent life in our solar system.
Because establishing a presence out there is a huge stepping stone to limitless possibilities.
Because we can.
Because our ambitions exceed this world.
Because humanity has unlimited curiosity and is destined to conquer the universe for good.
We should go to Mars because it's been long enough.
Because it helps to develop new technologies that are also very useful on Earth.
Because look at Mars could improve the way we look at our Earth.
Because Mars exploration is a huge milestone to extend our vision and discover a new home.
To play sports in low gravity.
And to define past, present and future of our planet.
It opens doors of opportunities for developing talents like us who wish to explore newer horizons and decide for the unimaginable. We should go to Mars because the sky is no longer the limit.
Space industry is booming all over Europe. And so whether you're Luxembourg or Portugal or Spain or Italy, whether you're big or small, you try to be part of this.
I cannot imagine a better way of preparing people for our future projects than, competitions like this.
And all these jobs are there to be had. So if you're studying something that you think has nothing to do with space, check again. You might find out that 10 years from now, you're actually needed.
Great engineers and great scientists building great products. That is what the space industry consists of.
There's something deeply philosophical about space.
And we are the first generation where Mars is just about to be at the reach of our hands. It's a logical continuation of feeding and nourishing that nomadic gene that is within us as humans.
The most important and fundamental part of being human is imagination, this aspiration that we have, which drives us to explore space. So this is something to be proud of, this is something to celebrate.
The cooperation is obviously not just between governments, but it's between the private sector, academics, non-governmental organizations, even students that are combining math and science studies with imagination and creativity.
One person can make a difference and therefore should. That's my assignment to you.
And welcome back to the outside world here at the European Rover Challenge 2023. We are back here on the Mars Yard, where, as you can see, the competition is still going on. We're in the second day of the competition. Tomorrow will be the final day and the award ceremony. So I hope you'll stay tuned to the live stream, which will continue until approximately 4:45, 5 o'clock today, and we'll start again at 10 o'clock tomorrow morning. In the meantime, follow everything on your favorite social media channel under hashtag ERC2023. We're continuing here with a few very special guests. So you've seen several guests in the auditorium with Milena before the break, and we'll continue the conversation with some of these guests and some new guests here outside in the brilliant sunshine here in Kielce on the Mars Yard. My name is Remco Timmermans, and I will be the host of the outside part of the live stream today and tomorrow. And right now with me here, I have Professor Alessandro Golkar of the Technical University of Munich in Germany, who is a specialist in a lot of the technology that we're seeing here, but also a lot of the technology that is used now to bring technology into space and to develop much of this technology. There's a lot of things that you are doing, Professor Golkar, that I think are worthwhile talking about. Now, previously we talked about, well, the theme of the day today is Artemis and going back to the moon. But we also talk a lot about the new space economy, the new commercial space, new space, commercial space, and you play a role in there. So first of all, tell us a little bit about what this new space economy is.
Sure. Well, essentially, new space economy is, this new cycle of activities, which is mostly driven by private entities which are funded by private capital, okay, which are experimenting with new technology. Now, this is not, the term new sometimes is misappropriated because this is essentially what Boeing and, Lockheed did at the beginning, right? So there were startups. So all companies were startups at their time, and this is the new generation. And something new is happening in terms of approach, product, technology, as well as financing.
So still we talk about the new space economy because it's offering new opportunities. In the last, say, 5, 10, 15 years, depending on the definition, we've seen this upcoming of commercial space,
sure,
which also indicates a move away from traditional players, from government-led players to more commercially-led players. What's the significance of that?
I would say it's more of a complement, okay? So there's always, let's say, a part of institutional business that also the new space companies go after, right? But there's also the attempt to reach new markets, right? So to make space relevant for Earth, for society. So for example, using space data for quote-unquote terrestrial purposes. This is really the attempt, right? So this is what all these new companies are trying to do across the whole value chain, so from upstream to downstream.
I see. Now, one of the developments that's playing an important role is miniaturization, and you are involved in projects involving nanosats. Yep. Can you explain to us what that is?
Sure. So essentially, over the years, technology evolves, right? And one of the let's say steps of technology is the miniaturization. So being able to pack more capacity, in a certain space. So if you look at CubeSats, right? This is the standard of cube is 10 centimeter, 10 centimeter, 10 centimeter, which you can stack and modularize. This started, I think at least 2 decades ago, even a bit more. And it was at the beginning just seen as a tool for universities, for learning, right? And today, 25 years later, it's actually, a very important platform for industry and for enabling applications which are critical, right? As in communication, as in Earth observation, and as well maybe in the future in navigation. Now, do they substitute, existing platforms? They can't. Right, because there are physical limitations, but definitely with with this new miniaturized technology, which we also see in rovers, by the way, we can do many interesting things.
Okay, you mentioned rovers. Of course, this whole event is about rovers. Sure. How does this miniaturization of technology impact the design of rovers, and how can students benefit from it in competitions like these?
Well, you see, in a rover system, like in some satellites, but more in the robotics side, you have perception, right? So you need to be able to ingest data in order to, train and, use your algorithms for navigation, right? And this data can be quite massive, right? So there are some instruments which require significant computational ability, and embedded hardware has done, huge giant leaps to enable that. So today we can have machine learning on board. We can have complex capability, which even 15 years ago was not even possible or very expensive. So students have an opportunity now to use technology that some time ago was only pure domain of bigger companies, and now it's available at least on the processing power side. Then, of course, there is all the the radiation hardening, all the things that make them available for space, but it's another story, right? But in competitions like this one, people can use very capable technology to develop, for example, autonomous navigation for these rovers. That's very exciting.
That is very exciting. Now, where will this go? How will this continue into the the next edition of the European Rover Challenge, or the next
Sure.
editions, I should say,
So-
in the next 5 years?
Ask my bet, for example, I would say we will see faster and faster rovers, right? So if you see the rovers of today, they're quote unquote slow, right? Even the operational rovers are slow for a good reason, right? Because they need to have time to identify obstacles, to plan, and so on. I think in the future we're going to see more and more ability, more dexterity, being able to handle more terrains, being able to be more confident, right?
I see, I see. Now there's another aspect of competitions. Actually, you were part of a competition as part of your CV. You won the 2017 Copernicus Masters.
That's right.
Now that's a whole different type of competition than this year. Can you tell us a little bit about how that helped your career?
Sure. Well, actually, that was a great opportunity. That was together with Professor Adriano Camps at the Universitat Politècnica de Catalunya in Spain. And basically, what Adriano and I did proposed there, kind of, our jewels, right? So what we had, the most valuable we had, we put it together to create a new concept. And that one, if I'm not mistaken, was the first Earth observation CubeSat that was financed by the ESA Earth Observation Department at the time. It was a great experience. It was very challenging because developing a satellite in 12 months, it's very, very challenging, especially when you have many instruments, many players to coordinate. And definitely was pivotal for my career. I think for Professor Camps as well was a great experience. And for all the students involved, so all the activities that were around the platforms.
Excellent. Actually, we have the UPC performing here with the Rover team.
Yeah.
So they're involved in many aspects of space, as are many universities here. You've also been instrumental in developing technology called concurrent design and concurrent engineering.
Yeah.
Can you tell us a little bit about what that is and how that can help teams that are building rovers for competitions like
Sure.
this?
Concurrent design has been around for some time already. And depending on the domain, it has different meanings. Okay, if you look at the aeronautical domain, they typically mean designing the aircraft together with the industrial system. Okay, if you look at the space domain, usually what it's meant, it's a help to help converge a design which has to coordinate multiple subsystems together. Right. So, for example, in ESTEC, in the European Space Agency, they have a CDF, concurrent design facility, which job is exactly to do this. Okay, so to come up with a coherent baseline for the satellite platform. The one that actually, this is a methodology that you can use essentially to coordinate the work of engineers in an efficient way. And basically designing systems using engineering models. These models can be applied to engineering systems, to system of systems, so when you're having multiple things working together, or as in the case of what I was doing some years ago at Airbus, was about coordinating studies informing technology roadmaps. So even for the technology management side, this approach can be helpful.
I see, very interesting. So that's how engineering processes can help not just technical innovation, but also, well, as you say, roadmaps, technology
that is
roadmaps
right.
into the future. Well, thank you very much, Professor Golka, for your insights and for being here and for your support in the European Rover Challenge. And I'm looking forward to seeing more of your work and your continued support for the ERC.
Right. Thank you so much. And
thank you very much for being here.
Good luck to all the teams here.
Thank you very much. We move over to our next guest. And our next guest, for those of you who've watched the live stream before, will be a familiar face. We have Mr. Nico Detman here. Let me put my paperwork away. Who is, in a very long title, as is usual in the European Space Agency, the ESA Group Leader for Lunar Exploration Development Projects in the Directorate of Human and Robotic Exploration. Did I say that correctly?
Well, it has changed in the meantime, obviously, because we are changing a lot. It's now called Lunar Transportation Group.
Okay, that sounds a lot shorter anyway. Well, thank you for joining us here on Mars in Poland. We saw you, of course, in the panel before, and there's one thing that struck me that you said in the panel discussion that actually aligns with one of the questions that I prepared. You said there is no crewed mission to the moon without ESA.
That's true.
Can you elaborate on that, please?
Well, part of the Orion is a service module, and the service module is, we are the prime contractor. We have been selected by NASA proudly, probably because we have shown our expertise and our reliability through the ATV program. There is a lot of lessons learned from the ATV in the service module. And so we are developing it since 2011. We had our successful, almost flawless maiden flight last year, and We have another 5 service modules already in production, and we are currently negotiating a batch for another 3.
Wow, that's amazing. The question that I had prepared in that same line is, the world tends to look still at the United States, at NASA and now SpaceX, but also China and since recently India as leaders in lunar exploration, and maybe still less so to Europe. But what is the role that ESA plays in this new space race, if you like it?
Well, we don't consider being part of a space race. We are trying to do the best with the taxpayer money we get. And at the last ministerial conference, we have got approval from our member states to develop our own lander, which is called the Argonaut. The Argonaut will be a cargo lander, so it will not be manned. As I have mentioned earlier, the first launch is planned in the year 2031. And it is a lander which can be used autonomously as a European mission, but also in cooperation and therefore contributing to the lunar architecture which is planned in the Artemis program.
Okay, because as part of that lunar architecture at an IAC last year or the year before, we saw a habitat popping up. Is that part of the program as well?
Well, the habitat is also part of the Artemis program. It's actually called the IHAB,
yes.
And it's one of the elements which shall be launched in 2028 to the Lunar Gateway.
Excellent. Well, that was an amazing thing to see. That
Well, it's only one of the 2 elements we're delivering, because there is another element called the Esprit refueling module. It's partially a habitat that actually has windows, a bit like the cupola of the ISS, but it's mainly used to fill the propulsion element with bipropellant and with the xenon, which is needed for the electric propulsion.
Okay, okay. Now, let's move back to what we're doing here at the competition. We see a lot of robotic technology, and as you are involved in robotic and human exploration, robotic technology is increasingly getting better. We see it even in the teams here that are using technology that even 5 years ago was the domain of space agencies. We see a rapid increase on the use of artificial intelligence, again here in the software that these rovers use. So not only do robots now have better arms, not legs, but arms is the theme here, but soon they will also have better brains than humans. Why do we need people in space at all?
Because nobody is as handy as a human being. You cannot react that fast as a robot, and you cannot anticipate maybe things as good as a human. You probably can take less good commands from the ground. I think robots will be a tremendous help, and they will ease operations, but they will never be fully capable to replace the humans.
It's interesting because in the interview before, Professor Golkar said that very soon these rovers are extremely slow. We see it right behind me. They will be much faster in 5 to 10 years from now. So fast that they might even be faster than humans. Is that statement that you make now still valid in 10 years?
Well, a car is also faster than a human. I wouldn't say a car is can be compared with a human. Speed is not everything, but cleverness and smartness, and that's what counts.
Okay. Well, I have faith. I'm a human. I don't want to be replaced by a robot, so I'm fully in agreement with what you're saying. Robots and humans will work together on the moon. Now, you're in charge of the development of both these developments for ESA. What are the key elements that ESA is currently developing to make this happen in the next decade?
So our current contributions to the Artemis program is, as I said, this lunar lander, but we are also contributing with providing this moonlight, 3 satellites which are supposed to orbit around the moon to help all systems to communicate and to navigate better. And this is all these elements I just mentioned, the Orion, the Gateway, the lander. All these are what is called the foundational Moon to Mars segment. And what's coming afterwards in the second phase, that will be to be defined in what is called the lunar architecture concept, which is not yet finalized. Mm-hmm. And then the contributing agencies will decide what will be their contributions. That's not yet decided.
I see. Now you talk about the contributing agencies. Today we talk about the Artemis Accords. Of course, the Artemis Accords are bilateral agreements between countries. ESA is not a country, ESA is an agency. What is the role that ESA plays in the Artemis infrastructure?
Well, as you correctly said, the Artemis Accords are signed on governmental level and not on agency level. So we work on programmatic agreements. We have MOUs and implementing arrangements.
Because not all ESA member states
level.
are signatories, are they?
That's true. That's true. But only those who are member state of ESA can contribute at least to an ESA cooperation with NASA. The other important partners in the Artemis program are obviously our Canadian colleagues and the JAXA colleagues with significant contributions, and yeah, we're going ahead.
Very good. Now, what's the role of the new, because we interviewed the new Polish ESA astronaut this morning, he was with us here. What is the role of the new class of ESA astronauts in all this?
Well, as you know, their missions are decided at a much later stage. I mean, for the Polish astronauts, the mission is, let's say, identified. It's not yet formalized, but it's identified. But for the selected class, the missions are not yet selected. Probably the first mission will still go to ISS.
Right, but the big question is in all the world, as you're very well aware, will the first European on the moon be part of that class?
First of all, we have agreed so far with NASA that we have bought through our contributions to the Gateway program 3 astronauts flight to the Gateway and not to lunar surface. I think the idea is here that through our services with this lunar lander, providing logistics services, we create the possibility to barter elements for a European flight to lunar surface, but that's far off from today.
To be decided.
Yeah.
Now, there's lots of people watching who look at this new astronaut class thinking, I really want to be part of that. Will there be a new astronaut class anytime in the next 5-10 years?
I would be surprised if not, but I couldn't give you the date.
Of course. Well, that's what people are hoping for, I guess, that that will be very soon, announced very soon. But the hope is there at least. So, well, I thank you very much for your contribution here. Thank you very much for being here, for supporting the European Rover Challenge, and I'm looking forward to seeing Europe on the moon very soon.
Thank you.
Thank you. Then we move on to our next guest. Anna Krzyżanowska works at the Danish Technological Institute. Now, you have a background in wearable technology and in digital health systems for people.
And also electronics.
And electronics, yes. Now, however, you are developing spacesuits for robots and even smart skin for robot arms. Will robots replace humans in space soon?
Not necessarily replace, but in some of the conditions it's better and more cost efficient to send robots instead of human beings. Because as we know, we are dealing with a very hazardous environment in space. So in terms of preventing some of the damage to people, we will be sending more robots for some of the missions that does not necessarily require human being presence.
So you're developing smart skin, as it's called, for robot arms. Why do robots need a skin when there's nothing in space?
Yeah, that's a good point, actually. When we think about skin, we think about something that is very thin, like our human skin. It's extremely thin tissue. So what is very important in space? It's weight. And we call this smart skin for collaboration robots, cobots, because we will develop ultra-thin skin with sensors in order to prevent damage and in order to help with heat transmission and dust protection. And why skin? It's because in this project we are combining 3 different technologies, like 3D printing, printed electronics, which is based from nanotechnology, and robotics, because we are doing this for robotic arm. So it's a great example how 3 technologies combined together can bring amazing solution.
So what will this skin do? What will the skin protect the robots from? Because I said space is empty, but it doesn't mean there's no dangers or no risks in space. What should I be thinking about?
So this skin will not only protect the robots, but also human being that needs to operate in space with robots. So in order to deliver instant feedback for the people operating the robots or for the machine, we will need to supply the skin with different sensors like strain sensors, force sensors, and shock absorption sensors, also temperature and so on. So in this case, we will prevent the damage. And as we all know, maintenance in space can be dangerous for astronauts and as well very, very expensive.
Now, we talked earlier today about solar sails and the risk of micrometeorites. When a robot has a skin and it's hit by a micrometeorite, should I be thinking about self-healing type of technology as we see in Star Trek?
I think this is far away in the development plans because we don't consider self-healing smart skin, but part of this project is to actually support these robotic arms with something that can absorb these micrometeorites and so on. So that's one of the purposes. Of course, as you mentioned before, self-healing, it's maybe not the stage of the art because this is very low TRL, but maybe in the future.
Okay, now you're developing these spacesuits for robots and smart skin for robots. How would this apply to human missions? Because humans are much more vulnerable in space than robots are. Does this have applications for, say, human spacesuits as well?
It does not have, but we are making different solutions for human beings. So as you mentioned at the beginning, I also work with wearables, so printed sensors that you can put in the clothes, for example, which already has practical application in digital health. So some of the projects that we experienced before and that we can deliver, it's about making printed sensors for astronauts. For example, as we all know, astronauts in space, they have some problems with their muscles, for example, because of the environment. So by delivering printed sensors that will be attached to in their socks or in their clothes, we can detect what's going on with the muscles of astronauts. Besides this, we can also, and it's lightweight, this is the main advantage. And we can also check their heart status by EKG sensor, also detect what's going on with their brain by EEG sensor. So there are several things that we can use our technology in space.
Okay, now we can use the technology in space. We can also use the technology for all of us.
For all of us.
And maybe the viewers think, okay, there's been a handful of people in space, but there's 8 billion of us on Earth. How could this technology help us? Because most of us don't have experience with putting electronics in my shirt and in my socks.
No, I always tend to say that why space technology and space development is important for us. Because what we do in space, we always bring down to Earth, like microwave and GPS and many other examples. So this is one of these examples. So that's why we should support space technology. Already now, different companies, health companies, and also medical institutions like hospital, doctors, they are working in collaboration with scientists to bring this technology back to us on Earth. Because as we faced, not that long time ago, corona pandemic, before we invented vaccination, medical personnel was very exposed to, being sick because of the straight contact with the patients.
Yes.
And in order to prevent this, we are trying to implement remote health control. So by using nanosensors, wearables, and so on, we will be able to be treated at our houses. Because we are also facing that we will have aging society. And that's why we are risking that our hospitals and medical staff will be overloaded. And therefore, we need to come with some technologies that will help with this. So as our viewers may see, this is maybe beginning, but we can observe in the next few years, it will be more and more present.
Okay, excellent to hear. Now, let's go back to the competition here. These teams here are all developing very high-tech robots. How could they benefit, maybe in a few years, from the technology that you're developing for robots in space?
Yeah, as I already noticed that they have some problems by encounter some of the rocks and so on. Maybe they need to use smart skin because they will have some extra shock absorption layer, and then they will be informed upfront what is in front of the vehicle and so on. So I think definitely, especially for this kind of robots, it's something that they can use in the future.
Is this technology available now, or does it need to go through?
It's in the requirement stage, but it's a plan that it will be, because we already talked with different stakeholders, that it will be available soon. So I'm looking forward for this student to be able to use our technology.
And what we do see here, which is exciting, is that when there is new technology, like the big upcoming of AI over the last year, we see that applied by these teams very, very quickly. So as soon as it will be available, I'm sure they will pick that up, and especially since they will all be watching the replay of this live stream,
and I think
they can come to you for advice, perhaps.
Exactly, and I think what is beautiful about technology that it shouldn't be only in the lab. It should be brought to the people, that they can use it. That will help society and help developers to make their ideas better.
And it's interesting that you say that, because this is sort of a lab, but it's also not. This is kind of in between, because the competitions are real. I mean, they all want to win the big prize here. But it's also a lab. You see many of these systems failing and many systems succeeding here in the harsh reality of this Mars yard. That might also be interesting for organizations such as yours, for institutes such as yours, to bring that technology actively to competitors here and test it out here on the Mars yard. Is that something you would consider?
Yeah, I think so, definitely. We should, because as I say, combined technologies can create bigger, results. So I think this is a great opportunity for me to seek for new technologies and maybe some collaboration and so on. And as you mentioned, they failure and so on. Failure is never a failure. It's a good sign because we are testing before the real mission.
Yeah, well, and that's exactly it. Failure is a good thing because failure is the way we learn. So,
it's a lesson.
Good. It's also a good call out to whoever is watching that has technology that would be relevant for these teams to win the awards. This is a great lab for you to test out your technology here on the Mars yard. So again, a call to sponsors, supporters, technology supporters for the teams here. We have 25 on-site teams, 15 remote teams, 40 teams that provide opportunities for you to test new technology, to test software, to test hardware, to test technology like you are describing here, Anna, that will help robotics developments in the future. So thank you very much for your insights and for these interesting developments. And thank you for being here and for supporting the European Rover Challenge.
Thank you very much.
2023. Thank you, Anna. We will now move to one or two commercials, and after that we will move to the exhibitor zone to show you what's going on here at the exhibitor zone in Kielce in Poland. We'll be back in a few minutes. Okay, we are back here in the exhibitor zone, and we went behind the scene a little bit to talk to Professor Germán Sarmiento, the president of the Mars Society of Colombia, also a member of the European Space Foundation, one of the organizers of the European Rover Challenge here. Now, Professor Sarmiento is a specialist in food in space. And we have had a discussion, interestingly, yesterday with someone who works on freeze-drying processes to bring food into space. Now, freeze-drying is great, but you still have to take food from Earth into space. The technology that you're developing is different. Is that correct?
Es correcto. Uno de los trabajos que venimos haciendo en el capítulo de Colombia con The Mars Society y con el European Space Foundation es el trabajo de la creación de comida y bebida para futuros astronautas.
So one of the things that the Mars Society in Colombia, together with the European Space Foundation, is developing is methods to produce food and drink in space for human consumption. Now, this is based on algae, I understand.
Ok. Nosotros lo que buscamos con este trabajo es que no solamente los rovers sean un trabajo que se hacen a nivel de investigación, sino que también nosotros podamos mostrar cómo se pueden desarrollar otro tipo de tecnologías para el mundo y en este caso no solamente para la Tierra, sino para temas espaciales, en este caso el Marte, la Luna y todos estos nuevos programas que se están trabajando.
Okay, so the technology that's being developed is valuable here on Earth, but also works in space environments like the Moon and Mars. Y usted lo puede demostrar lo que significa, ¿no?
Claro, claro.
So we're going to see a little demonstration.
Ok, en este caso tenemos un fotobioreactor que lo que hace es producir comida y oxígeno para astronautas. En este caso, este equipo, que es un equipo portátil, lo que busca es que a través de la clorela máxima, es una microalga que estamos trabajando desde hace 10 años, lo que buscamos es que poder controlar y generar algo que se conoce como la biomasa. Esta biomasa lo que va a permitir es que los astronautas puedan sobrevivir por una semana con este equipo en específico.
Okay. If I can translate this, because not all our viewers are fluent in Spanish, we have here a photobioreactor based on algae that is producing food and oxygen for astronauts living on the Moon or on Mars. And with this unit alone, if I understand correctly, an astronaut can survive for an entire week.
Lo que buscamos a través del bioreactor es que sea un equipo totalmente portable que le permita al astronauta poder alimentarse. En este caso, la microalga, la clorera vulgaris, lo que va a permitir es que como tiene harto
here, the reactor, the photobioreactor here, produces enough. And this unit has been used in testing on Earth in different environments, like volcanic environments, on mountains, in expeditions all around the world, and is ready to be applied to space. But this is still a test model. So I would like to thank you very much for demonstrating this. Another use of producing space of producing food in space for the next steps of humanity in space. So thank you very much, Germán, for showing this and for bringing us this. And with that, we would like to move on to the next one. Hang on, I didn't hear that. Okay, can we look at the drone? Okay, very good. We are moving on to the next exhibitor now, so I'm going to follow my assistants. Thank you very much, Germán. Muchas gracias.
Gracias, Renko.
Y bueno, mucha suerte con este proyecto. Es muy interesante.
Gracias,
Muchas gracias. Okay, and we move on to another area here on the Inspiration Zone, and I'm following my colleagues here. And we're going to visit another one of these exhibitors here, if we can find our way through all the children and all the people who are here. We lost connection. Do I use this microphone or better that one? Can speak something. And we are back. We had a few technical issues because there's so much technology around us that we lost the connection. So sorry about that, but we are back here in the Inspiration Zone with some of the exhibitors. And there's one thing that I'd like to start with to show, and that is this here. If we can start with this, because you must be extremely proud of this. This is the award that all the teams are looking for tomorrow. So can you introduce yourself? Who are we talking to here?
My name is Robert and this is Patricia, and we are from AGH Space Systems. We are a student organization and we are building Martian rovers, but also rockets and stratospheric balloons. Of course, today we are presenting our rover, Kalman, which is trying to, protect this first place from last year. And we, of course, are very proud about this, first place from last year, but we feel also pressure, Yes, it's really extreme.
I can imagine, and the pressure is the same for all the teams here, I presume. But tell us a little bit about the technology that you're presenting here. I see rover wheels, I see half rover wheels. What is so special about the things that we're looking at here?
Of course, we can start with our wheels. These are really wheels from our rover Kalman. They are 3D printed, how you can see. They are examples, of course, of wheels we are using same right now. Actually, we can see different types of structures which we used across many years. First, we started with structure of honeycomb. First, of course, our first tries with this type of 3D printed wheels. Of course, this type of structure is well known because, for example, bees are using this type of structures to build their homes. Later, we figure out other types, like here you can see more complicated, really mathematical complicated structures. They are much more stronger than this one which we used previous.
Okay, now normally people look at 3D printed objects as very hard plastic. This is very soft. Yes, so you're 3D printing sort of a rubber compound?
Especially it's PTU, it's type of elastic plastic.
Okay. Okay, very good. Now, you also talked about you do rover projects.
And rocket, yes.
But what's this here?
Right here. It's our rocket Carbonara. Carbonara is very, very old rocket. We have this rocket for many years. It was flying, I think, more than 10 times. We are actually not counting right now. It was, so many of this. This rocket actually is one of our smallest rockets. We use this to test electronic components and other parts for our bigger projects. This rocket is smaller. It flies usually for 1 or 2 kilometers. So we can start with testing these all components, and later we can use these components to build our bigger projects. Like right now, actually this year we've built our rocket 3TTK, which flight during Spaceport America Cup in United States in May this year, and we were flying on 4.5 kilometers. And yes, it was actually our highest altitude ever.
4.5 kilometers with a small rocket like this.
With much more bigger. This project, which was flying in United States, it's 5 meters tall. So it's really, really hard to take this rocket with us.
But it's very cool that students are working on projects like these rockets and on these rovers. Is it the same team at AGH that is working on both rockets and rovers?
We are one big team interested generally in space technologies, but inside we are mostly divided into separate projects. Of course, after many, many years, our projects are really complicated. And for example, in rover works something around 30-40 people, same with rockets, so we need specialized teams, specialized in mechanical engineering, in, for example, electronics, in software. There are some small groups of people which are working really hard for many months to prepare for competition like this. So, of course, they must be focused on one project. But many people are working in both teams, and we are always open to share experience to help each other. For example, yes, some parts of Martian rover Kalman is made with some materials in help of members of the rocket team.
Okay, so students have the choice, they can work on everything. This is not part of the standard curriculum of the university, is it?
Actually, yes, we are part of university, but mostly we work on our own. We have our own ideas, which we are developing, and of course, university is helping us with everything, with financing, for example, with providing us with materials, with space for constructing our rockets, which are more than 5 meters long, so we need a lot of space.
But it's your own time that you're putting in this.
Yes, and our own time, of course. But it's worth working on this, because after years of making our projects in, now in university, but later you use this knowledge in real work. You can find a job in space projects or other projects in some other industries.
Well, and that's the cool thing. And may I ask you a question as well? Because you have a booth here, you not just have a team on the Mars Yard, you also have a big stand here. What are you trying to achieve? What is the reason that you also have this display here?
We really want to show people what our team is doing, and we have a special section of marketing who want to show all of our achievements, and we are going on organizations like this and events like this to talk with people, and yeah.
Okay, marketing, as you say, is important. Now, I'm a marketeer as well. This is very important because we really want to show the next generation of the space workforce what is happening. So, how is marketing integrated in the AGA Space Systems group?
It's integrated with all the sections with Rover and with the rocket section, and we are helping them to, for example, get money for our projects, and to show all of our achievements on the social media, and mostly that's how we work.
Okay, now you mentioned social media. How can people find AGH Space Systems online, on the internet, on social media?
Yeah, you can check us on every social media, like Instagram, Facebook, LinkedIn, or Twitter, and you just have to write an AGH Space Systems.
Okay, so Google AGH Space Systems, find it on social media, find it online, and see what this amazing club from the University of Krakow is doing here on the Mars Yard and here in the Inspiration Zone. So thank you very much for your time, and good luck with the competition.
Thank you very much.
Okay, that's us here at the Inspiration Zone. Are we going back? Yes, okay, we're going back to close off the day, I suppose. So we'll show 1 or 2 videos, and then we'll be back on the Mars Yard. today, and we have 2 more teams to talk to, and we're at the end of the second day of the European Rover Challenge 2023. But before we close the live stream for today and move over to tomorrow, we have more teams. So welcome Team Rover. The Czech team. Can you introduce yourself and your team?
Yeah, thanks. So I'm Robert from the team Rover. We're the only rover team from the Czech Republic. And yeah, I think this is our 5th, perhaps?
5th, maybe 6th. Also.
No, maybe 4th or 5th, I don't know. We've been here a bunch of times, and it's always a pleasure to visit Kielce and the European Rover Challenge. We enjoy the event and also just roving around the Mars. Yeah.
Okay, tell us about roving around the Mars yard. How many people did you bring to rove around the Mars yard?
Yeah, from our team?
Yes.
There were 7.
7 people from your team?
Yeah, just 7. We're a small team.
You are a small team. Is this the whole team?
I think that there's probably like 10 people.
Yeah, there's like 10 in total.
Yeah.
Okay, so tell us a little bit about what the team. Are you from a particular university?
Oh yeah, we're from Technical University of Ostrava, VSB, and from the Faculty of Mechanical Engineering, from Department of Robotics. But not everyone in the team is from the department. Like most of us are, but we have also people from other departments and other faculties, but all of us are from the university. Yeah.
Okay, but tell us a little bit about the interdisciplinary nature of your team. You say most of you are from the engineering department, but some of you are from other departments. Which other departments are important in a rover team?
Yeah, I think I will let my
colleague
speak for a second.
Thank you. Well, unfortunately, we don't have so much variety in our team when it comes to different discipline, when it comes like that. So we are, as my colleague says, we're mostly mechanical engineers. We have one person who is from the IT faculty, and that's unfortunately it. Like we are still looking for someone from this like scientific expertise of geology, for example, which is really important for the competition.
We see several teams who have geologists on board as well, for obvious reasons. Now, tell us a little bit about the technology. Why is Rover going to win this competition?
Well, I would say that we are the most heartwarming in here. We want to discuss with anyone, we want to share the knowledge with everybody who would ask. So just, because of the good spirit.
Okay, good spirit, that's one thing, but good spirit doesn't make the rover perform the best of all rovers. So what specific technology have you implemented in Rover 2023 that will make it stand out from the others?
Well, perhaps the only, I don't know if it's the only thing, but I haven't seen anyone else using any, how to say it, like any. It was kind of like a puppeteering arm that we can just control dynamically, and it controls the robotic arm one-to-one, so we can do the same movement on the operator side, and it does the same movement on the rover side. So it makes the whole thing really intuitive, and I haven't seen anyone else using that.
Okay, well, very cool. I have to stop because we ran out of time, but thank you very much for your time. I'm looking forward to seeing Rover here on the field very soon. And with that, I'm going to close off the live stream for today. Tomorrow we'll be back with you, starting at 10 o'clock, with more guests, with more teams, with more of the exhibition. You can follow everything on social media while we're away under hashtag ERC2023. And of course, make sure to tune into the live stream at roverchallenge.eu from 10 o'clock Central European Time tomorrow. I'm Remco Timmermans, live from Kielce in Poland. I'll see you tomorrow. Bye-bye.
So, can you hear me? Raz. Yes. So welcome back. Sorry for the delay, but the Mars Yard broadcast was still ongoing, and we didn't want your colleague Remco to go away from the Mars Yard. So apologize, Artemis, for this delay, and apologize to all of you. So let me invite on stage Artemis Westenberg from Explore Mars Europe, who will tell us about the crime in space, and I'm looking forward to listen to your talk.
Well, here we start. Crime in space. And I say crimes because I do not believe that it will be only one crime. And, you know, it's a threat to our future, and I will try to explain why it is a threat to our future. Now, like I said, for a long, long time, I thought I had organized everything. You know, not these three guys, but in general, you know, astronauts are being trained, being selected, who will probably go, you know, in the next 10 years, you know, first to the moon and then later to Mars. So, you know, someone else has that worry, and I believe that NASA, ESA, and all the others doing well. But now imagine, this was 1969, these three guys, I take it that everyone knows who these three guys are, right? It's not just on their suits. Armstrong, Collins, Aldrin. So these were the three that were, you know, two of them were going to step on the moon. One of them, Collins, was just, you know, doing circles around the moon and probably praying that everything would be well with his two colleagues, because I do not imagine that, Michael Collins would have been really rejoicing if he would have been the only one coming back. So, okay, they went. Now, what crime would have stopped this step? Even, you know, going already en route to the moon. Now imagine if Michael Collins would have thought, you know, okay, I'm not stupid. Neil Armstrong is the best pilot we have, and it's still iffy, so I'm not going to push him, but I'm going to hurt Buzz Aldrin, so I can, you know, get into his suit, you know, get down to the soil, to the surface of the moon, and walk instead of Aldrin. Impossible? I don't know. They're human beings, and I'm pretty sure that all the guys, because remember, no girls, all the guys who were training to go to the moon and be an astronaut walking, all of them must have hoped to be the ones that would be walking there. And of course, you know, the higher-ups would decide who would be on what mission and with you know, what group of people would mix best. But I bet that Michael Collins would have loved to also walk on the moon. So imagine we're going, and in this suit, although it says Buzz Aldrin, it's actually Michael Collins, because, you know, he has pushed, you know, hurt Buzz Aldrin, which would have been hard in zero gravity. But, you know, if you want, it's probably possible. Would we have said, you know, okay, this is so important, this first mission, this first step on the moon, with this moon race with the Soviet Union, that, you know, you've done a crime, you hurt your fellow astronaut, that's definitely a crime, but you get out of jail card free, because we want to have this mission succeed anyway. You know, it didn't happen, but what if? So where do crimes in space take place? Well, this is a very optimistic picture of a space hotel. And, you know, at the moment, it's the ISS or any other space station. The moon, Mars in the near future. Space hotels when they become realistic. And a rocket or spaceship to wherever, of course, you know, because while you're traveling, you could do something wrong as well. Now, you know, the International Space Station, yes. Deep Space Gateway. By the way, I love this name. Whoever came up with this name, you know, should get a raise in salary. Because this, not for us, I mean, we already love space and we now know space. But the general public, I mean, this is a name that, you know, speaks to the general public. This speaks like the Tracy family and International Rescue, Deep Space Gateway. So, yeah, someone did right there. Then, of course, there's the Chinese space station. that we very often don't exactly know what's happening with it and how many people, etc., because, you know, the Chinese are not that open about it. And this, I don't know whether I can light him up. No, apparently not. The second guy from the right is the Dutch astronaut André Kuipers. And of course they have an official picture of their Expedition 30, you do understand. But if you go online, you will find many of posters like this, many other missions to the ISS that will have this whimsical idea. And apparently these guys felt themselves to be pirates. And I do think pirates are people that, you know, break the law, as far as I understood so far. So I can tell you no American female committed a crime before the 8th of June, 1983. I can guarantee you that is true, because that was the moment that the first American female went into space. Now, of course, you know, the Russians had, you know, Valentina Tereshkova already in the 60s, so no idea whether she did anything wrong, but otherwise I can say if there were crimes in space, no female committed one, guaranteed until that date. And I don't even say that, you know, Sally Ride did commit a crime. I don't think so. We would probably have heard it. So this is our space truth for the next 10 years. You know, we have Mars. Probably in 10 years' time we'll be there. We have the space stations, the ISS, the Chinese, the Deep Space Gateway. And truth be told, you can also commit crimes from the surface of Earth by launching a missile that destroys, I don't know, a satellite. Could be a spy satellite, but also one of the Copernicus Sentinel satellites. So, you know, it's not guaranteed that people on Earth never will do something for us, against us. So what's also in crime in space? Well, a spy, you know, is a spy satellite perhaps a crime committed against us in space? Depends, of course. We probably will feel who the spy satellite is the owner of the spy satellite. Of course, you can have satellites destroying another one. It's not impossible. I mean, missiles launched from Earth to space, to Earth from space, also possible. You know, you do remember one of the American presidents, Ronald Reagan, with his space missile ideas. Destruction of property in space or from space, because I can, you know, perhaps something big is coming down and destroys us. And, you know, you will say, you do realize that Mir came down, and thankfully it fell in the ocean, and thankfully, as far as I know, it didn't fall on any ship. But it was, for a time, iffy when this big thing was coming down, whether anything, you know, would happen to anyone on Earth because of it. Then, of course, there is stupidity. And the more people who go into space, exponentially, the more people might be stupid, right? And I'm not saying that an astronaut will never be stupid, but, you know, with the selection process and the 10,000 competitors you have, if you try to become an astronaut, with the training, with the fact that you know if you do something stupid, you might never fly, or you might never fly again, you know, there's a fair chance that they will be careful. But it's still possible. And of course, what if I am an asteroid mining company and I do something stupid? Now, of course, we have space tourists. And that's actually one of the worries that I have. Because, like I said, if I'm an astronaut and I have 10,000 competitors when I apply for the job, I'm probably really, really committed to be a good astronaut and to be, you know, obedient to the organization and, you know, be a good one. But now we're having space tourists. Part of these space tourists are billionaires. And some billionaires are really nice people, but there are also billionaires that aren't nice people because they feel they're entitled to everything. And this feeling of entitlement, whether that's on Earth or in space, is usually not a good idea for the rest of you around. So who knows? I mean, I remember Jeff Bezos going into the edge of space, coming down, and then, the next thing you hear, he's thanking his employees for making it possible. Do you all know what I thought? That was a space crime, the first, as far as I'm concerned. Do you know why? He could have given his employees a better salary. He still would have been a billionaire. Oh yeah, perhaps 20 billion less. So not 178 billion, but only 158 billion. But all his employees would have had a better life. So, I wouldn't call his behavior exemplary and the kind of person that I want us to bring to space. So, and like I said, not all space tourists, I say, will be bad, but some of them will have an attitude that we wouldn't want to have in a colleague on your workplace here on Earth. Now, what is a crime in space? Theft. I'm in space, I'm in a space hotel, and I want to do a spacewalk, and I damage my own, a part of my, my suit, so let's say a glove, which is essential, of course. And now I'm stealing your glove, because at least then I can do my spacewalk. But then you don't have a glove. So that could be a simple theft. Like I said, it could also be a simple theft of some special food that I took up, that you're eating. It could be physical violence. I mean, why not? I mean, we could have an altercation. You're in space, you can't really go away if someone is getting on your nerves. They're people, so they might get, there's sexual violence. We haven't had that in space as far as we know, but I know we've had that in 1999 in a simulation in Moscow that then was ended because of the mixed male-female crew. And the one female that was assaulted, the leaders of the experiment said, yeah, she shouldn't really, be too much upset about it because this was how Russian men were. That's really insulting to all Russian men, I think. But it was at least insulting enough for the Japanese astronaut, male astronaut, to walk out on the experiment. Because he felt like if that's, how you see men, then I don't want to be a part of this organization. So he walked out. Murder, why not? We're humans. Destruction of property, stupidity that harms someone, but also Earth. And of course, I think it's a crime under the Space Treaty to claim a part of the Moon, a part of Mars, an asteroid, unless I'm using it like going on the sea and fishing to harvest something. There are, but otherwise it's a crime. Now, what do we do if someone commits a crime en route to the Moon? Well, that's only 3 days away. You probably can take him or her down and, you can solve it. Not as easy as it would be here on Earth, but it's solvable. But you're en route to Mars, and that's a minimum of 6 months. And someone commits a crime. Then you have to figure out what crime is serious enough to abort the mission or, or to do other things to curb occurring it again. Will this be a card of go to jail en route to Mars? We're locking someone up, or we're locking someone up on Mars while we're there. That's not really feasible. For the very simple reason, we will not be sending these first few missions like a slew of people. It's not be a big buzz of 54 people. It will be at most 6 people. And we will need each one of them to survive, to not just make the mission a success, but also to simply survive. I mean, you can't lock up the pilot who's supposed to land us on Mars, because you might not, survive a landing then. And so there are other, if there are only 6 people, then any one of them is crucial to the mission, to survival as a group. So what do? And you go like, yeah, it hasn't happened yet. No, but it might. And we better think about it. Gender differences. We don't know yet about, gender differences of crimes in space, but for the fact that no female did a crime before the 18th of June, 1983, that we do know. But we do know this. Crimes on Earth is a ratio of 1 to 10, whether it's a female or a male doing it, which makes, of course, a big difference. So will we allow this, or will we say, oh, in that case, we're sending more women? I'm not saying that we should. But it's, one of the things we have to consider if we try to, make it there. Now, the other thing is, of course, should crimes in space be carrying a heavier sentence than they are on Earth? After all, space is very dangerous, and I don't have an extra crew member if you hurt a crew member. So it's not like, here on Earth that your colleague is hurt, and which would be really bad here on Earth as well, but at least there's a great chance that we can, have a temporary replacement of that colleague. Not so much in space. So now I imagine I have an asteroid mining company. And to harvest the, let's say, cobalt of an asteroid, I bring it to Earth. And I miscalculate. I push it just a bit too hard, and we all know in space things will not stop automatically. So if I make a mistake like that as a company, bye-bye Krakow. Too bad. And now you go like, of course, that's, I hope you don't have family in Krakow, but, you could say, okay, Krakow is gone, we'll rebuild or something like that. I don't think you will be that easygoing about it, but nevertheless. The thing is now, of course, also, the space treaty does make governments liable, but I just told you it was a private company doing the asteroid mining, which means that we don't have laws yet how to manage this. And we should, because, a mistake could kill thousands or even millions. So who are we sending into space? This is just a grip, of the present astronauts, female astronauts, because thankfully in Europe and in America we have more and more female astronauts, not just males. Finally we're getting there. Now, what court will be the judge? This, by the way, is the International Criminal Court in The Hague, what you're looking at, this modern building. Because if we have a crime in space, and we know that will happen, because, like I said, humans are humans. And it might not happen in the first year or the second year, but it will happen. Then we have to decide beforehand who is the organization or the person who will judge you. Because you could say, if I'm Dutch and I'm doing something wrong, and you're Polish and you're doing something wrong, we have a fight in space and we really hurt each other. That's not good. Now, will it be the International Criminal Court? Or, how and when will the judge be involved? While we are still in space fighting? Or will it after we've come down to Earth? If you're on the moon, it's 1.25 second time delay. That's not really a problem. But if you're en route to Mars or on Mars, there is a real time delay. So, you have to be self-reliant as a crew anyway. Does it also mean that we give the authority to the captain of the ship, like, the captain of a ship on the sea? What do we do? And the law differs per country. So, let's say, I said, Poland, but let's say Florida. So, I'm from the Netherlands, and I, fight with someone from Florida. Laws are definitely not the same in both parts of the world. So, what judge will educate? And if we say, it will be a national judge, you can see the problem here, right? Someone does something that is not considered a good idea, but because of prestige, your country, Florida perhaps as a state, decides it's not important because, the mission must continue, or, it's okay if a Floridian person, really batters that Dutch person. You don't know. That's why you really, really need to decide what court will be the group that is the valid organization to judge what's happening. Now, of course, we do have other laws, you know, like the law at the sea, and, you know, where are you at the sea? Are you, you know, at the close to the area at the territorial sea of a country? Then obviously it's the country that educates. You know, if you are, you know, the continuous zone or completely outside that zone in high seas, then of course, you know, so we did have, here on Earth, we do have situations that we already thought about. What do you do if it's not exactly in a state, in one country or the other? You know, how do you range? The thing is, though, the fact that we have this doesn't mean that it applies to space. It's just a model that we could use. But then we still have to write those laws, write those treaties. Where is space policy made? In the EU? These are the catacombs of the Congress in America, where I regularly am. Here, Vienna, United Nations Office of Outer Space Affairs. And like I said, the problem is that we haven't. When in 1967, of course, there were two countries that were fighting for being the best in space, right? So they weren't thinking yet that any one of us could have a space company that does things in space, and that you then need to have laws to manage this. So the space treaty says things like, no weapons of mass destruction, good. You know, no military bases on celestial bodies, so not just on other planets, but also on the moon or wherever, asteroid. Peaceful exploration and use of space. Like I said, that's a bit like the fishing at the sea. I can fish the sea, although the sea isn't mine. You know, then probably the same, you know, holds for asteroids. I can harvest cobalt, but it's, you know, the asteroid is not really mine. No national claims of ownership. It's still a thing. Can I, as a person or a company, and especially multinational, can I claim ownership? No contamination or harming of space. That makes, you know, sense, and it also means that I can't bury you in space. If I kill you on the moon, I have to find another way of, you know, disposing of the body. And of course, the liability for damage caused by nations. By nations. So the Netherlands would be liable if the Netherlands did something wrong. So probably it would be liable for a Dutch astronaut doing something wrong while in the service of NASA or European Space Agency. But if, I don't know, Airbus, the Netherlands, I'm not saying that they would, but, you know, let's name a company, would they do something? Is it then the problem of the Dutch government, especially since Airbus is an international company, you know, just has, you know, many different departments all over Europe. So we don't know. Now, of course, we do have the Artemis Accords, and in a way, these are also helping to tell us, you know, how are we going cooperating, how are we going to manage stuff, but it's a non-binding, multilateral between governments participating in the Artemis program. Governments, again, not multinationals, not companies. Signed, I think, very recently, now by 29 countries and 1 territory. Do we all agree what we need to do? And of course, I'm showing you this map because this is another way of looking at the world. Because, you know, it's just, you know, it's convention that the North Pole is north and the South Pole is south. But, you know, it's space, it's three-dimensional. So we could say that this is our planet. And as you can see, it makes a difference for how big the various continents are. So do we all agree? We have to figure this one out. You know, are there situations where we say, yeah, okay, it was a crime, and on Earth it would be really a crime that you get more than a fine, you would get jail time. But because it's in space and there are no other crew members to replace you, we have to let it go, at least for now. We can also then decide we won't let it go when you come back. then the thing is, of course, will I come back if I know that I then go to jail for 10, 15 years? I'm not sure. And like I said, there's only a limited time to figure this out, because 6th of October 2033 is at the moment the aim of the first mission to Mars. By now, I must confess that NASA is saying that by 2033 they will send humans to Mars, but not to land. So that then it would be December, 25th of December 2035. But still, you know, it's already September, nearly October 2023. So it's very few years to figure this out. And actually, if we're talking about space, this is what we should consider, of course. And not just crimes and not, you know, what all the nasty things that can happen. The thing is, though, if we send humans someplace, we have to figure it out. We have to. And as I told you before I started this talk, for many years I've been involved in trying to get humans to Mars and trying to figure out all the things you need to organize to make sure that people get there, people are safe, people are kept healthy, they do useful work, they do science, we can get them back safely, all these things, everything figured out. Until in June, the Liberal University of Amsterdam said, can we interview you about what your thoughts are on crimes in space? And I was like, oops. I never thought about this part of humanity, you know, the psychology of us as humans, that would also come into play. So for now, I am trying to figure this out together with university and others, and I'm trying to find a way to remedy this in a treaty or whatever before we send these humans to Mars. And I won't be in time for the people to land on the moon. You understand that, unless I manage to, you know, make this happen in the next 2 years. So that's my thought. So like I said, think about it. You're a billionaire, you can go to space. What crime would you commit? Someone already said murder, that's great. Any other ideas? What could go wrong? Okay, we are now sabotaging the competitors or the enemy. I don't know how I see this. Yes? What? Oh, yes, of course, drugs in space and you know, liquor, although that's usually already in space. Yeah, you know, true. You know, it's true, the things that are forbidden here on Earth, you know, what happens if I do take heroin up or cocaine to be able to perform longer? Yeah, you're right. I mean, that's something we need to figure out. Any other big crimes? Anyone thinking of anything?
Tax fraud.
What?
Tax fraud.
Tax fraud, yeah, why not? But I must say, it can't be cheap to first go to space to commit tax fraud. So, as you know, I can't say you're a very handy crook in that case. Yeah, it's true. You know, and like I said, you know, in reality, of course, there already has been satellites that damaged another satellite. And sometimes it's not completely certain whether that was done, you know, by accident or on purpose. So it's not like we don't, you know, we're in the Liberal University and me, we are interviewing people about, you know, what crimes can you imagine? Do you know whether crimes already were committed? So far, no one has fessed up, even by knowing a crime of someone else. And of course, a bit of a problem is that astronauts probably can't freely talk about it, even if they would know that someone stole from someone else at the ISS or something. They probably can't, because they probably, you know how it is, right? Astronauts don't fart, because, at least the European Space Agency, JAXA, and all the others, they will deny that astronauts are normal people. Of course, astronauts know they're normal people, but, because we do have this, not perhaps us, who are very much involved in space, but for the general public, we very often have this feeling that we need to make it look better than ordinary life. So we don't know. But so we're interviewing people to find out and to, also talk to the UN and UNOSA and all these. We're setting that up to figure out whether we can organize this in time before humans go really into space. Mars, I said, but it also in the next 10 years, I don't know, because sometimes developments go really fast. There could be a company suddenly that makes the decision to indeed mine an asteroid. It has also a bit to do with how much it would, what profit it would bring, because how rare the element is that they would harvest on that asteroid. So that was my talk. Like I said, food for thought, right? And please don't plan crimes in space. I asked you to imagine it, not to really plan it, okay? Promise? Okay, any questions, by the way? No more questions? Oh. A hacker or something, yes, why not? I would consider, the moment I hack the systems of the ISS, I would consider that a crime in space. Because, although it is committed from indeed a desktop here on Earth, it would affect space travel and space operations in such a way that I would hope it would fall under a crimes in space judge. Because of the effect of it. I mean, it's already very nasty if they hack you here on Earth, but let alone that. Okay.
Thank you. Do you have any more questions? If not, let's thank Artemis again. Thank you very much.
You're welcome.
And you can stay with me here to finish our Artemis Day during European Rover Challenge 2023.
Name, right?
So, okay, it's the end of our meeting today. It's the end of our broadcast as well. Let's have some more informal discussions after this event formally ends. And see you tomorrow at 10 a.m. We see each other here, and we're gonna experience the Earth Day, the last day of European Rover Challenge 2023. Thank you very much.
We should go to Mars.
We should go to Mars.
Because it's human nature to keep exploring.
Because we want to discover intelligent life in our solar system.
Because establishing a presence out there is a huge stepping stone to limitless possibilities.
Because we can.
Because our ambitions exceed this world.
Because humanity has unlimited curiosity and is destined to conquer the universe for good.
We should go to Mars because it's been long enough.
Because it helps to develop new technologies that are also very useful on Earth.
Because look at Mars could improve the way we look at our Earth.
Because Mars exploration is a huge milestone to extend our vision and discover a new home.
To play sports in low gravity.
And to define past, present and future of our planet.
It opens doors of opportunities for developing talents like us who wish to explore newer horizons and decipher the unimaginable.
We should go to Mars because the sky is no longer the limit.
Space industry is booming all over Europe. And so whether you're Luxembourg or Portugal or Spain or Italy, you know, whether you're big or small, you try to be part of this.
I cannot imagine a better way of preparing people for our future projects than, competitions like this.
And all these jobs are there to be had. So if you're studying something that you think has nothing to do with space, check again. You might find out that 10 years from now, you're actually needed.
Great engineers and great scientists building great products. That is what the space industry consists of.
There's something deeply philosophical about space.
And we are the first generation where Mars is just about to be at the reach of our hands. It's a logical continuation of feeding and nourishing that nomadic gene that is within us as humans.
The most important and fundamental part of being human is imagination, this aspiration that we have, which drives us to explore space. So this is something to be proud of, this is something to celebrate.
The cooperation is obviously not just between governments, but it's between the private sector, academics, non-governmental organizations, even students that are combining math and science studies with imagination and creativity.
One person can make a difference and therefore should. That's my assignment to you.